Testing, testing. Yeah? Great.
Test the mic.
Yeah, but the lectern, right? Oh, I thought they were using the lectern.
It's whatever you want.
Is the lectern? Oh, there you go. The reverb from that. All right, with that, let's begin. Hi, everyone. Good morning. And welcome to the 11th edition of Cloud Native Rejekts. I would wait till the end, but we can vote and clap now. It's so nice to see so many of you here. So many of you I'm still getting to know. So many of you I don't know. So many of you I do know. So bear with me. And yeah, and I'm Benazir, by the way. I'm Benazir Khan. I'm a community program manager here at Microsoft. I've been running a few of these Rejekts events, and it's so happy. I'm so happy to kind of see the overwhelming response to it each time. We're almost not able to deal with how good it is in a great way. And yeah, so I'm so happy to be welcoming you today. I'm joined with an esteemed colleague, with Ralph Squillace, and Ralph will talk to us more about his experiences of being in the program committee this time, and also kind of the schedule at large, some of the content we've seen. I do want to say that we received over 200 proposals this time. I didn't want to have like a spectacular graph or anything shown. I've tried that before, and I'm like, I think there are many people with a lot of stats here today, so I'll just keep it to that and say that it's great that so many folks actually think of Rejekts as this great venue and this great platform where they can submit their rejected proposals from KubeCon, sometimes even brand new ones, I've been told by the program committee. So just goes on to show its importance, and we hope to keep that growing and that momentum going. And yeah, just want to say that there's a couple of rules I'd like to share here with you. One of them is, of course, please collect your badges. Meet the registration folks. They're volunteers from our community, so it's nice to say hi to them. They're friendly faces. And they'll help you get your swag and your badges should have this QR code, which will take you straight to the conference schedule. Please consult the schedule at all times to see what's on. And yeah, speaking of the program committee, big thanks to Natalie, Laurie, Joseph, Mario, Carlos, and Ralph. Ralph, take it away with what you thought about some of the talks.
Let's see if my voice holds out. I was in Barcelona doing a WebAssembly conference before this, so I'm a little gravelly because there's lots of fun things to talk about. But right here, I just want to say that the bulk of all the work is done by everybody else on the program committee. And so I want to thank them because they, of course, spent their time volunteering to go through all those 200 applications. Many of them also did the CFPs for various areas in CNCF and the KubeCon thing. So we're talking about hundreds and hundreds and hundreds of applications per person. And they try their very, very best to deliver the geekiest crap they can possibly find for everybody here. Because that's the fun part of the stuff, that people like you will come on the weekend, on the Sunday or the Monday before the conference, to really dig into some subjects. And for example, there are some AI talks. I don't know if anybody noticed, not that many. That's great, because then the ones that are here you can think about like in a reasonable way.
Yeah.
But there's a whole bunch. There's a whole bunch of talks that are about pushing the edges of the envelope in and around Kubernetes, containers, and other kinds of processes, specifically in the Linux world by and large. There's edge talks, which are really, really going to be important because the network can go everywhere, and public cloud is a known entity. Most chips are off of public cloud. Most computing, as we roll forward, will not be in, and is not now in public cloud. So this is critically important area. Another one is getting the gearing of Kubernetes to run faster, to not be just the kind of lazy data center style reactions that we're now very confident that they work. We now need to press those kinds of gears faster and faster. And so there's a whole bunch of talks that do that as well. And I just can't be happier and more interested. I'm really happy you're all here, but those people did all the work. One last question. Are all of you, how many people are kind of more or less local to the UK? Not nearly as many. I mean, it's a bunch of people came here because they had the opportunity, right? Fantastic. I think that's great. Oh, and one other thing. The sponsors that do this work, we represent Microsoft. That's great. I'm glad we're still supporting all this kind of stuff. You can never take that for granted. However, I want to call out Suse also for constantly supporting Cloud Native Rejekts, right? When a big company that is not the main sponsor continues to support financially these kinds of gatherings about geeky engineering specific stuff, it says something about the quality of the company. And so I want to actually call out Suse and thank them very much, along with the other sponsors. That's what I got to say.
Yeah, lovely. That was a cool segue. So yes, big thank you to our sponsors. We really couldn't have managed to do this without you. You're seeing the venue. It's wonderful and plush and posh. So yeah, I was just sharing with a few colleagues earlier that there was a running joke with the venue, which is that I kind of had to keep intimating them that this is not the crowd that will dress up. So if there's a dress code you want in place, just be aware of that. And yeah, but you're very welcome to. As you can see, it's not obligatory, but if you want to dress up, I've had a few folks reach out to me and go like, what if I do want to come up in a tux? And if that's what you want to do, you're very free to do that. And as you can see, it's very befitting for the venue anyway. Yeah, I'd like to thank Microsoft. Of course, we're from Microsoft and everything, and Ralph's touched upon the importance of doing events like this, but also, for Microsoft to go ahead and, make sure all tickets are free for everyone, that it's free to attend for all. We also have some tables. Tracy's here. Tracy's from the Microsoft research team. She'll be sitting at the Microsoft table, and she'll be conducting some fun surveys for you. So feel free to go and chat with her at any time. And of course, we also have tables with SUSE, CNCF, and Isovalent. Thanks to them too for sponsoring. And I'd really like to emphasize that, we don't really have booths, and we keep it very casual and make sure that sponsors still have some visibility, and because they've actually helped us get through all of this and get all of this in place, do spend some time with them, talk to them about their projects and their plans in the CNCF landscape. And yes, thanks to our other sponsors too, to Dagger for consistently coming on board for the last event or two, and to Cube simplifying the new stack as well. Make sure you find the sponsors also strolling around from time to time, so you can chat with them about anything topical and of interest to you. I'll go on to the spaces that we have here, which is, you're here at the Nash, which is the main room. This is the main track. We're all basically, the entire event venue is this floor. We're here at the Nash. This is where all the plenary sessions will happen. This is where the lightning talks at the end of day 2, which is tomorrow, will also take place. We have the Waterloo, which is the other track, where you can also, attend other talks. Check the conference schedule for what's on. I oftentimes find people who are confused between one room and the other, so the conference schedule should be a good guide for that, and there's enough signage placed around. But if there are any questions, please ask registration or one of us. There's also the common areas that are St. James 1 and St. James 2, like I pointed out earlier, with the sponsor tables also being there. Feel free to also work in one of those rooms while getting your coffee and tea and everything. I'm afraid we don't have too many chairs around, but I think it should suffice. Please be respectful of the CNCF Code of Conduct. And I'll quickly end with this lovely photo that we took just early this morning. Everyone here, these are the lovely volunteers that actually came here at 7 a.m. to help out with the setup, because the venue was shut yesterday. So big kudos and big thanks to them, because as you can imagine, this is all a community effort, and yeah. We do look like a happy bunch, don't we? Yeah. Oh my God, okay, there's also like horns on Emma there. Okay, yeah, but yeah, feel free. But feel free to chat with any of us folks here. I don't think everyone's pictured here, but of course there's a ton of folks who came together to help us get this conference through. All right, then I'll leave it to you, Orlin, to take this further, and we can start. Yep.
Thank you.
Yep.
No? Oh, whoa, okay. Hello, everyone. My name is Orlin. Hi. I'm your host for this morning. So if you have any questions about room, about the schedule and everything, you can ask me. And next we have Joe Salisbury. He's going to talk about cluster API migration. So warm welcome to Joe.
Give me a second. We got to start with the geeky shit, which is working out presenter view. Where does this live? There we go. We're very ready. There we go. How do I make this like full screen? There we go. There we go. And obviously I can't get the little thing back here now. There we go. Perfect. There we go. Can everyone hear me? Can everyone see the screen? Fine. Let's start. I'm here to talk about these obnoxiously large letters. At Giant Swarm, we recently did and are working through the end of a large migration from our homegrown Kubernetes cluster management system to Cluster API, which some of you might have heard of. That involved migrating a whole bunch of enterprise production clusters without downtime. I reckon that might be interesting to some other folks, so I thought I'd say a few words about it. Just thanks to Rejekts for giving me the space to do that, and thanks to everyone else for coming to London, because it's nice to have people visit the hometown. For those of you who've not had the misfortune of meeting me, I'm Joe Salisbury. I work at Giant Swarm as VP Engineering. At some point, I'll have a good description of my job, but basically today my job is talking to you all about some of the stuff we've been up to. Hit up the link tree or scan the QR code for socials. I don't really post, and it's crap when I do, but maybe you're into that. I'm going to talk about where we started, how we made our decision to go on this journey, what the migration itself looked like, some problems we knew about, some problems we didn't know about until we got there, and then some reflection on our overall approach, our overall journey, and share some things we were forced to learn along the way. As a note, I'm going for more of a coherent story than some sort of company archaeology project. So while this might sound straightforward because of the linear nature of a presentation, it really is also a multi-year journey with a ton of iteration. We're putting several years into half an hour. Let's dig into where we were at before we started this migration. For those of you who've not heard of Giant Swarm before, I'm super offended. Leave. But all these statements are true in some way. We build, operate, manage cloud-native developer platforms for enterprise. We deploy software into our customers' accounts. We take the pager. We allow platform teams to focus on differentiating work that's sort of more specific to their company. The general aim is to help platform teams be more successful in an enterprise context. And towards that, this is what our architecture. Let's get into the geeky shit. This is what our architecture very roughly looked like before the migration. It's a sort of very high-level view of our Kubernetes as a service product before the migration. You can kind of think of it as a REST API to CRUD Kubernetes clusters. You have a sort of web client and some REST APIs at the top. The Kubernetes operators, that's the sort of core of it, and then infrastructure providers. The operators are the sort of key components here. So, for example, the AWS operator, which is probably the thing I'm going to be talking about the most, we started in February 2017, and it's so old it used TPRs before CRDs were a thing, which was a fucking nightmare. And you'd get one of these boxes installed sort of per cloud region or data center. It's sort of part of the management cluster. And if we just look at the AWS case and sort of more the data flow, you have that REST API creating a cluster custom resource, right, which describes the desired state of some cluster. The AWS operator then reconciles that CR into a set of CloudFormation stacks, and those stacks then form the actual Kubernetes clusters. And we'd have the same for our other providers using whatever CloudFormation is on Azure. I don't remember. There we go. And topologically, in terms of how this is laid out, we'd sort of set it up in a management cluster to multiple workload clusters set up. So the management clusters are responsible for managing the infrastructure, and then the workload clusters are where your actual customer workloads or deployments are run. and we'd have one MC per cloud region or data center per customer, right? And then we're sort of taking care of all these management clusters. And there's no sort of shared infrastructure between management clusters or customers. That's enough about Giant Swarm. Let's move to Cluster API. This is the, I'm about to say this is the earliest reference Marcus could find in our Slack to Cluster API. If you search cluster and API in a technical Slack, it's a nightmare. And this was a bit after it was getting kicked off. This sort of second quote, you can see one of the sort of keps beforehand. None of these links work anymore. But you can see the push around having a declarative API for cluster management. And yeah, to dig in, Cluster API also started in 2017. It's now a fully fledged Kubernetes subproject around having declarative APIs or custom resource definitions and tooling for managing Kubernetes clusters, right? Users include, well, us, but other companies like Red Hat, Azure, I think Mercedes and Twilio and stuff. And the idea is to have Kubernetes operators to manage Kubernetes clusters, which sounds familiar. Yeah, see, there's foreshadowing. I've stolen this from the Cluster API documentation, and it sort of shows the architecture briefly. So you've got the controllers to the left. They sort of support more infrastructure providers and different ways to provision Kubernetes, so they sort of split out the behavior a lot. You've got custom resources to the top right and providers to the bottom right. I'm not going to go into detail on specific controllers and custom resources. I'd recommend finding a Cluster API deep dive talk from people who actually know what they're talking about. But there's some notable similarities in the overall design, right? You stick a custom resource in, and you get a Kubernetes cluster out. But there are some notable differences, right? I can use my laser pointer. BAP. Cluster API has a sort of shared controller that we didn't have, and they've sort of also used different Bootstrap providers as a separate operator, where we had like a shared library in Giant Swarm. There's a few things like that. Topologically, it's a similar layout. This is one management cluster. You then have a number of workload clusters. And they're already supporting, at this point, sort of a more flexible topology around providers, whereas we had a sort of one-to-one relationship. And yeah, at a certain point, we realized we were somehow building the same thing, or at least building towards the same thing. There's a shared basic set of features, and some features in Cluster API we'd like to have, and some features we knew we'd have to add. At the very least, there's some isomorphism between the two systems. I couldn't get the joke onto the slides, but that whole thing about like all crustaceans eventually become crabs body plans, it's like all cluster management systems probably evolve into something that looks like Cluster API. There we go. I'm just using a single train emoji because I couldn't find a way to describe the whole bunch of internal discussion that I'm going to really hand wave over. But eventually we got to a point where we were in the understanding that Cluster API would probably be a better way forwards than building our own internal controllers. The major benefits we were looking for were not having to spend as much time developing our own controllers, right? Like maintenance around new Kubernetes releases was quite onerous. There was definitely some features in Cluster API we wanted to take advantage of, and with new providers, we definitely wanted to be able to sort of use the community there. We previously reckoned it would take one team around 6 months to sort of build out a provider, which is just a heavy investment. That was something we're trying to improve. So yeah, let's talk about the actual work of getting from our custom controllers to Cluster API. Just for some jargon, because otherwise I'll confuse everyone. We ended up naming the old legacy system Vintage. I wasn't in the meeting. The new Cluster API product is Cappy or Cluster API. Creative, names are hard. So there's an old system and the new system. The old system is Vintage, not Legacy. It's a nicer name. The new one is Cluster API or Cappy. So I'll say Vintage, translate Legacy. It's just too ingrained in my brain at this point. We were running on 3 providers, so AWS, Azure, and KVM. Hopefully, AWS and Azure are obvious what that means. KVM was a custom bare metal solution that used KVM for like nested virtualization in Kubernetes. It's another talk, ignore it. Think bare metal. And Cappy has multiple providers, so the naming pattern is sort of CapX is Cluster API for X. So Cluster API for AWS, Azure, and vSphere, I've checked my notes here, and VMware Cloud Director, which is a different virtualization product. I got it right? Which I learned about while we were doing this. we decided pretty early on that we'd have to perform a managed migration for AWS. For us, it was a large number of clusters, and we want to provide as much value to our customer platform teams as we can practically or pragmatically. And also as a smaller team, prolonging the time we'd have to maintain both systems would be painful. We had a breaking change on Vintage in late 2019 that required customers to move clusters, and it was just painful for everyone involved. For Azure and KVM, we actually opted to not perform a managed migration. There's a smaller number of clusters that, sorry, Microsoft. Some customers were on and offboarding, and we reckon it just wasn't worth the investment, especially with moving from the sort of nested virtualization to vSphere is just a project I wouldn't want to be on personally. So the live migration part covers AWS only. I'll sort of implicitly talk about AWS from now on. With the other providers, we built them out as part of the new product line. And new customers would create those clusters. Old customers, we had to sort of handle them with a sort of manual migration. This is a fun organizational quirk. Timo, this is your slide. Early on in the journey, we organized what we called a hive sprint, which is very on-the-nose naming, I know, for Giant Swarm, but names are hard. The aim was to get the whole company to understand, try out, and ideally implement the migration from Vintage to Cluster API. So we actually just took a month, suspended our usual teams and meetings, self-organized new teams, and hacked on Cluster API. We didn't manage to do the migration in a month. It took a little longer, but it did work well for some other reasons. We got the whole organization to understand the future direction. People got in touch and tried things out with Cluster API, and we managed to sort of iterate on blockers and issues quite quickly. And it kickstarted a lot of the larger decisions that we sort of then followed up with in the following period. And yeah, sort of coming out of that, we found Cluster API wasn't a 100% fit as a replacement, right? And to some degree, why would it be? We also found that different Cluster API providers had different levels of maturity, like they're essentially different projects, and then sort of required different levels of investment. This is one of our many GitHub issues tracking various work. Because a lot of the time between the sort of hive sprint and now was spent on product development, which I think interestingly is various pieces of work. There wasn't any sort of single horrendous bug fix or major feature. It looked more like stability and security and enterprise requirements, right? And I quite like this actually as a good example of how open source projects actually get built. It's multiple parties working together, and it's that hard work of you have 1,000 small features and bug fixes to ship and upstream. Because yeah, if you're adopting open source projects, they won't get where you need them to be if you're not putting in the work upstream, to be blunt. As a fun problem, if you work for HashiCorp, you legally have to leave the room before this part of the talk. We built support in Vintage for using HashiCorp Vault. It's like a secret store for PKI and sort of certificate management. So the AWS operator would indirectly talk to Vault to issue certificates and then distribute them to worker nodes with Ignition. Because we're using Flatcar, thanks Kinfolk. And we'd then use a sort of separate PKI route for each workload cluster because it's like nice for security. When we migrate, we need to have the same certificate route, otherwise things get super fucking hairy. I tried not to swear in this one, I did that there. We knew we'd be using kubeadm for provisioning the Kubernetes clusters, and with kubeadm you can give it a CA cert and a CA key, and that works and it's all fine. The fun fact is with Vault, it won't give up the root CA signing key. It's part of their security model that you only get the root CA cert. So what we ended up doing was forking and patching Vault, so we have a insecure version of Vault that will give you the root CA signing key. So at the start of the migration, we moved to our hack version, and we can then use that to put all the certificate material out. It's a sketchy thing we did. For the actual work of the migration, we decided not to mix Vintage and Cappy in the same management cluster. It's more straightforward with like Kubernetes API versioning. And in the Hive sprint, we manually proved you could migrate, and we started building that out into a CLI tool, which we creatively called Cappy Migration CLI. Names. And at a very high level, you can understand the migration as moving the workload cluster from the Vintage management cluster to the Cluster API management cluster and transforming it from one to the other sort of during that. Because people asked, we did have some other approaches we sort of discussed for handling the migration. The CLI was what we ended up doing. We also discussed having a sort of operator solution to more automatically handle this. and some ideas around sort of like a blue-green Kubernetes cluster solution. The CLI is what we ended up with. It's practical for our number of clusters, right? It's in the hundreds, right? It's doable, and the development is very straightforward. If we did end up doing thousands or tens of thousands of clusters, we would have done the operator, but we reckon it would require more development work for a sort of fully automated solution. And the sort of blue-green option was the least explored. A lot of our customers have really limited IP network space, so sort of doubling up a cluster for the migration just isn't practical for them because enterprise is a nightmare. And for the actual migration process, I found it best to discuss the migration in two parts. This first part relates to the migration of custom resources and that management, and the second part relates to the sort of the infrastructure and the management of nodes. So our CLI takes care of all of this, but what we're essentially doing is fetching all the cluster custom resources from the vintage management cluster. So those are the sort of CRs that represent the infrastructure. And then we'll use our hacked vault to migrate the secrets from Vault into the CAPI management cluster. We'd have switched that beforehand, and we'll then stop reconciliation of the old controllers. We have a pause annotation, and it's so that the old controllers don't try to sort of start migrating back, right? You have one hand on the wheel. And what we do then is the CAPI migration CLI has logic to translate from vintage custom resource to cluster API management, cluster API custom resources, and it will then apply those to the cluster API management cluster. And if you then look at it in terms of, this is a horrible slide, I'm so sorry. If you then look at it in terms of nodes or the infrastructure, the cluster API workload cluster starts coming up, and this is where the actual migration happens. I'll break it down by etcd and the control plane and workers, because this is a complicated thing otherwise. etcd is probably the most interesting part, or the most complicated part, because it's etcd and it's kind of the core of the cluster. What you actually end up having is we start off with Quorum with a sort of HA etcd cluster from vintage. One cluster, you sort of read it left to right, yeah? One cluster API control plane node will start, it joins the cluster, and amusingly, cluster API's etcd management will then kick out the unknown vintage members. One of the engineers referred to this as a virus, and I kind of like that analogy. And then once it's kicked out the other two members, then as the next two cluster API control plane nodes come up, they join the cluster and you've fully replaced it. The control plane and the workers somehow are symmetrical. We start off with the vintage control plane. The CLI tool is actually adding the CAPI control plane nodes to the vintage ELB as they become ready sort of throughout. So we always have healthy targets. But essentially, as the cluster API control plane comes up, it's talking to the same etcd cluster, the API server is stateless otherwise. Once that comes up, we stop the control plane components on the vintage nodes, and then cordon drain delete. And with the workers, once new workers have come up, we then start for each node pool, cordoning, draining, deleting. And it's a ship of Theseus vibe, right? Like if you replace all the planks in the boat, you have a new boat. That's my philosophy anyway. And yeah, this is the most important thing I want to share. Churros time is a really important time of the day. At this point, we've ended up with the workload cluster entirely replaced and managed by cluster API, so somehow mission accomplished. And I think it's interesting that if you exclude the special cases, right, so Vault generating the new cluster API resources or migrating the management cluster, it somehow looks a lot like a regular Kubernetes upgrade, right? You replace the control plane, you replace the workers, you've upgraded. As a note for the networking of the clusters, we actually sort of preserve the VPCs and DNS before and after. Those aren't affected here. Cluster API or Cluster API for AWS has features to support that, and our aim is then, like with VPCs and DNS, to sort of slowly migrate that over time in less customer impacting ways. And these are the commits over time for the migration CLI tool. The first few migrations obviously exposed issues, and we also found we'd encounter new issues every time we migrated a new customer. Or in the other way, there are some clusters that are just gigantic, and we found issues there. It's a whole other talk to go through the bugs, but if you're interested, there was one bug where we ended up with different default node siders. So we were like using a /25 in vintage and then accidentally a /24 in cluster API, which led to pods having the same IP address, which is a nightmare when that happens. We had one customer who'd manually done changes to root tables in their AWS account. So when we migrated, it didn't know where the root tables were. And we also doing migrations in AWS China. And if you've done stuff in AWS China, things are just weird there. But yeah, with the CLI approach, sorry, if I hit this, it's an awful sound, isn't it? With the CLI approach, it just requires the lead work, right? We started with a nice customer, not our non-nice customer, and you can take an iterative approach with these things. And with the actual migration done for one cluster, in a repeatable fashion, the job becomes customer management, and our account engineers do a hell of a good work here. Because there is actually a fair degree of customer management, especially with enterprise, right? You have change freezes, you have stakeholder management. With one enterprise customer, they wanted a video call for every migration, and they have hundreds of clusters. But after migrating several together, they gained enough trust that they only joined in for high-level environments, production. It becomes a lot easier. And I don't have any wood here. I will knock on wood later, but we achieved all the migrations to date with no data loss and wording, no major production customer workload impact, because dev clusters did get a bit hairy. And yeah, this is the schedule for next week. I don't know which clusters. I don't think I will talk about customers. That's not a good idea. So yeah, let's talk about some reflection. This is the retrospective side of this. Yeah, there's just a lot of emoji slides. I'm sorry, I'm not good at slide design. I think one thing we learned was you're always going to be juggling more than one migration. This was not the only migration we were doing over time. You can't stop the world and just do this one thing. So for example, we ended up replacing our custom SSH access solution with Teleport, or we moved from that REST API to a sort of Kubernetes API solution with SSO, and we built GitOps support. And there's all the rest of the development we did over 5 years. And I think with my engineering hat on, you'd love to be able to do one thing at a time, but realistically, at any thing apart from a small scale, it's just not feasible, right? So we sort of ended up sort of embracing the juggling, which is a phrase, don't like that as a phrase. And we were also initially worried that using an upstream solution would slow our pace of development and then sort of lead to customer frustration. I think that's because we ended up doing bad things with our custom-built solution, right? We were very happy throwing out a hack quickly to make a customer happy. But we ended up having a really positive reaction from using a fully upstream solution, right? I think the upstream actually makes their decisions with more consensus, there's more use cases, it's a more flexible architecture. It's that sort of get it right to go fast vibe. And I think we'll end up actually also thinking more upstream across the company, which is quite nice. And interestingly, upstream's kind of turned out to be a source of authority with our customers. Like if we tell our customers, this is what we understand upstream's ideas and their direction, they take that as written, and it's actually quite powerful argumentation for us. With team topologies, at a company level, we had a balance between sort of keeping existing customers happy and working on the new system, right? If you start reading like Mythical Man Month, Second System Effect, that's some sort of stuff here. To begin with, we had one team working on both Vintage and Cluster API. It kind of worked to begin with when Cluster API was a lower priority, but given the degree of work and customer support for Vintage, with both priorities in the team, we ended up just not developing Cluster API as much as we wanted. So we ended up splitting the teams. We had one team working on Vintage in more of a maintenance mode and building that capstone release to launch the migration from, and the other team with the primary priority to sort of get Cluster API to production or migration ready state and sort of land the migration. And that's when development really started taking off. We did also start using CapG, so Google Cloud, and Capo OpenStack while we were quite early in this journey, so sort of building out that product line. We had some customer interest in these providers. We definitely learned a lot from Cluster API, or sort of about how to manage new providers. It was definitely tough and distracted from the migration, or sort of building out those other products. I think my learning here is like trying to reap the benefits of a migration before it's done, right? We weren't really there to use it sort of at that point. But we've definitely gotten to a point now where new providers aren't particularly scary. 5 minutes, oof. So we're definitely a lot further with integrating Cluster API into our product, as well as supporting and bringing up new providers. For some reason, people aren't as keen on VMware for some reason lately. It's an easy joke, that one. So for example, with Proxmox and Nutanix, we're investigating the new providers. We don't think it's actually going to be that painful to bring up. It's definitely not going to be a one team for 6 months, which is the big benefit there. And I think one of the most interesting questions, or for me personally, has been when to replace a custom-built solution with open source. I think very often you can choose an open source project and it'll do exactly what you need it to do, right? You're not going to have to push a PR to Node Exporter for it to do what you want. because it's feature complete, not shading on Node Exporter. But some of the time, especially with more complex requirements, the project is close but won't match 100%. The project will develop and mature, but it's not going to eventually magically add your requirements. And you need to do some degree of the work, but when do you do that work, right? And I think I'd actually reframe the question more as, is your solution custom or differentiated to customers, and will it differentiate in the future? So I'm going to very quickly throw up big graphs. This is a Wardley map. It's a tool for describing value chains. The y-axis represents how visible something is to a user, and the x-axis sort of represents commoditization. At Giant Swarm, we want to provide internal developer platforms that has requirements like Kubernetes management, Kubernetes clusters, and compute and stuff like this. And these things are all commoditizing over time, right? Like, compute is now a commodity. And for example, with Kubernetes clusters, we've seen them move from custom built into more of a product to where I would argue they're more of a commodity now. And I think as a component becomes more commoditized, your methods change, right? You're sort of moving from agile into more, you can actually build a community around it together, right? You're going to have a group of people with requirements. And I think that's the inflection point where to replace a homemade component with an open source component, right? Where you actually can have multiple organizations working on it together. And then, as individual companies, we still want to be competitive. We can move up the stack, right? Or in another way, your company has a limited number of innovation tokens. Don't spend them on things where you can work together with people. Spend them on the things that differentiate you. It's theory, I don't know. Here's a super scary looking diagram. I will not go off into this. I'm not going to explain connectware. But this is, for example, our newer hybrid smart factory industrial IoT platform. This currently is working at producing 1/3 of all the toilet paper in Europe. Fun fact. But we run a management cluster in the cloud and worker clusters in factories on VMware and stuff like this. And this is what we've been able to start doing since migrating to Cluster API. We're building on functionality on top because we're managing to make use of that open source product where we're all collaborating and sort of building on top. Don't take photos of this. It's not good. And I'll start finishing off. This is a bunch of really attractive people. One theme I had because I had to talk to a bunch of people in the company to prepare this talk, everyone noted that it was very much a team effort from the whole company. So this is me saying thanks to everyone who pushed this effort in any way. I wouldn't be able to talk about this and pretend I did all this work if they hadn't actually done the real engineering. This is us in Morocco. It was lovely. So yeah, that's all. I think I'm in time. Thank you very much. If you're on a platform team and want to do less of this, talk to me. Thank you very much.
We have time for maybe 2 questions.
Oh, fuck. Yes.
Sorry, you rushed too much. All right?
I've taken the slides off, so if I have to reference something, I'm dead.
Hello, thank you for the talk. I wanted to ask, what concerns, especially the technical ones, do customers see when migrating? Because I can imagine that they are scared of the unknown. They are maybe scared of the complexity. But is there something valid, maybe technical, from your perspective?
I mean, it is a fairly intensive procedure for a cluster. Let's put it like that. I think you end up sort of into a customer management stance, right? Like we have a lot of preparation there in terms of explaining to them what's going on. And we would all, with some customers, we start new clusters and then show them the migration on that, so it's not even close to a production. And then we'll work from low environments to high, right? We know it works, customers don't know it works, and that's very valid. So, we start off with tests, making sure they really understand the solution, and then sort of work upwards from that, yeah. We have a long-term relationship with most of our customers, so they generally kind of go, okay, we'll work through this together and go from there. Yeah.
Right. Thank you. Once again, thank you to Joe. And next up, we have Daniele and Thilo from Microsoft. That's their keynote. Daniele and Thilo. No? They were here. Benazir? Do you know where Daniele is? And Thilo? Sorry, I had to do the question thing.
You got to throw one.
they'll come up. Hello, welcome to the stage, Daniele. All right, Daniele and Thilo are going to do super short keynote from Microsoft about the community effort at Microsoft. So you have 5 minutes. Hi.
Hello.
Hi.
How's it going?
Pretty good.
Good to see nice, friendly faces here. We're from Berlin. We like to keep it, casual.
Sorry. Okay. This is you. So.
We have a
Here you are. Oops. It's point and click. Just. Yeah. It's really just fully automatic point and click. Zoom is here, and then you shut and then.
all right.
All right.
So, just a second. There we go. So, today we're going to talk about building on Azure with open source. Hi, I'm Danielle, and over here is Thilo. We work at Microsoft on open source software and with open source communities.
And it just worked a minute ago.
Okay.
There we are. Open source open source adoption isn't just about starting to use the code. It's about embracing an open mindset and fostering a culture of knowledge sharing. Open source provides the infrastructure for companies to focus on their core competencies as it helps them to keep up with the pace of industry innovation. Thank you.
Organizations are seeing 3 times higher impact through the adoption of open source. And open source and score 30% higher on innovation and 20% higher on developer satisfaction. Just as our customers are choosing open source, Microsoft is participating in its rich ecosystem and immersed community. The list of cloud-native software, for example, is growing all the time.
We also increased the contributions we make to open source projects, climbing from rank 3 to rank 2 of the top contributors to open source projects in the CNCF over the last year.
Let's look at projects that help us to build on Azure. I'll give you a quick overview here, and I encourage you later to explore this list, dive into it. There are many available tools in this space. Let's talk about infrastructure. In the Kubernetes project, we lead releases, step security response committee, and also help running the SIG-OAuth. We help steer Istio service mesh and work with the Envoy community.
Hyperlight is a lightweight virtual machine management for micro virtual machines written in Rust. It helps to secure your workloads through isolation while not compromising on performance. It's especially useful for WebAssembly workloads. Developers. Microsoft has a rich tradition in developer tools. We've been the creators and longtime maintainers of the Helm package manager for Kubernetes. And Radius is a software application framework that allows you to develop for multiple environments, thus abstracting infrastructure and providing consistent workflows for both developers and operators.
The Headlamp open source project from the Cloud Native ecosystem team is now being proposed as the new Kubernetes desktop. Security. Open Policy Agent Gatekeeper is a customizable webhook for enforcing Kubernetes policies. Donated to CNCF in 2018 and since then adopted by all major cloud providers, it is integrated with Azure Policy, now a widely used security feature with built-in policies for AKS.
And Ratify verifies container image metadata, and together with Gatekeeper, it builds the Azure Image Integrity feature, ensuring authenticity and integrity of AKS images at provisioning time. Copacetic helps you to cope with operating system security issues by scanning operating system packages in your containers and adding a patched layer on top, eliminating the need for full image rebuilds.
We understand community is something that is larger than the sum of its parts. Our community investment go above and beyond what is needed for Azure, and aiming to sustain and to strengthen the whole ecosystem. We support projects like Cilium, Inspector Gadget, and Flatcar, building a sustainable infrastructure.
Our community managers help in advisory groups, in technical committees, and in working groups to build and to maintain successful open communities. And lastly, we organize events like Cloud Native Rejekts and a number of Cloud Native meetups around the world. Open source software fosters innovation and attracts developer talent. It has revolutionized the software development industry, as we have witnessed in our own transformation as a company.
As we contribute to open source communities, the long-term trust we've built has become invaluable for the company's brand. We're now building value together and welcome all of you to participate. Closing with KubeCon events as we support and sponsor. There's Easter Day on Monday, the Maintainers Summit, and of course the Azure Kubernetes Day. We have over 30 talks, sessions, workshops at KubeCon, including keynotes on Wednesday and a theater demo on Thursday.
Microsoft folks will also be staffing booths at the CNCF Project Pavilion, including Headlamp, Ratify, Notary, Flatcar, Istio, Cilium, and Inspector Gadget. Come over for a chat.
Enjoy your time at the conferences, folks.
Thank you very much. Next up, we have Clay. Is Clay in the room? Hi. So Clay is going to talk about, what's he going to talk about, Clay? CRD data. So stage is yours.
Howdy, everyone. Let me get you some video here. Let's see. On screen. Let's try this. Yeah, perfect. Yeah. Thank you. We'll have some time for Q&A. It should work out well.
Actually, one slight challenge. Let me actually get it so I can see it too, because that will probably make it a lot easier for all of us. Oh, or not. Well. No, I can't get it back on my screen. Let's see here. I can't figure out how to make it just the same display.
To mirror it?
Yeah, just to mirror it.
Click on the range.
Thanks.
Yeah. No. So it's not here.
Yeah.
No. Done?
No.
What about this one? Yeah.
Perfect. Mirror for Black Magic. Thanks. Hey, cool. Well, the hardest part of a presentation, actually getting it so that everyone can see the presentation. Welcome, everyone. So I'm with Bloomberg. Want to talk to you today about custom resource definitions and kind of an interesting finding that my team's had with managing lots of Kubernetes platforms, which is actually the need for a data architecture kind of discussion with CRDs. And so with that, you know, we've got this challenge of managing Kubernetes clusters at scale. I think Joe's talk was a great entry into this when you have thousands of clusters, I think in Joe's case. How do you manage Kubernetes clusters at scale? And in particular, when you're doing your Kubernetes clusters with Kubernetes. So my organization at Bloomberg is a Kubernetes first software organization. We live CRDs, we live controllers. And in particular, we've started coming up with CRDs for our Kubernetes platforms, kind of what we actually host various projects and software platforms on, but then the tiers of those platforms. You could think of these maybe as organizations. If you are a hosting company, might be your customers would be platforms, and those tiers would be their deployment tiers. And then at the end, you have your various clusters. But ideally, we're all running Kubernetes to run an application. So at some point, you have to deploy a namespace and actually put things on your Kubernetes cluster. One of the interesting challenges, if you're managing Kubernetes with Kubernetes, is you'll have an API server to store all this data. Starts looking a little bit like a database, which is kind of an interesting challenge, perhaps. Similarly, of course, you'll want to use controllers to affect your broader world. Bloomberg, we're a very large organization, so we not only have our Kubernetes clusters, but all of the sources of truth in systems outside of our Kubernetes clusters that have to both reconcile in, or we have to reconcile out to. And then, of course, controllers to affect those platform clusters. So with that, let's kind of dig into the CRDs. One thing you'll notice here, if there's text in yellow, that is an upstream open source component or component from Kubernetes, one of the special interest groups like SIG multi-cluster, for example, from Kubernetes. If it's in pink, it's specific to Bloomberg and what we've built. And just trying to motivate a conversation here, because it sounds like a lot of folks in this room perhaps have had these problems, but I don't see it too often discussed externally. So with that, we've got these platform tiers, clusters. We want to actually kind of aggregate clusters into cluster sets, and we've got this interesting concept called a compute namespace. So Kubernetes has a namespace, but quite often you have a lot more metadata than just a namespace specification. So let's talk about what we mean by platforms. In particular, Kubernetes platforms that we have at Bloomberg, and we have some cool stuff in my mind. We have Apache Spark running data analytics, usually in a batch workflow system. We've got Apache Flink running on Kubernetes, which a nice streaming processing infrastructure. We've got Argo for workflows, either to schedule jobs on these platforms or on other systems, as well as Jupyter Notebooks, because it's always nice to have humans actually using computers, and so Jupyter gives a very nice window to do that. And often, AI, of course, has to happen somewhere, so model development and training for AI and Kserve for inference, which runs again on Kubernetes clusters. So when we talk about scale for us, that's about 9,000 software engineers, so definitely a couple folks that we have to make this pretty straightforward for and deploy their applications. So one of the questions comes up is, how do we decompose a platform, right? So we've got something like Kserve or Jupyter running on a Kubernetes platform, but how do we decompose that? And then how do we scale so that my team, which is responsible for all this metadata on how these platforms work, can actually scale out where we're not going crazy trying to figure out what's different between all of these platforms. So let's kind of just sit back and quickly take an SRE view or a DevOps view of the world and understand what a tier of one of these platforms might look like. Tiers are contained within a platform, and keep in mind each of these pink terms right now is a CRD. So we've got the platform CRD. We have a tier CRD. These tiers roll up to a platform CRD. For us, a tier is kind of the highest level to define a useful configuration. Usually a platform doesn't have a lot, right? It's really hard to abstract out and say, every Kubernetes cluster running Spark is going to have some axiom about it. But at a tier level, I can start to rationalize that there might be access policies, right? I probably don't want all my developers logging into a prod system, but dev might be a little okay. Similarly, resource usages. Each cluster is going to be different, or at least each tier is going to be different with what it supports. Again, let's think about AI. If you've got a bunch of GPUs, probably going to have to think about resource usage a little differently between prod and dev. Similarly, for network controls, again, kind of tautologically, those are going to be different. But then when we start to actually roll up these tiers, we've got cluster sets within them. And for us, that's kind of an availability zone sharding system, or it can be a sharding system for how applications might be deployed to one of these tiers. So basically, one or more clusters will roll up into a cluster set. This kind of brings us to the concept that my team really wants to make sure all of these platform teams are thinking about is their clusters are cattle, not pets. You know, this was a common term a decade ago, right? Think of your machines as cattle, not pets. You don't want to hand build a system. You want to have just infrastructure as code, and thankfully we've come to this world now where Kubernetes exists, but start thinking of your clusters much more as cattle and not pets. So we want to manage clusters in aggregate by tier, and this brings an interesting question. If we've got all these clusters rolling up into a tier, perhaps some of you have heard a concept called the namespace sameness principle, and we'll cover that later in this talk. But here, think about this as a cluster sameness principle. Clusters within a tier, the way our system's defined, have to be feature homogeneous. So that means that you don't have maybe a Spark and an Argo cluster in the same tier, because they would be in different platforms. You wouldn't have a cluster that maybe has GPUs in a tier and another cluster in that same tier that doesn't have GPUs, because you can't deploy an application homogeneously to any cluster within that tier. And to kind of give just a concrete example here, let's say we've got a platform like the Spark platform. Under that, we might have tiers such as runtime development, end user development, beta, and then maybe multiple tiers even, like at a certain level, like production here. So let's walk through Kubernetes namespaces. This is, after all, what my team is looking to deploy. We want to make sure that we've got containers ready to accept applications on each of these platforms. And so the platform teams deploy applications, again, that's out of scope for my team and this talk. But the namespaces, at least, will now be ready to accept those applications and have all the resource controls they need. So that compute namespace CRD we have is associated with a cluster set. Basically, that compute namespace has to actually know where it's being deployed. The cluster set is that deployment home. Compute namespaces define that Kubernetes namespace, and so quite often these are the axioms like service accounts, limit ranges, resource quotas, RBAC, that might be necessary to define for a namespace, as well as business logic. Again, you know, any company always has its special business logic, but all of that rolls up into the CRD. You know, again, namespaces are deployed at the cluster level, and here we've got a nice diagram just to kind of give you that visualization of how this rolls up. You can see here we've got two cluster sets, cluster set X, cluster set Y. Each one has a compute namespace that deploys into that cluster set, and then within that cluster set we have two clusters, X1, X2, and Y1, Y2, and then the actual Kubernetes namespaces that are created. So I want to step back. That's what my team does. That's how we've done it. What I'd love to motivate a conversation in the community about is SIG multi-cluster. So you can usually find me hanging out on the Kubernetes Slack in #SIG multi-cluster. And SIG multi-cluster really thinks about a lot of these issues. And the question is, how do we kind of roll it up to this level? Right now, we'll talk about namespace sameness here, but that SIG is the one that's really ratified what namespace sameness means. Similarly, there's a number of KEPs that have come out of this SIG, such as Multi-Cluster Services API. We'll dock in kind of how that relates to the work that we've done at Bloomberg, cluster inventory as well, which relates. But we won't actually talk about another KEP that the SIG's done, and I want to bring up why, cluster ID and the cluster property CRD, which is really cool work. It just, we didn't happen to adopt it. It's where you can actually figure out when you're running on a cluster what that cluster might be able to offer, or just various material about that cluster. Our systems always come from the outside of the cluster in, rather than running in the cluster and introspecting out. So with that, let's dig into kind of the cluster profile, KEP 4322 cluster inventory, and what it defines with SIG multi-cluster. So on the left-hand side here, we've got SIG multi-clusters definition. On the right-hand side, we've got a decomposition of what our cluster CRD kind of specifies. There are some similarities, however. Display name, what you actually call a cluster is kind of key, right? We're still humans and we need a handle on what we call something. The cluster manager, for us this is rather implicit. We have one cluster manager, so we don't have to define that. But SIG multi-cluster is trying to build a framework that we can all adopt. So the cluster manager and where that might live is a key part of the cluster inventory. Similarly, status, the Kubernetes version, you know, I think it was mentioned earlier today that CRDs came out, I think in version 1.16, but you know, if you are running a cluster, you need to know what Kubernetes version you have so you know what features it supports. Similarly, conditions on the cluster, your cluster health, whether it's actually joined to your cluster management system, and then this goes back to why cluster how our system works with deployment. Cluster access is a really key part, right? We all are used to working with tokens. We might have OAuth or other mechanisms on our API servers. But are we pulling data into the clusters with such as Work API and other SIG multi-cluster specification? Or are we pushing with, say, maybe federated identity? Or are we pushing with just a pure token? So all of this is defined in KEP 4322. Our cluster definition is a little more simple. We need status, and it's in some ways a little more descriptive too. We're able to say, hey, what is the status of this cluster? And we can actually set up the state there. So we've got inactive or active, right? Very, very coarse, but we could have cordoned, deprecated, or decommissioning. And this gives ideas for people deploying application to those clusters. What's the stability of that cluster? As well as a status message for humans, because otherwise it's hard to communicate. Similarly, cluster access for us is maybe there's certificate needs, maybe there's proxy needs. Server URL, regardless of where you're at, you usually need some way to find the API server. And for us, we still do have authentication configuration. It just doesn't quite fit the models from 4322, but we are still doing a pull model for our work. So with that, let's look at KEP 1645 multi-cluster services API. And this defines a cluster set in this SIG multi-cluster universe. And basically, one of the key things to think about is namespace sameness applies. And that basically means that any namespace deployed within a cluster set has to be the same on any cluster within that cluster set. One of the interesting implications of that from the cluster inventory KEP is that means that a cluster really shouldn't belong to multiple cluster sets, because now you have the risk that the namespaces might collide. So kind of a one-to-one mapping here. One of the key things we can look at here then is that ties very nicely into how our system's implemented with cluster sets. Here we could see Apache Spark platform has dev interactive, dev batch tiers, and within each tier we have two different cluster sets, an A cluster set and a B cluster set. One of the key things that's worth pointing out, again, with SIG multi-cluster is it tries to be very opinionated on what it can be and very open to implementations. So it doesn't have any implementations, it's just specifications. And here you'll see the specific mechanism is out of scope for this proposal as far as how tracking membership and defining membership for a cluster set is. So now let's dig into namespace sameness. I've referenced it a couple times. And the SIG multi-cluster definition is very nice. It's very short, concise. But permissions and heuristics are consistent across clusters for a given namespace. Namespaces don't have to exist in every cluster. So again, this is kind of a key part for our tiers. A namespace deploys into a cluster set within a tier, but may not deploy into other cluster sets in that tier. And they do have to behave the same, though, if they are deployed. And this is why we end up with that challenge that a cluster probably ought not be in multiple cluster sets. So for us, this works out very well. The compute namespace that has all of this bundle of data about a namespace is at the tier level, and this allows for consistent Kubernetes namespaces. And again, kind of a diagram to give us a nice visual way to look at that. So now let's dig into cluster names. And again, we all are humans. We like to have some way to handle things. So the multi-cluster services API defines a cluster name as something kind of obvious, a unique identifier for a cluster, scoped to the cluster's registry, how you're actually managing your clusters. Again, it's very nice and hands-off, says we don't really want to define the registry, that's up to you, but we just want to make sure we have this concept we all agree on called a cluster name. And again, it's used for definition in the cluster set. Again, also, it's really hard to change a cluster name, so clusters is cattle, not pet. Don't try to change the darn thing, just blow it away, recreate it, so it's an immutable state in that cluster. So now let's talk about the data and storage. We've got all of these different terms, we've got kind of an ontology of how this can go together, but this is where it starts to get interesting, right? We're talking about data concepts for our cluster management. So let's talk about where this all lives, and in SIG multi-cluster, that is the hub cluster. For us, we call that the Managed Compute API server. It is an actual Kubernetes API server. And then let's talk about, since this is kind of looking like a database, we can use etcd, it is the great data store. We could also use something called Kine, which comes from the K3S project. And now, well, we've just talked about databases, let's talk about referential integrity of our CRDs. Wait, what? So that's one of the things that I want to motivate here too, because I have not heard this come out at a Kubernetes conference before, but we kind of have to start thinking about it when you're layering CRDs one after the other, referencing another. So KEP 4322 cluster inventory basically needs to reside on a dedicated Kubernetes cluster, aka that hub cluster. And so let's look at what our hub cluster, the managed compute cluster, looks like. Here we can see that we've got some cluster-wide CRDs, the platforms and tiers, and then we can see an actual namespace for one of those tiers in the kind of beige box here. So we can see two platforms defined, the CRDs for platform 1 and platform 2, very descriptive, and then tiers for dev and beta. Now, each dev and beta have to point to platform 1 because they are tiers in that platform, and now we can actually look at the beta tiers namespace. And so here again, we have cluster sameness and we have namespace sameness that have to apply, so that actually lives in a namespace on our managed compute API server. This server has no nodes, it's just storing data for us. It allows us to operate with Kubernetes controllers, it allows us to treat this like any other Kubernetes cluster because it just doesn't do workloads. So here we see cluster A and cluster B are defined, they're all in cluster set X, and then we've got 3 compute namespaces. So now let's talk about the high availability aspect, because you really don't want to lose your control plane usually. And so we use something called kind from K3S. It translates the etcd API. So it actually will allow us to now, instead of using etcd, use SQLite. Well, that doesn't really give us high availability, but it's kind of cool for local development. But Postgres. Bloomberg, we've got an amazing Postgres team. They say, hey, yeah, you want Postgres? We can make that highly available and replicate wherever you need. So we use that. It supports a number of other databases as well. Nats is a very cool thing. I actually hadn't realized until I was reading the README for Kind. But with that, there's some key features of Kind. It can be run standalone. It's very lightweight. Basically, it works for any Kubernetes API server. It doesn't have to be specific to the K3S project. A key part that they want to make sure that everyone's very well aware of, if you have etcd doing some cool, crazy thing for you, they are not a generic etcd drop-in replacement. They only translate some of the calls, but the ones that Kubernetes API servers need, such as create, update, and delete, the transaction calls. And we use that so that way now we have multiple API servers that all can point back to our data, ironically living in Postgres, and we can manage our clusters that way. So let's talk about that referential integrity. We've set up that we've got platforms, tiers, clusters, cluster sets, and compute namespaces, but they all reference one another. And so we now need to make sure that, for example, you don't deploy a tier to a platform that doesn't exist. We need to make sure that we've got a compute namespace that actually is defined in a cluster set. And we need to make sure that all works out well. So some challenges with that are enforcements and updating. So we use cell expressions to make sure things are well formed, but that doesn't give us referential integrity. Webhooks do, though. So now we can actually have a webhook that says, hey, let me make sure that platform exists that you've specified. Let me make sure that tier exists. Let me make sure you don't delete a platform that still has data. And now we can also have controllers. So you'll notice here our compute namespace, as I mentioned, has some business logic, such as on-call groups or owning user IDs. And those live in other sources of truth, right? My phone number doesn't live in a Kubernetes cluster. Well, it might, but that's not a metadata in a CRD field. So that has to go and reconcile out if I change my phone number. Similarly, who owns that, right? People like to change teams, so we have to actually push that in to the CRD and make sure it's bidirectionally replicating. So we have controllers to implement all of that. So let's talk about resource creation now. It's great you've got all these CRDs, but if they just live on a Kubernetes cluster, it really doesn't buy you much. So this is where I think it'd be great to have a discussion of how do people do this. For us, we have a pretty simple API layer. It is a Kubernetes client that reads our management cluster on the right-hand side. Again, kind of that straightforward process with the compute namespace. But now we have a replicator that, again, is kind of a controller. It is able to talk to that API, which basically takes a compute namespace and renders me a Kubernetes namespace YAML. And now I can just create that on the cluster. Each cluster knows this well-known API and API translation service, and it's able to talk to its local API server to create necessary resources. Similarly, this gets kind of more interesting because we have sources of truth for permissions that out of scope here, but they can generate OPA bundles. And so now I've just got OPA bundles running around on kind of something like an S3 bucket or what have you, and that translation service can pull those bundles down now. and start to parse those bundles so I can query it and say, hey, what cluster role bindings should I have in this cluster? What cluster roles, et cetera? And that replicator service, as long as I'm generating those YAML specs, can inject that into my cluster. So with that, I think I'm out of time, or nearly out of time. And so, yeah, with any questions, I just want to make sure that everyone here kind of hears a call to action. I think there's lots of folks in this room probably creating similar systems. Let's have conversations on them with that, I think.
Hi, thank you for your presentation. Sure. I have a general question, since I've been actually diving into multi-clusters myself. And the one thing that I did notice when going through multiple solutions is that each and every single provider, company creates their own multi-cluster. Why did you decide to build your own rather than use one of the currently available? I believe there's like a pretty handful of choices available, both supporting pull and push models, and with roughly functionality matching what you just described. Yeah,
so we do use Karmata, for example, today. We have looked at a couple other solutions. Ours is also relatively old. It actually predates me joining this team, which is about 3 years now. So we're kind of trying to figure out, to your point, Karmata is a great example. I'm drawing a blank on some of the others right now, but they do follow a lot of the specifications here from SIG multi-cluster, and that's one of the reasons I wanted to highlight. I ran this by a SIG multi-cluster call to say, talking about a lot of your work that I've not been involved in, but I want to make sure people know about, and they said, thank you, yes. We find people don't always know that these definitions even exist. And so being able to make sure that folks are aware. Things like Karmata, though, and a number of the other projects do actually implement these features. For us, the biggest challenge is things like translation with the OPA bundles, stuff like that, where we haven't yet been able to find a good way to upstream them or a good home for those features. So.
Hi, thanks for the talk and the inspiration with the SIG multi-cluster group, actually. You kind of lost me, though, once. The data model. Yeah. And the connection between the cluster set and the cluster inventory, cluster profiles and cluster inventories. Could you explain that again, please?
Yeah, so cluster profile really defines metadata about a cluster. So this can be, for example, right now there's a discussion in the community on access for, how you define access to a cluster. So this is very similar to our internal cluster CRD. Basically saying, what's the name, where, how do I access this thing, and all of the properties about a cluster. So, cool.
We have time for a few more questions. Thank you.
So you mentioned that you're using Kind and Postgre, because you have an amazing Postgre platform, but does that run on the same Kubernetes? So like, do you manage those clusters that run Postgre and Kubernetes, and then you use it for the entire persistence layer? Because that can make...
No, that's a great question. So admittedly, management of Postgres is out of scope from this talk for sure, but they are not, there's no stack dependence in this case. It is worth pointing out too that like our management clusters are actually really lightweight. But they do run in a Kubernetes cluster. So yeah, it is actually kind of funny that shortly they will be self-managing and we'll have a Bootstrap inception challenge to overcome. So.
Last one.
Cool, thanks for a great talk. So you said you're running a full-blown Kubernetes cluster. Is there anything you need from that, like in terms of workloads, or have you been looking at KCP as well, which is doing similar things?
Yeah, so actually in this case, it's not a full-blown Kubernetes cluster. It is just the API server, largely. No nodes, no actual workloads running on it. So like all the controllers that reconcile against that are, again, running in the Kubernetes cluster that's hosting the API server that is our management cluster. KCP, pardon my ignorance off the top of my head, I don't have any pros or cons for it right now. We're able to do this with a pretty lightweight Helm chart, admittedly. So.
Thank you. With that, we're on time. Thank you, Clay. So now we're going to have a coffee break until 11:10, and then we have 2 more sessions before lunch, so enjoy the coffee. All right. Hello, everyone. I hope you had your coffee and you're ready to continue. Next one, we have Tom from Mirantis. He's going to talk about QoS. Take it away.
Yeah, thanks. Thanks for coming. So let's dig into Kubernetes and cgroup. So my name is Tom. I'm working for Mirantis. I'm working for Mirantis. I'm an engineer there, and I'm working on K0s. And K0s has recently been accepted to be a CNCF sandbox project. So we're currently in the onboarding phase of that. And yeah, then we're pretty excited. So let's see what that means for us as a project. So yeah. So this talk is about noisy neighbors. So why do we have the noisy neighbor problem in the first place? So where are the mics? Yes. Thank you. Check, check. All right. So the reason is bin packing, right? So we have the computers, and the computers are costing money even if they don't do anything. So not doing anything on computers means we're losing money. So we try to bin pack everything. And for that, we're using Kubernetes. So Kubernetes makes bin packing super easy. But in the end, computers are still physical devices. So there are some strings attached. For example, scaling out is not it is a process which takes time, and the resources aren't infinite. And sometimes it can happen that all out of a sudden your neighborhood is in flames because of that. And yeah, that is not a good situation, and we can do better about that. So let's see how we do that. So for once, we need to tell the system about our preferences that we have about our services. So if we do that, the system can actually help us in maintaining those. And that is very crucial here. So how do you do that? We will first look at the Linux containers in general, and then how they interact with cgroups. And then we will look at Kubernetes and how Kubernetes interacts with cgroups. And in the end, there is also the init systems involved. We will see about that later. And with all that knowledge, we can go to the kubelet and tell the kubelet about it. Right, so for once, containers and cgroup. Reminder, Linux containers are not a thing in the kernel. They are basically emerging from lower level concepts like namespaces and file systems and cgroups. And there's software which we could call nowadays container runtimes, which basically pack everything up and make a container out of that. And we will be looking at how that works with control groups. So control groups are a means of regulating process groups across resources. So you need to have the resources assigned to cgroups, and then the cgroups, and then the Linux kernel can interact with that. And cgroups are basically a hierarchical concept, and each cgroup has a set of resource controllers attached to this, which actually controls a certain resource type. So when talking about cgroups in a hierarchy, I mean basically you can imagine that like they are a file system. So you have a root cgroup, and each cgroup has its child cgroups, just like directories and files. So that hierarchical concept has some implications. For example, that parents define resources for their children, and the children cannot escape those resource requirements. And you have a proportional balancing across siblings, and that makes cgroups a good concept for delegating resource access to lower level processes. So cgroup controllers are basically controlling certain resource types. So the most important ones are the CPU and memory controllers. So the CPU controller basically controls how CPU cycles are spent across all the processes of a system. And the memory controller basically controls how memory can be allocated and is allocated to certain C groups. An example for those C group settings is, for example, C group weight, C group maps, and memory max. So C group settings are usually named in a dotted annotation. So the first part is being the controller, and following some information about that. So for once, the C group weight is a proportional setting. So it ranges from 1 to 10,000, the default being 100. So it's basically a really proportional thing. So if you have 3 C groups, 3 sibling C groups in a under the root C group, which all are weighted at a C group CPU weight of 100, they will get all 1/3 of a CPU. So this means that the value 100 can be scaled down by 100 to reach the minimum CPU weight, and can be scaled up by multiplying 100 to reach the maximum. So this is a good fit in the middle to basically adjust into both directions. The CPU max value is in this time ratio, so you can basically spend so many CPU time per a certain time slice, which means that in this example you can spend 50 milliseconds out of a 100 millisecond time slice. And this is actually a hard cap, where CPU weight is actually only relevant if you're under contention, which is an important distinction, which we will see later on. And then there is the memory max setting, which is basically just the amount of memory that a certain C group might consume completely maximal. So we will see how that fits to Kubernetes later on. Then a certain historic note that C groups v2 is now the thing. There has been C groups v1 before, but that is phasing out by 2025. This is still, or this is nearly phased out. So this talk is mainly about C groups v2, but it's still important to know, if you read that, there is still a lot of quick glitches and compatibility layers and software around. So it's good to know, if you read that, you might be focusing on v2 only. So how does Kubernetes relate to C groups? We now have a rather understanding what C groups are in the Linux kernel. And Kubernetes does it in the following ways. So it defines quality of service classes. Those quality of service classes is nothing that we can assign. We just pick the resource requests and limits. And by doing that, Kubernetes will automatically figure out which QoS class it will assign to our workloads. So the 3 of them are best effort, burstable, and guaranteed. The best effort one is basically the one who will be in problems at first. So if we are in a resource contention, the best effort pods will be in trouble first. And while the guaranteed ones are the ones who will be sustaining the most trouble, but they are also like throttled by design. So even if there is spare resources to spend on the computer, guaranteed pods won't be allowed to use those. So this is basically already a trade-off. When we are mapping the resource requests to the limits, this is how this goes. So as you might have thought already, we have like the 3 settings that I shortly introduced before, which is the CPU.max setting, which is responsible for the CPU limits, which is a straightforward like translation. So if you have like half of a CPU, you will get 500 milliseconds out of a 100 milliseconds time slice. If you have 3 CPUs, you will get 300 milliseconds of a 100 millisecond time slice. This is a hard limit, so you cannot exceed that. If you need more time, your process will get stalled until the time replenishes, even if there is still time available, compute time available on your system. Whereas the CPU requests are using the proportional CPU.weight setting. So there is a fixed formula inside Kubernetes, which basically translates the CPU requests on your workloads to a certain value of the CPU wait. So this is important to know. CPU requests are not only used for Kubernetes scheduling, they're actually used in the Linux kernel. So the Linux kernel is being told via the cgroups about your preference of the CPU requests. The major difference is here, they just don't care as long as your computer has still slack CPU time available. They only kick in under contention. For memory, the story is a bit different. So there is the mem.max setting. The mem.max setting behaves a bit differently because it's enforced differently. So if you're exceeding the CPU time in the CPU.max area, you're throttled. That won't happen for the mem.max setting. The mem.max setting, you can basically exceed your max memory requests, but then you will be killed by the kernel. So there's no way to like test it out and like just not get the memory. You will just get the memory fine, but then probably the kernel comes along and gives you a shot. For the memory requests, the story is a bit different. There is no direct relation to cgroup here. There is a cap about this. You might want to look at that for more details. But in the end, there is still the OOM score adjustments, which will be done by Kubernetes. But they're not a cgroup setting per se. They're a general process setting, and they are also working without cgroups. Anyhow, they still have influence on how the kernel will select which process to kill when there is memory contention, which is also important, because if you overcommit your memory requests, then the higher likely you will be selected for OOM kills than otherwise. All right, so that's how requests and limits are mapped to individual cgroup settings. And now we will have a look at the structure, how the hierarchy, the cgroup hierarchy in a Kubernetes node looks like. So the kubelet will maintain a root cgroup, which is called kube pods. And then you get sub cgroups for each QoS class. And then in that QoS class, you will find the pods. And below the pods, you will find the containers. And the resource assignments will happen from bottom to top. So all of your resource requests and limits will be translated to cgroup settings, which will then be applied on the individual cgroups on the containers. And then Kubernetes will sum that up, will do the sum, and put that on the parent, and will then do the sum again amongst all the parent siblings, and then we'll put that on the QoS class level, and then something will up, and all these sums will end up in the kube pods root cgroup. Also noteworthy is that guaranteed pods don't have a container cgroup. They are directly competing at the top level with all the other pods. So as I said, the proportional balancing is happening on a sibling level. So the guaranteed pods are directly competing with all the burstable pods and all the best effort pods, which gives them even more precedence in the scheduling decisions. So now that we know what Linux cgroups are and we know how Kubernetes uses cgroups, we also need to have a look at the init systems. The question is, why do we have to do that? Well, the init systems are the software which is basically started by Linux after the computer is booted. So this is the first thing which the Linux kernel does, and the init system is responsible for all the rest. So this also means that the init system then itself will bootstrap our Kubernetes node components. And most likely it will interact with cgroup 2. And that of course means we have to look at that so that the resource constraints that are done by the kubelet match those that are done by the init system, because everything is proportional, and if those proportions won't fit, it doesn't work. So here's a short overview of all the init systems out there, right? So there's some historical ones and some niche ones and also some simple ones, like OpenRC is kind of simple and still popular, for example, for usage in Alpine and Gentoo. And then there is the dominant ones, right? And the dominant ones are on the right side. But the dominant ones might not be so simple. And in this case, it's systemd, which is not simple at all. The thing about systemd in this case is that it's very dominant in all the popular distributions, like almost every distribution uses it. And this means that we have to look at how systemd deals with cgroups. And yeah, it has certain idiosyncrasies that you need to be aware of, and that's also important if you have software that wants to integrate with cgroups and is running on a systemd system. And Kubernetes is no exception there. So systemd basically wants to own the whole cgroup hierarchy on your system. So usually you can go ahead and fiddle with cgroups on your own, if you have root rights, for example. In theory, you can do that on a systemd system as well, but systemd doesn't like it. So it has a certain idea about how cgroups should be structured, and it wants to own all of the settings of them. So you need to integrate with systemd itself. So you cannot just do the Linux way of interacting with cgroups. You basically need to use the systemd API to manipulate cgroups. And that means you need to integrate with systemd. An example cgroup hierarchy on a Kubernetes node on a systemd system looks as follows. So you have a system cgroup and a user cgroup. The system cgroup basically contains all the services and sub-cgroups that systemd is running. So like your SSH daemon and your Kubernetes API server, I don't know what, all those funky parts. And then you have the user cgroup, which contains all user logins. And in this picture also you see the kubepods cgroup that we've looked at before, and you also see the naming scheme that systemd wants us to use. So in this case, the kubepods cgroup directly competes with the system and the user cgroup at the top level. A quick comparison to OpenRC, which doesn't have that many opinions about cgroups. It just basically uses all the services in the root cgroup. It just puts every service into its own sibling cgroup under the root. And kubepods will then, on the same level, compete as a sibling with all the other system services on the same cgroup level for the resources, which is a bit different take, and you should be knowing that if you're using OpenRC or systemd. If we now know how init systems deal with that, how Kubernetes uses cgroups, we also need to have a look at how kubelet does it. So the kubelet basically has this view of the world of a Kubernetes node. So it basically has the system reserved group of resources, it has the kube reserved group of resources, and it has the pods group of resources. The system reserved stuff is basically all the OS system daemons that we've seen before. It's basically very well correlating to the system cgroup in systemd, whereas it also defines the kube reserved cgroup, or the kube reserved pool, let's say, which basically contains all the services that scale with the number of pods on the system. So there's the difference. The system reserved stuff is not dependent on the number of pods on the node, and the kube reserved is the resource pool for the components which actually scale with or which actually need more resources the more pods are scheduled on the node. So this usually affects kubelet and the container runtime, but there might be more depending on that. And then it takes the resource requirements of those two reserved pools and deduces that from the complete capacity of the node. And this is actually the allocatable resources on the node itself. So if you have a 4 CPU node or a 32 CPU node, then you can, for example, save 2 CPUs for the reserved pools, and this means that you can still assign 30 CPUs for the Kubernetes workloads. And how do we do that in the kubelet configuration? First of all, we need to tell kubelet that we're actually using systemd, so it uses the systemd driver and knows about all the idiosyncrasies that systemd has, which means that it will use systemd APIs to configure the cgroup settings, and which makes it very well integrated into the system and will make systemd happy. And now the important part is that we can, for each of those resource pools, we can define a cgroup, and that cgroup will receive certain settings for the resources. So just in the same way as we define the resources for our workloads, we can set the resources for those two system and kube cgroups. And the advantage of this is that the kubelet actually will use the same mechanics to calculate all the cgroup settings and put that on those cgroups. So the proportional weights are in sync. So this is very important because CPU weights, for example, are proportional, and usually all the cgroups have a standard CPU weight of 100, which is very different from the CPU weight that the kubelet will calculate. And if you do that into proportional calculations, it just won't work out, and like the real CPU requirements aren't met because Linux calculates something different than the kubelet wants it to have. And if you use that technique, you will use the same calculations, or the kubelet is doing the same things to these C groups as it would be doing to the workload C groups, right? And yeah, what does that mean for us? When configuring a node, we basically need to know all about this and take that into consideration. So C group layouts have practical implications, and the weights are proportional, and if they don't fit to each other, then our resource requirements aren't met, and that is a bummer. And it also means that we need to, as I said before, we need to tell the system about our resource requirements, and there is no right or wrong, right? So we need to figure out ourselves what is best for our workloads. And this is a constant process, so you have to have a feedback loop, try to find out what's best for you. And one last thing I wanted to say, have you ever been warned by some static analysis tools about missing resource limits? I have, but my point here is we shouldn't be carrying that much as long as we have our CPU requests in place and consider the CPU weights accordingly, because they actually kick in. So the CPU requests are actually part of the kernel via the CPU weight system, and they will kick in when you're under contention, but they will only kick in under contention, which is a fine thing to have, because as long as there is still CPU cycles to spend, everything is fine. Your workloads can just burst. But in the situation when you actually are under contention, then you actually will get your CPU requests like the limits. All right, that's all I have. Thank you.
All right, we have time for a few questions.
Oh, thanks for the session. I wanted to ask about the time slice. It is defined on 100 millisecond. It is adjustable or not?
If the time slice is adjustable, on the C group level, yes, but Kubernetes hard codes this at the moment.
Thank you.
First of all, thank you for this very informative talk, and it kind of takes quite some courage actually to stand there, so really appreciate it. My question is actually about the following. We have in the later Kubernetes version, I believe starting 130 and that kind of stuff, next to cgroup CPU and cgroup mem, we also have something like cgroup in this case with the paging space and that kind of stuff. How does that actually relate to the two? So in this case, also, for example, to the quality of service groups and that kind of stuff. So if we take paging space into account.
Which space?
The paging space, so the swap counting and that kind of stuff. That's actually in the later Kubernetes
paging. Yeah, yes. That is a good question. I mean, swapping and Kubernetes and kubelet would be a whole nother talk, I think. I'm actually not sure about that. I think there are some settings in the memory controller which affect swappiness, and then there is also like general swappiness settings in the kernel. And yeah, I think that is a very complicated question actually, and it might very much depend on what you actually need from your workloads and your nodes actually. So I don't have a good answer on this.
No worries, let's talk about it after the talk.
Yeah.
Anyone else? No? If that's the end. Thank you very much, Tom, once again. And
thanks.
We're going to have a short break, and then we have Eric to talk about Fluent Bit. All right. Hello again, everyone. Next up, we have Eric, and he's going to talk about mastering Fluent Bit. This time I got it right.
Good job. Good job. Good job.
Stage is yours.
Okay, welcome everybody. Really quick question to get an idea what kind of audience I got. Developers in the room? Hands up. Not very many. SREs? 1, 2, 3, 4, 5. Yeah, quite a few. Ooh, it's about 50-50. Architects? If you're a developer, you're an architect by default, right? Managers? Lost? I always wonder what they do in things like this. Anybody here using Fluent Bit? Professionally or as a hobby? Fluent D? Know of it? OTEL? Using or know of it? There's a difference. There's a big difference. All right. So what you're going to see today, what we're going to talk about today, is all backed by a workshop. There's no need to take pictures of the slides. They're online right now. If you go to chabelle.org, you can get them yourself. There will be QR codes scattered through towards the end for jumping straight to the workshop if you want to go bookmark that. All the stuff you see today that we hopefully get to hands-on live, you know, demoing and stuff is going to be stuff you build and you can do online at your own self-paced tempo. So everything you see today, you should be able to repeat at home. First thing we're going to look at here is what's the difference. So understanding what Fluent Bit and OTEL or collectors are doing is out there at the front end collecting your telemetry data, right? And a lot of the conversations you might see, or when you start having discussions internally about this, might be we have to pick one or the other. I'm here to tell you that that's not really the case. You will often in a true enterprise see a mixture of these things or use cases that can easily apply to one or the other in favor of the telemetry type that you're collecting. They all have strengths and weaknesses. I'm not going to go into every single one of them, but they also work together seamlessly, so there's absolutely nothing holding you back from using either one, right? And you should see that today. Just want to make that really clear. If we look at Fluent Bit, this is a derivative, basically over time from Fluent D. Fluent D was developed in a time when we were doing VMs and APM, and observability really wasn't a word. It was monitoring, monolithic kind of stuff. Not very performant if you take this stuff straight into the cloud and into the container environments, right? Did not perform well. Too much resource, too intensive, too big. So Fluent Bit was developed as a sub-project of Fluent D. So it automatically inherited the graduated status. Was adopted really quickly in the organizations. It's very lightweight, very performant, scales massively and easily across an organization, especially on the edge, especially in container environments. Limited resources, right? Am I walking too far? I'm here for the fans, not for the recording. Sorry out there in the recording. So this thing scales and it's really good at high throughput, high, you know, really performant. So keep that in mind. It's really flexible as far as that goes. Traces first, written and go. OTEL we've seen, and you see no matter where you go, a ton of talks about this, right? This talk focuses on the collector only, and also on the open telemetry protocol. One of the biggest strengths here is they spend a lot of time trying to standardize the communication protocol. Doesn't do us any good if we're all doing our own version of YAML, right? So having the OTLP, the open telemetry transmission protocol is super important, right? The best part is they both can speak to each other fluently. See how I did that, fluently? Fluent Bit has a forwarding protocol. It's called the Fluent Bit forward output plugin. OTEL can take that directly, and since about 6 months now, they have the ability to put everything that comes out of Fluent Bit into an OTEL envelope. So you can ingest it natively as OTLP. So basically you can go back and forth. It really doesn't matter at all, right? This is really handy when you come into an organization, you see that they have one or the other. There's no need to replace one or the other. There's no need to get in the way of one another. You might have some kind of legacy monolithic stuff somewhere. You can put it into Fluent Bit, which is known for anything in, anything out. So the input plugins, there's massive amounts of these things. You can collect almost anything, and you can output almost anywhere to any backend, right? Super important to understand that. Some of the use cases, we've mentioned it a little bit here. So collecting at the edge, resource constrained. You want to have something really lightweight, really easy to use. And you're going to see here, I'm going to walk you through exactly the 5 phases involved with using Fluent Bit. It's very easy to digest both in your mind and to physically use. You're going to kick yourself that you did not think to write this yourself. That's basically what the feeling is when you start using it for the first time. The OTEL collector is a centralized aggregation point. Does a lot of advanced processing inside there also. So you're hearing basically the same thing for both of these. It's just a different focus, a different collective way of doing stuff. And a lot of people are buying into the open telemetry ecosystem inside of organizations, so then you'll run into this there. But they can run together, huh? You can do them either one, it doesn't really matter. You're gonna see that shortly. So, telemetry pipeline, what's this thing look like? That's it. 5 steps, super easy. Man, I should have wrote this. I wouldn't be here standing here talking to you guys if I did. Eduardo is the head of the Fluent Bit. He's one of the original developers of this thing. It's beautiful. So the idea behind this initially was logs, right? We came out of Fluent D with logs. Fluent D's idea was, okay, anybody here ever been a Java developer? So I don't know about you, but back in the day when I was a Java developer at a financial institution, we used to spend time at the coffee machines because back then the machines were slow enough that it took a while to compile your Java. And we'd be talking about what are we going to put in our exceptions? What English language thing were we going to say so that when you get a dump of this big stack trace that the guy sitting there or the lady sitting there at the op side of the house would be able to understand what the hell was going on. We broke our heads all the time about this stuff, and it made no friggin' difference because the third floor would call and make me go down there and look at the stack trace and explain to them what was going on anyway, right? Everybody's gone through that. The idea here with Fluent D and Fluent Bit, it's parsing is the first thing that happens. Turns it into machine-readable language, turns it into YAML, turns it into JSON, turns it into key value pairs so that you can then use all kinds of tools to parse this stuff, right? First thing that happens. Second thing is filtering. Now, what do you want to do if you have sensitive data? You want to remove it. What if you have data you don't even care about? Remove it. Maybe you want to aggregate things. Maybe you want to enrich the data. You do all that in the filter phase. Then you have a buffering phase. Buffering is, by default, in memory. Everything that's read through this is broken up into chunks and is just run through a memory buffer. Problem is, what happens when you run out of memory? You start losing data, right? So you have the ability to turn on file system memory and stuff like that to buffer into the file system and make a big queue and then process it at your own time. There's also a lab inside, 2 labs actually, inside the workshop that'll take you through exactly that on your own machine, and you can see how it breaks and how you can fix it and some of the things you can tweak. And then you have routing. So based on these key value pairs, you can make decisions of where you want your information to go. Some of it might go to an Elastic backend. Some of it might go to a Prometheus backend. Some of it might go to some kind of proprietary backend. Some of it might go to storage in the cloud. It doesn't matter. You can make choices and filter based on the routing there. And then it goes to an output plugin. These output plugins is a whole list of stuff you can find online in the documentation that covers these backends. Pretty straightforward. I forgot to click while I was telling you about this. So basically, you just walk through all this stuff, and boom, you're to the output. Now, it's all fun and games, so let's look at it, right? So, this work? Hello, hello, hello. There we go. All right, so the idea here, if you guys can hear me, is that we're going to go look at this under the hood. Hello. There we go. Better? All right. So, what you're looking at here is, and we're going to need both of these. So I'm going to come over here. Ooh. Hello. I'm going to switch back and forth and make your life hard. So if you look at the top there, you see a service section, you see a pipeline, and you see outputs. Within the pipeline is where everything's happening. I've commented out a bunch of stuff, but what we have an input that's generating a fake log line. I have other demos where you generate them out of Kubernetes and all that kind of stuff, but that's too much confusion right now. It's not about what's coming through the log message. It's about getting something standard that we can digest. We see you have a service and a back end. We have a user ID with some kind of secret ID inside there. Imagine your social security number or something like that. And you have a log entry. And in the output, very straightforward, it's going to standard out to the console. It's going to put everything in the console. And the first thing we're going to see here is that it just dumps it out as the log line. I'm always too tall for these things. So here we're starting out Fluent Bit, and number 2, you're going to see a premiere here right now. You notice the t-shirt I'm wearing right now says version 3, right? version 3. What you're about to see is going to be actually announced next Monday. So you're looking at a candidate release of version 4. So this is a premiere. You're the first people on the planet to see this. They love their ASCII code, right? There you see the log lines coming out. Nothing special, nothing exciting, right? It's just generating and processing them as it goes. And you see here that it's checking it every second. So that's why you see about every second we're getting a new log line, right? Now, you notice here at the bottom, right here, and what we're going to do is we're going to just give it a kick, and I'm not going to restart it every time. Right here. Which one? 4, 4, 2, 4, 6. You see you got a kickstart in place, and now look what it's doing. It's turning it into JSON. See the difference? This is your parsed output. Remember the parse phase? All right, next thing we're going to do is go over here, and we don't like to have secret information in there, right? So let's uncomment this, and what we're saying right here is let's modify our log lines that are coming in. We're looking for every single one of them for the keyword user ID, and we're going to remove it, right? Save this. Go back over here and give it a kick. No more user ID. Right? Wait a second. I think I might have, yeah, hold on. Sorry guys, I see shocked faces and I'm like, wait a minute. All right, let's go back here and reset that. Just seeing if you're awake. All right. Now we got to check the, where are we at here? We got to check the ID. It's a different ID. Back here. Which one we got? 4351. Whoop. Now we're talking. Now you believe me? Didn't believe me, did you? You're just full of crap. But you still see we got the secret user ID in there. That's not good. So let's go back there and start modifying what we're doing. And I mean, let's be honest. This is so easy, right? Oh, wait a minute here. I promised you we would do that first. JSON. Whoops, this way. Here, sig up. A lot of moving parts. There we go. Does that look better? Now we got JSON. See, now you're nodding your heads. Now you believe me. All right. Up here, let's remove the ID. Comes with sounds. Oops, too far. Let's go here, kick it again. There we go. No more secret IDs are being processed through the back end. Now think about this. Where's this running? This is running out very close to the end. It's out collecting from your application. It's before you're going through your back end, through your cloud, and all this other stuff. So you're out on the edge, already cutting data out of the pipeline that costs a lot of money. Right? You could send this all to your back end and then edit it, but that costs you money in the cloud. Think about that. Yeah? All right, what's the other one here? Now we're going to do something a little bit more interesting. Let's start adding something. We're going to enrich our data. So the problem here was, or problem is a big word, but we see that we have a back end. Can you read this? Is it big enough? Good. Just a generic back end, right? Now let's make it something a little bit more interesting. Because back end really doesn't tell us anything when we're an SRE carrying a beeper. Ask the SRE sitting next to you. He doesn't like that, or she doesn't like that. Now we see that our back end is from Rejekts, and we're very happy with this code, right? It's very simple, easy to understand, right? Everybody got that? Also, one thing I should mention, see the top says hot reload on. That needs to be turned on, otherwise we can't do sig hubs and kick it like that. All right? Otherwise it'll ignore you when you do that. So it's something you can turn off so people can't do that. All right. Now we go, let me stop it before it overloads my machine. If we let it run long enough, it will fill up my memory. Here we go. All right, what's next? That's all fun and games. That's the basics of, you know, what a parser does, what a filter does, what the outputs look like, and that kind of stuff. We sent everything to standard A, and we didn't send it all over the place. This case here, now you're looking at the architecture. We have a host of applications, whatever it is. We have our pipelines collecting. What we're going to do is we're going to create metrics out of this. We're going to make a metrics endpoint. Anybody here work with Prometheus? For those that don't know, Prometheus is famous for going out and getting its metrics data. So what you do is you create an endpoint where you post your metrics data, and it goes out there and it scrapes it. So you see here that it's going to push to the edge of the host. It's just going to locally put an endpoint out there, and I got to configure a backend, Prometheus, and turn it on and tell it to go get it, right? So what's that look like? So we will be doing this one. And if we take a close look here, I'm going to turn it on. You're going to see that it's going to be generating just a log line. Go over here. Run that. So it's just doing a very simple message. I think we already have the JSON on, yes. So I'm a big fan of just keeping it in JSON anyway. That's pretty much how you're going to process it. Very simple message. We got success lines going, right? So the next thing we want to do now is we want to turn on an endpoint where we're going to host our metrics. So this is going to be a local host, and it's going to be generating these metrics at the Fluent Bit side. And then we got to go back over here, figure out what the ID is so we can kick the right process. 619 it looks like. If you watch what happens here, this is set to do it every 5 seconds. There it's collecting the metrics and putting them on the endpoint on the Fluent Bit side of the house, over by your application where we saw that little endpoint, right? There's nothing collecting it, nothing scraping it. It's just now every 5 seconds, boom, kicks another bunch of metrics out, right? So what we want to do now is we want to go over here and sorry. Turn on the actual stuff so that it can be scraped. And then we're going to add a couple of labels to it. So when we go to our Prometheus, we're going to be able to see this. So let's kick this. So right now, you're not going to see anything different on this end. You're going to still see it every 5 seconds kick out the metrics. You don't see those labels and stuff. Those are inside of one of these metrics. There are labels being added. And then we will go over here. And this is the configuration that I've set up for Prometheus for those that know it. Basically, all we're doing is saying Fluent Bit's out there. That's the name of the target. And you're going to find it on localhost 9999, right? So I have a Prometheus binary here. Config file. I think it's YAML. And now it's collecting, and we should be able to prove this by someplace I got over here. Gonna have to come out of this quick and on the local host. And you can prove that the metrics are actually hitting the scene here. Oops. So this is Prometheus. It's a little small, I think, isn't it? There you go. Now you see that it's command line completing inside this to find the metrics that are available that it's scraping. You can also go see in the status my targets. You see he's really happy that I'm collecting stuff on localhost 9090. And those are the same metrics you just saw on the Fluent Bit side that are now being pulled over here and collected and stored inside of my Prometheus backend. And if you want to see the extra labels we added, I think it's uptime. whoops. It's really hard to type. I'm tall, and this is very low uptime. If you see there, you're basically seeing the metric being collected with the labels that have been added. So the rejects in London, and what's the other one that we added in there? Fluent Bit there, I guess. The app name is on the front end. So now you're seeing the ability to collect your data, your telemetry data on the front end, turn it into metrics and show this stuff, right? That takes us back to, let me turn this all off. See? Turn that off. And I'm told I have 5 minutes. So here we go. So now we're going to have one where we're going to do, where did my Google go? There we go. Here, slideshow. All right. Now we're going to do one where we do the same thing kind of collecting. You saw the console output. I'm not going to run that because we're running out of time, so I'll just skip it, and you can assume that I'll show you that it's running, and then we'll start modifying stuff in it. And then we're going to put it into an OTEL envelope, and I'm going to show you at the front end. So you have Fluent Bit collecting it, you have Fluent Bit output, you're going to see that it's in an OTEL envelope. It's going to go from JSON to an OTEL envelope format. And then we're going to turn on an OTEL collector. And we're going to have that collect that. We're going to turn on pushing it to it. It's not pulling, you have to push to an OTEL collector. So I have to tell Fluent Bit where to send this stuff. It uses an OTEL output plugin to push it to OTEL collector. On the backside of OTEL, you're going to see it come out of the console, because we're just going to use debugging on the console side of OTEL collector. Normally you want to go to some kind of backend, right, with that kind of data. So to do that, we're going to simulate going to a file system. So there'll be an actual file in the temp directory where you're going to see this stored, just like you would in the cloud, right? Cloud storage, cloud backend, whatever you're doing. Okay? So what's that look like? What you see here is we have the hot reload on, we have a certain kind of backend and all that kind of stuff going on, and you see this going to standard output. So we'll turn that on. So here's the front end running. It's got it coming out of the console. And we're going to go over here and we're going to turn on the OTEL envelope. That happens in the processor section. And oops. There. And we'll do this to 4912. You see now what's been added is a resource and a scope. This is part of the OTLP protocol. So not only do you have the workload and the description of what you're doing, you have a resource and a scope with a bunch of information you can add into there. And you see that nothing's really happening with that, right? It's just empty. So let's go in here and let's show that we can modify by adding a few things to that scope, or to the resource, I guess you would call it. And now you see inside the resource, you see a service name and you see a host name being added. You can also go down here and you can add in the scope. Now we see stuff inside the resource and inside the scope, right? Not very pretty yet. Let's go turn on the OTEL. Just collecting and sending it to the back end. So now it's ready to go, but right now we haven't sent it anywhere yet. So let's go down here and send it somewhere to the actual collector. And the funny part is if you kill the collector, instead of seeing that nice status 200 there for the HTTP, it'll start saying, I can't send it there, I can't send it there, I can't send it there. So he just stops, he doesn't get to hit that back end. If you watch over here on the OTEL collector, oops. Yeah, there it goes. So it's basically feeding and coming out this back end. It's not very pretty though, is it? So let's go over here and make it a little bit more prettier. And will send it to the file system now. And the only thing that requires is that we change this to 2, which has a different. So the original OTEL configuration was just sending it to the debug output, so basically to the log, and now we've added a file output, right? And he's listening on the 4317 port. So before I do that, I'll show you that. See over here, it's puking now. It's saying I can't send it to the OTEL. It's not on. We can turn it on. It says, oh, I'm happy again now, right? Now I can send it to it. Now what's interesting here is it should be sending it to the logs and to but that looks like crap, doesn't it? It's not really easy to see what's going on in these things, but you see it's streaming, so it's sending it to the file system. So let's make it a little bit prettier. And if we look here, we can make it smaller, and you can actually feed the scope. You can see the resource section, and you can see we've added some stuff to the actual body, right? So we've done it all, basically, that I promised. That being said, back to this, see if they're awake. Yep, good. Okay, so everything I promised we did, I believe. You can do the QR code to go to this. You can also go to the short URL. This is a 7-lab workshop right now. After they release 4.0, I'll start adding some new stuff in there because guess what? Head and tail sampling is coming. There's nothing cooler, I think, than head and tail sampling in a console. So you get traces in the Fluent Bit log output. It's pretty kind of neat. So there'll be some new stuff coming. It will be based on 4.0, not 3.2. You can do all this fun stuff in there. You can also go to this one and find a bunch of other stuff that we host. So you can do Prometheus workshops, you can do OTEL workshops, and Percy's. Anybody heard of Percy's? Nobody's heard of Percy's? It's a sandbox project inside the CNCF. It's the first visualization and dashboard project in the whole CNCF landscape. It's initially targeting metrics in Prometheus and PromQL. It's well worth taking a look at. You can build a really cool dashboard in there. And if you're interested in looking at some of the telemetry pipeline stuff at scale and what that looks like inside of an enterprise, feel free to go take a look at this one. This is also a lot of fun. And with that, are there any questions? I think I'm within a minute, right? Yeah. How about that? Pretty close. Spent more than half the time on the demo, so there you go. Tried to sneak it by you guys, but you were too sharp in the beginning. Any questions? Was it that self-explanatory? Cool beans.
Thank you, Eric.
You're welcome. Thank you for coming.
Yeah, with that, we complete the session for the morning. So now it's a lunch break, and see you in, I don't know, an hour and a half.
We have a bio slide, so yeah, we're good. Oh, okay, so no.
Okay, welcome back from lunch. Hello, everyone. Up first, 2 o'clock, we've got Fred and Jimmy, who are going to talk about from milliseconds to microseconds. So you guys can introduce yourself. I think you've got 30 minutes in total, so maybe 28 plus some time for questions. Cool. I'll take it away.
All right, welcome everyone. Today we're going to be talking about pushing Kubernetes to the limit when it comes to performance, specifically throughput and then latency. Now, this talk is going to be kind of jumping across different resource types and subjects, and that's largely because when it comes to kind of high performance, there's kind of these fundamental properties, and some of those properties live both in your code and in the cloud providers and also inside of Kubernetes. So while the subject is Kubernetes, we're going to kind of be like flipping across these different domains and then kind of bringing it back into Kubernetes and some of the settings that you need there to actually push your workloads. Because you kind of have to fundamentally understand what you're doing at a core level, whether that abstraction is provided by Kubernetes, your programming language, or your cloud provider. So here's an overview of the agenda today. Basically, we're going to give our intros and kind of tell you why you should be trusting us and listening to us, why we're the ones talking about this. Then we're going to talk about the significance of like why you care about low latency or high throughput workloads on Kubernetes. Then we're going to go through the high throughput one first. Frederick's going to cover that content. It's going to be largely talking about a use case, and object storage, networking, and disk I/O are going to be kind of the focus there. Then I'm going to talk about low latency, so specifically trying to deliver things within a few millisecond window. And that's going to focus largely on memory and CPU. So who are we? I'm Jimmy Zielinski. I'm a co-founder of a company called AuthZ. AuthZ built a product called SpiceDB, which is a database service built specifically for storing and querying authorization data. So that is a low latency system, and we run our products all on top of Kubernetes and support our customer environments all on top of Kubernetes. Prior to that, I basically have been in the cloud native space since the beginning. Before the CNCF was even created. I've created a couple of projects in the space, like the operator framework, and I've committed code to a bunch of foundational projects in the cloud native ecosystem. I'm also an OCI maintainer. Frederick?
Jimmy and I know each other from CoreOS, so we both kind of started around the same time. I'm the founder of a company called Polar Signals. Our product is a continuous profiling product, which essentially allows you to understand performance characteristics of your workloads down to the source code. And our system, in contrast to AuthZed's, is more of a high throughput system rather than a super low latency one. So that's why I'm focusing on that part. You may also know me through my work on the Prometheus projects. I'm a maintainer of the Prometheus project. I also created the Prometheus operator. If people are using maybe Prometheus on Kubernetes, you're maybe using some of those things as well as a Tanos maintainer.
All right, you may have seen a visual something like this. This is a representation of Jeff Dean's kind of latency numbers. Basically, if you're not familiar, Jeff Dean is like the head researcher at Google. He's been there for many years. He's basically championed a lot of the papers and foundational technologies that you've seen come out of Google, especially when it comes to the cloud software and how they've scaled their business and all the backends associated with it. This is just my favorite rendition of it because you can curl a very short URL and render this in any terminal. So if you're like, hey, hold up, wait a second, what is the latency for like decompressing something with Snappy? You can just like curl this really quick and then have like a ballpark idea of how it compares. The utility of this visual, I guess, is the real question. Like, why does Jeff Dean think that all programmers should have like a good understanding of kind of like these comparisons between latency? I think that is the same reason why this talk matters to this audience. Did you want to go over these 3 bullet points, Frederick?
Yeah, so basically, performance matters for essentially one of those 3 reasons. The most important one, and this is sort of the domain that Jimmy and I move in, fundamentally some problems require high throughput and or low latency to be solved at all, to work at all. But there may be other reasons why you want to improve performance of your system, and cost savings is certainly one of those. I think everybody likes the idea of doing the same work and spending less on that. And then ultimately, if we do less, often that results in simpler systems and ultimately then reducing the operational burden of operating those systems, which is also a property that I think everyone likes about systems. So yeah, let's dive into high throughput systems. And for that, I brought an example today of a cache that it sits in front of object storage. I think this is kind of an architecture that is becoming more and more important and more popular. You may have seen earlier, I'm also a maintainer of the Tanos project, which is kind of a distributed version of Prometheus if you're not familiar with it. It also stores the raw data on object storage. And so again, this is kind of becoming more and more popular. And so oftentimes, people want to, for various reasons, and we'll see which reasons a cache in front of object storage actually makes sense once we understand the fundamental nature and physics between these systems. So in our case at Polar Signals, the reason why caching of object storage data matters is because we run pretty heavy queries against a large amount of data that ultimately rests on object storage, but of course we want to make it as cheap and as fast as possible to query this data and make it available to be interactively explored by our users. And so this is kind of the example, this cache in the middle is what I'm going to go through and analyze the fundamental properties of so that we understand what we get out of a cache and when we should be applying this kind of architecture. So a bit of napkin math here. This is a little bit small, so I'll go through it. So basically, for every request that you do against object storage, ignoring the cache for a second here, we pay a baseline 200 milliseconds of latency. So every request, kind of the P99 latency, is 200 milliseconds. And so this is a fundamental factor why caching may be really desirable. If these 200 milliseconds matter to us and we want to remove these 200 milliseconds, then caching could be really interesting. Something that's quite interesting and something that we can rely on from our cloud providers is there's basically no throughput limits in terms of object storage as long as we have the network bandwidth on our network cards. And so this is actually a really interesting property and one that we're going to be making use of a lot with this cache. Roughly what AWS and GCP are telling us, for each request that you do against object storage, you'll get about 100 megabytes per second of throughput, provided that you still have enough bandwidth available on your network card to actually do this. The recommended chunk size, so when we have data at rest on object storage, the recommendation from AWS and Google and Azure are to chunk each of these requests. If we're, let's say, requesting a 1 gigabyte file, chunk them into 8 megabyte slices. That way you can achieve the highest throughput. However, something that we also need to be aware of with object storage is every single request that we do does cost. However, the cost is actually pretty low, which is ultimately why this kind of architecture is really desirable. We pay about 0.04 of a cent for 1,000 reads. And so a very quick example of napkin math here, if we do actually want to request a 1 gigabyte size file, we can chunk that up in 128 requests, each of 8 megabyte size, and that costs us the 200 millisecond base latency plus 125 milliseconds to actually retrieve all of those chunks. That ultimately ends up costing us 1/100th of a cent. So this is kind of a base number that we're going to be using throughout this example talk, and why some things matter and why some things don't matter. So I already kind of started hinting at this. This ultimately only truly works if we have 100 gigabits of network available. That does exist on cloud providers, but you would need to be careful, and we'll see this later, which instances you're actually choosing. So this kind of illusion that cloud providers have given us that you don't need to care about the underlying hardware and all of this is fundamentally false when you're thinking about high performance and low latency applications. You actually do need to care to quite a large degree what the capabilities are of the underlying instances, and you need to be careful with selecting those. So to get exactly the properties that we just talked about, you need 100 gigabits of networking, and every time we have that, and we'll see in a moment which instances this applies to, every time we have the network bandwidth, our latency doubles. So that's really important for low latency, for high throughput. On AWS, for example, some of the cheapest instances have only 5 gigabits, but it can go all the way up to 400 gigabits with the P4D instances. On GCP, we start a little bit higher, but we also top out a little bit earlier with their GPU instances, the A3 and G2 instances. The C4s are actually really interesting, particularly the C4A. Google has finally caught up a little bit in terms of the ARM64 game, which I think AWS has kind of been largely pioneering, I would say, in the cloud ecosystem. But the C4A instances are now super interesting for high throughput as well. So in case you can't read that, the C4A ones are the ones with 100 gigabits, and they're pretty good in terms of price per performance, both in terms of CPU, memory, and networking. So again, if we have this example of reading 1 gigabyte, ultimately, at some point, this has to be retrieved from object storage. If it's at rest there, we're always going to pay the 200 milliseconds of latency plus 125 milliseconds in actually retrieving this content. Now, between, in our case at Polar Signals, our query infrastructure and the actual cache, let's assume for a second that we're going to have 100% cache hits. We are still going to be paying 125 milliseconds in latency. And so this is actually a really important piece of data to understand because it influences what other things actually matter. Because, for example, a reality check in networking on cloud providers is everything that I've told you so far kind of ignores the fact that we are living in the real world and we have multiple zones in a region. If you're not familiar with this, basically each zone in a region on a cloud provider, they are dedicated data centers and are typically anywhere between 20 to 100 kilometers physically apart from each other. They are very, very well connected to each other with high-speed network connections, but we are still bound to the laws of physics. And let's take the example of data centers that are 100 kilometers apart from each other. We're still working with a base latency of 0.33 milliseconds. So that is assuming that there's no delay because of networking hardware or whatever. We cannot get faster than 0.33 milliseconds of latency between those zones. Obviously, the distance matters because speed of light, but that's what we'll work with for a second here. And so what that means for our example of high throughput, this kind of latency across zones doesn't matter. For some very low latency applications, it may matter because, as we're seeing here, I have a couple of examples of latency numbers. So within the same zone, within the same data center, we are definitely sub-millisecond, whereas across zones, we're somewhere in the realm of up to 2 milliseconds. In our example of we're always going to be paying 125 milliseconds of latency to retrieve 1 gigabyte of data. 2 milliseconds doesn't really matter. The big chunk is still how much network throughput can we actually push through the network cards, right? So this kind of latency, for our case, doesn't matter, but for other kinds of cases, may actually matter. For us, what matters much more is the cost of network bandwidth across the zone. That costs us 1 cent per gigabyte transferred. And so this fundamentally governs how we're going to be thinking about caching of object storage data. Because really the most important part here in the equation is the cost of network traffic. Within the same zone, we get effectively the throughput of our network card, and then the rule of thumb for cross-zone traffic is about 5 to 20% penalty, but in the grand scheme of things, not extremely huge. Your mileage may vary pretty significantly across cloud providers. It's pretty hard to see, I think, but the scale, the speed of light for AWS and GCP is clearly faster than for Azure. I don't know exactly what's up with that, but yeah, I don't know. The speed of light for Azure is about apparently half as fast. So yeah, if latency is actually what matters to you across zones, these kinds of data points do actually matter to you. So again, if we are always going to be paying 125 milliseconds in latency for getting our data through the network, then this kind of path across a zone for latency doesn't matter. However, in terms of cost, it certainly does matter. If we have a cache miss within the same zone, we're paying 1/100th of a cent in object storage calls, whereas for cross-zone traffic, we're paying 1 cent, which is 100 times more expensive. And so this is exactly for this type of workload, something we want to avoid at all cost. And so at Polar Signals, the way that we solve this is that we just encourage network traffic to never leave the zone. Now, there are various ways of encouraging this. There are features directly built into Kubernetes to encourage this. Up until, I'm forgetting the version number at the moment, but up until recently, this was done using topology-aware routing. And the auto mode essentially tried to load balance the traffic evenly across zones, but try to encourage it within the same zone. But there were kind of some sort of unpredictable features of tying network traffic to available CPUs, that this didn't become a particularly ergonomic feature. And so ultimately this encouraged the new evolution of what's now called traffic distribution, which essentially is just if there is a network endpoint available within the zone of where the outgoing workload is, then I'm going to route it to that endpoint that is within the same zone. Only if there is no endpoint available would it route the traffic to a different zone. And so I think this feature is probably going to become much more widely adopted, but it is a brand new feature as of Kubernetes 1.31. And so the configuration here, in case it's hard to see, is traffic distribution prefer close. So Kubernetes 1.31, traffic distribution prefer close, and your CNI provider actually has to support it. So that is one way to do it. And then the most naive way, and sometimes actually a really good way to do this, is to literally set up your stack multiple times, once per zone, and only genuinely allow ever routing that those requests within components that are within the same zone by literally having a service per zone. So yeah, but configuration is good, measuring it is better, and so due to lack of having good metrics available for this type of thing from cloud providers, we actually created a project called KubeSonnet at Polar Signals that allows us to measure exactly which workloads are causing cross-zone traffic, because that's a major cost driver for Polar Signals. And so whenever, now that we've gone through this exercise of actually optimizing our workloads to never cross the zone boundary, we can now use this for alerting purposes, for example, to make sure that if we're accidentally doing something that's causing cross-zone traffic, we're catching it early rather than when our cloud bill gets too large. Last but not least, disk also matters. So far, we've kind of assumed that everything is just zero latency and all in memory. Memory speed is much higher than network throughput. Disks, if you wanted to also kind of store all of the cache data on a local disk, let's say on a local SSD, that's a popular way to do this with object storage data. Then there's actually a really important piece of information that we need to know about, which is each of these SSDs that are attached to our instances on a cloud provider, each of them can only do 660 megabytes per second. And so this is, we need to have a pretty large RAID array of disks to actually match our 100 gigabits of network traffic, of network card that we have available that we used as our example. And so depending on the SSD available, that may be anywhere between 14 to 24 local SSDs that you would need to attach to your local to your nodes on GCP, for example, to match those 100 gigabits. And so all of these calculations are really important to do so that we don't have kind of unexpected behavior when it actually comes to running our workloads in the real world. So, oh, sorry, we got the order wrong here. The way to do this on Kubernetes is we can use this feature called local ephemeral storage. On GKE, for example, this is a managed feature where you can basically just say, I want all empty dir volumes that I'm going to be mounting into my containers on nodes that have local SSDs mounted. I want those to actually use the local SSD. And so we can then use just the ephemeral storage requests on our containers and limits to actually do those requests against the real local SSDs. And that way, we can actually tie this back into Kubernetes. We can also use the mtdir size limit to ultimately limit this. My general recommendation is keep the request, the limit, and the size limit the same. Otherwise, it gets kind of complicated to actually consistently manage across your entire infrastructure. So yeah, we'll flip back and forth a little bit here. Sorry about that. So now we've gone through an example of high throughput. What about low latency?
We've only got a couple minutes left, so I'm going to try to fly through this. So if you think about kind of the first image I showed, Jeff Dean's numbers, that comparison, and you're trying to target a low latency workload, like your workload has to be constantly delivered to the end user within a certain time boundary. That time boundary might be single-digit milliseconds. The first place you probably want to look is your programming language, and that's just because garbage collectors can span their pause times from nanoseconds all the way up to seconds, depending on what you're doing in the language. And if you're doing something high throughput, it probably means, or sorry, low latency, you're probably also trying to serve a lot of people at the same time, which means you're churning through lots of memory, which means there's lots of garbage being produced. So you're gonna have to fundamentally think about your garbage collector if you're writing a garbage collected language. And now fundamentally, garbage collectors kind of are this trade-off that you're always making, and that trade-off is throughput for latency. So to do that, you kind of have a couple different knobs you can use to kind of work in tandem or give hints to the garbage collector to help you actually get the performance that you're trying to achieve. The first is just fundamentally reducing allocations. And you can just do that by pre-allocating things. So making sure that you're not making a bunch of tiny, small individual allocations, which are going to add up to a bunch of different things now the garbage collector has to track. Rather, you can kind of pre-allocate one large thing at the beginning. There's a couple different strategies you can use there, like things like arenas. The real big one that I honestly see being a huge boon is allocation reuse. If you open up pull requests to like a community library and you just fix a couple allocation reuses, sometimes I've seen like massive performance improvements just like hit the whole community at once. Saving allocations in something like gRPC is just going to impact the entire community, and you might see throughput numbers like double or even triple just from a tiny pull request just reusing memory. Actually, LinkedIn did that pretty recently if you're interested in gRPC specifically. So there's also different allocation schemes. I kind of mentioned arenas earlier when it came to pre-allocation. Another thing you could do is fundamentally design your software a different way. One strategy would be thread per core. This is kind of how certain databases like SiloDB work. What they do is they actually design it such that requests come in, they get dispatched to one particular core, and then that core runs the end-to-end lifecycle of that request. Unlike a lot of other programming languages where you're kind of context switching in between and you're kind of managing, any core could be touching a particular workload. In this scenario, you know end to end that this request was processed by this core and then the next request came in serially to that core. So instead of kind of like switching between a bunch of different tasks, you kind of have these separate pipelines. And those pipelines then scale as you add more cores. The next thing is avoiding memory pressure. So you can just use GC-friendly types. I'm going to give an example of that after this. And then fundamentally just tuning the GC, giving the GC details about the environment so that it knows when it should be running, so it's not running the garbage collection process more often than it needs to. Cool. So I have this example of Go garbage collection. And the question here is how much time does GCing the code on the top take? Well, the answer is ON. It has to actually iterate over every item in the map. And that is because the user struct has a pointer in it. So the garbage collector needs to go through every single item in the map and then chase down all the pointers in every single item to know if it has hit a root or not. Hit a leaf or not. So if you were kind of storing session IDs to users, which I have as this example, one cool trick you could have is just storing session IDs straight to usernames. Say I only needed the name field. I didn't actually really care about the profile pointer. I could actually have a separate map, and while it would consume more memory, the GC time for the second, like the lower version of the code, is actually 01. The garbage collector can actually entirely skip iterating over any items in this map because it knows the native types to this are int and string. There's no pointers to chase, so it doesn't actually have to do any work. All right. So I kind of wanted to transition to talking about Kubernetes features that would actually help you achieve kind of these things once you've designed your software to be memory efficient. The Kubernetes defaults, I like to say, is like your kind of like router password. The defaults are basically like, it's best effort. It kind of works like, I'm sure if you look at the Wi-Fi right now, you'll see there's a bunch of people running default networks. You don't really know the password. It's not really secure though. That's kind of what the Kubernetes defaults are like. There's really no protection about any other pod consuming all the memory on your node if you haven't tweaked anything. You don't get quality of service. And then like if you have two sensitive workloads, they could still get actually scheduled on the same node. So that means if that node dies, like you actually lost 2 of your pods rather than 1. So the thing that everyone is going to tell you is, cool, just slap some requests and limits onto things. If you're unfamiliar, requests basically tell Kubernetes what must be available for something to get scheduled, and limits kind of like set a hard limit, and the killer actually will kill it once you kind of exceed those boundaries. The problem with this is it's actually reactive and not proactive. So what happens is the Kubernetes scheduler is actually going to ping every so often and check, and it's actually an API flag how often you're going to check to see if these pods are exceeding that boundary. The problem is there's actually a minimum value here. And the minimum value here, I can't remember what it is off the top of my head, but it's like a second. It's not milliseconds, right? And your workload is probably handling hundreds or thousands of requests per second. So that means in the time it takes for Kubernetes to react to something bursting on a particular node, you could have just flubbed thousands of requests. So that's not really acceptable for a lot of workloads. Then the other neat thing that you can do here, I haven't actually seen a lot of people talk about this. When you set these limits, so say you set a memory limit here, you can actually reference that memory limit using the downward API and pass that into your applications. Specifically, this is useful for garbage collected languages like Go or Java, because then you can actually tell that environment, hey, like you have this much memory, which means the garbage collector will be aware when you're getting pressed up against that memory limit, and it will actively run in tandem and work better with your environment. Cool. So once you kind of cover the memory side, you can start thinking about CPU. Once again, the most important thing here is kind of the design of your program. Ideally, you want to parallelize your core algorithm because fundamentally, like CPUs don't get faster, we just get more cores and kind of more clever architectures around sharing. So you're gonna have to do that. The next thing you can do is kind of take that parallelism and think about it not just on a per node basis, but on a like cluster-wide basis. So the example I have here is SpiceDB. SpiceDB actually does a thing where when it serves a request, it breaks it down into sub-requests, and those sub-requests use a consistent hash to associate where the sub-request will be routed to in the overall cluster. And then basically that work is identified by the actual kind of work being done in the consistent hash ring, and then we kind of cache those values in the cluster at that location. That way you kind of think of it as like a distributed cache storing thunks of partially evaluated results. So if you have any structural sharing across your requests, you can actually reuse that work. There's a couple other strategies here, things like function called deduplication. That means if 2 things actually are trying to do the same work, you can actually use a mutex to stop the second one from running until the first one returns, and then you use that result to return to both, which will cut the latency for the second one in half or more. The next thing you can do is actually build a scheduling system. Go, for example, and Java don't actually have ways to build priority around the default async framework, so you kind of have to build those yourself. The next thing you can do is just hedge. So if a request comes in, you can actually double the work, because if one of them breaks or fails, you need the other one to come back in time. The next thing here is like runtime diagnosis. You really have to profile to understand this stuff. There's no intuition. You're not going to like just understand from writing the code how it's going to perform. You have to measure, and measure in a real environment. Basically, all your time is going to be spent actually bookkeeping, probably not in your core algorithm. So things, you could use SIM in a bunch of places, but most likely you have to worry more so about noisy neighbors. So at a high level, if you're unfamiliar, there's context switching. That is going to be your killer here. Basically, your machine, there's parallelism and concurrency. You're probably doing a lot of concurrency, swapping between different tasks. What you really need to do is prevent this from happening, because this is happening actually at a bunch of different layers. Happens in your programming language, then it happens at Linux. Linux is swapping your process with other processes on the hardware, and then if you're using a CPU that has hyperthreading, for example, your CPU process actually is swapping between the actual physical core. It has hyperthreads that it's scheduling across a single core. Every single one of those context switches at any of those layers is adding overhead and blowing away caches that are going to impact your performance. So there's one kind of like major Kubernetes thing you can use here, which is taints and tolerations. That basically lets you pin your workloads to specific cores, and you can kind of set labels to build policies around that. That's going to guarantee you that like you at least land on a machine that has hardware optimized for your workload. Then there's this super obscure feature, which is static CPU manager. This one lets you actually specify a whole number CPU, and if you do that, you don't give it like part of a CPU core, it will actually pin those cores. And you can actually use this to say, actually, I want 0 other processes running on these cores ever on this node. This is super useful because you actually get that guarantee, but you are trading off one core that has to run the system. All right, try to make it really quick, but I hope you learned something in this talk, and then I hope you get excited and go look at your programs and get ideas for how to speed them up. Cool. Thanks, everyone.
So there's no time for questions because the guys have ran over, so we'll be starting the next one in probably about a minute. Yeah.
Sorry about that, Ben.
That's okay. Next one is Antonella and Yuri, who are talking about building air-gapped control planes. There's 5 minutes. Okay, the full thing. You want the full thing, or are you going to do question answer at the end?
We will try to feed, but most probably we will not have time.
Right, I can give you a couple of minutes extra if you do go over, but not much more.
Okay, so like plus 2 minutes.
Yeah. I'll. Don't worry, I'll keep you on time.
Yeah. Okay.
Okay.
Thank you. How's the audio? Like, is it
Audio's fine. Both of these work, and the upper one works. Yeah, so that's fine.
So I can just stand in front of. The main question, should I...
you can use one of these as well, if you want.
But it's not mandatory, right?
Not mandatory?
Yeah.
So
okay.
if you can stand here,
yeah.
stand in front of it, it's quite good.
Okay.
Yeah.
Okay, cool. Appreciate it. Yeah, and very nice to meet you.
Andrew?
Like, the venue is amazing.
Yeah, it's lovely. It's lovely. Okay, with that, I think we'll give it a start. If you just walk closer. So we have Antonella and we have Yuri, who are going to talk about building a gap control plane.
Thank you guys a lot for showing up for our presentation. Today we are going to talk about how we have built the air gap control planes in Novo Nordisk by using Crossplane and Argo CD. So this project was combined effort between Novo Nordisk and Outbound. And from Novo Nordisk side, it's me. I'm Antonella Chukarin. I'm a tech lead in a control plane team that is part of the software engineering platform. And Yuri?
Hey, I'm Yuri from Outbound. We are creators of Crossplane. And super excited to be here. And Antonella, please kick us off.
Thank you. So I'll just briefly say what we prepared for today. We will explain a little bit what is the Ymir platform, so what my team is actually doing, how that goes into the pharmaceutical industry, our solution, some challenges along the way, and hopefully demo at the end. So Ymir platform, that is what my team is building, and Ymir is coming from the Nordic mythology. It is a big giant from which the world was created. It is a bit more big story. It's like from his flesh, the earth was created and etc., like all the mythology stories, right? But it goes very, very well with what we are trying to do. So we are building the foundational abstraction platform that is interfacing with the different providers just to create different cloud resources and also some of the Kubernetes resources. Our main goal is to have a fast time to market, and we are just trying to enable our developers, our product teams, to focus on the code, focus on the new features that they have, and just leave for us any kind of commonalities that they have across their applications. We are also empowering them to build agnostic platforms that can run on any kind of environments, and we are doing that by leveraging Crossplane and Argo CD. So how Yammer works in the pharma industry? I think many of you probably worked or are working in the industries that are highly regulated. And I would say the pharma industry is one of the top of the list. And I was working in also in the finance industry. So what I can say that the compliance with the pharmaceutical industry regulations is vital to ensure the data security, traceability, and integrity. So the IT systems that we have in Novo Nordisk play a critical role to develop, manufacture, and distribute our products. It is very important that this chain is not broken, because our end customers are patients that are using our products daily. And our company is 70,000 people, so it's employing 70,000 people, and I think less than 2,000 is developers. So until recently, I would say nobody cared about us, even though we were yelling all over that like we need to make our compliance better, that we need to change the processes that we have just to enter in the new age of development. So the second thing is we need to have secure platform. We call Yammer the key of the kingdom, and it really is, because it's holding everything that we have. And we want to have as minimal human interaction on our control planes. And we wanted to do that through the GitOps. We wanted to make sure that everything is coming, any kind of change, any kind of configuration, modification is coming from the GitOps side that is then interfacing with our control planes. And of course, we are building Kubernetes platform, so I think natural choice was to use Crossplane from the beginning. But as many of you, if you tried Crossplane, know that there is a chicken and an egg problem. And we were in a bit of situation where we needed to figure out the way how to create the infrastructure that will hold any kind of cluster, right? Deploy Crossplane there, and then from there create our Kubernetes cluster with Crossplane that is then going to create the target clusters. So it's a whole circle, and Yuri is going to explain it how we achieved it. And the last thing that we needed to consider, as I mentioned before, is GitOps. So we needed to have everything as a code. We needed to have our commits signed. We need to have traceability to any kind of change that we are doing, together with automated testing and, of course, PR approvals. And I think Crossplane and Argo CD are the perfect combination for that problem. And now Yuri is going to present the solution that we have.
All right. Can you hear me? All good? Yeah, perfect. So let's jump into solution specifically. So as Santanella mentioned, and thanks a lot for Antonella for the great context, we will operate in a kind of air-gapped environment. And we will operate specifically in Azure here, but everything is like conceptually applicable to any cloud platform. So focusing on Azure, obvious kind of thing to try out for air-gapped environment is a private AKS, but it has like a special properties, let's say. So public AKS, if you play with that, it's pretty straightforward. You deploy it, you contact the API, everything is working almost out of the box. We have a bunch of examples available upstream as a bound reference platforms, so no issues there. If we try to depict the situation and a happy path with a public AKS, it's kind of easy. So we have a cross-plane cluster. Hopefully it's visible here, right? It talks to the AKS APIs. AKS Cloud Control Plane deploys the actual Kubernetes cluster. It's a still happy scenario, deploys the actual Kubernetes cluster, and public standard Kubernetes API are publicly accessible, right? So with provider Kubernetes of Crossplane, we can get into cluster and make us some special configurations, deployments, anything we like. So it's pretty straightforward. In case of private AKS, though, it's a little bit more complicated because we still can deploy AKS cluster because API is available, but the Kubernetes API itself is private, so it's not publicly exposed, and provider Kubernetes can't configure stuff. So we have this tricky situation of chicken egg, as Antonella mentioned. So what we are going to do, we came up with the idea of solutions that we will deploy a shared private network, meaning like it will be shared between some bootstrapping mechanism and actual this private AKS cluster. And it will be act like on top of Bastion VM, and we will use Azure Bastion service like just for admin connections there. So if we depict that on a diagram, it will look like this, pretty straightforward private network, right? Bastion VM on top, some service in front of it. But how to bootstrap the bootstrap, right? So we still need some form of mechanism, automation that would bootstrap the initial bootstrap environment. So kind of maybe popular, non-popular solutions for that are like a Terraform, nowadays OpenTofu, but we quickly discarded this kind of legacy infrastructure as a code. We want to use Crossplane on every stage. We want reusable abstractions, and we decided to put Crossplane within a GitHub action. But how to do that? Pretty frequent counter-argument to use Crossplane in these kind of bootstrap environments is actually that you need a Kubernetes cluster to run Crossplane, so where to get it? In this case, we will need to deploy like a local client or CRD cluster, anything will work within a GitHub action on top of GitHub runner. Install Crossplane there, install configuration, propagate credentials, reference them in provider configs, and actually finally instantiate this Bastion composite resource that will bootstrap our environment. So it's quite amount of moving parts and quite amount of work to do it on your own, so it might be also annoying to maintain. So luckily we have a thing called uptest that most of this stuff, maintenance stuff, are fully automated. So what is uptest itself? So main mission of uptest is provide end-to-end test framework for your Crossplane configurations. So it's available open source, available upstream. Together with my colleague Steven, we did a talk on testing Crossplane back in Hong Kong last year. So if you're interested in uptest as a framework, please check it out. In this particular story of bootstrapping, we will use uptest as a bootstrapping mechanism. So for uptest to test stuff, it needs to create a Crossplane-based environment, right? So, and all these steps that I mentioned before, they're fully automated. So we'll just use uptest for bootstrapping things. So in this case, we will run an uptest on top of standard GitHub hosted runner. So basically GitHub managed, like everybody here most probably worked with GitHub hosted runners in one form or another, right? Just by running GitHub actions. So uptest will be deployed there. Uptest will deploy a local Kubernetes cluster with Crossplane on top, and everything will be configured to bootstrap the actual bootstrap Bastion setup. So we will solve this first chicken egg. We have a quite amount of chicken eggs in this story, so this is the first stage one, and we deploy the first Bastion VM that will act as a next stage bootstrap mechanism. So now we have this air-gapped Bastion, but how to connect to this guy, right? So it is isolated virtual machine. We only have a Azure Bastion service, but it's designed only to be like, you know, admin-only operations, only like in case of some incident. It's not for automation. So in this case, to work around that problem, we will register Bastion VM as a self-hosted GitHub runner. So basically, right after deployment, Bastion VM is going to be automatically registered as a self-hosted GitHub runner. Basically, it will provide us with integration and access to GitHub repositories, GitHub secrets, and basically seamless integration of our Bastion setup with GitHub machinery. So very nice, legitimate backdoor, right? Exactly what we want. We want nice mechanism to deploy to drive deployment within a bastion. So, and all the registration, again, it's automatically configured by crossplane. You don't need to do anything when you already encapsulated within a crossplane abstraction. Next stage, we have a bastion cluster, right? Now we are almost ready to the next stage, but first, before we deploy our real control plane, we still need some form of cross-plane cluster that will drive it. And we will use uptest again. So our bastion VM will become a local bastion cluster. Basically, uptest will deploy a Kubernetes again, a crossplane, but this time it will use crossplane also to deploy Argo next to itself, basically making this bastion cluster fully GitOpsified. Now we have actually we solved this chicken egg problem with 2 stages. We already have a crossplane cluster fully GitOpsified within our private environment. And now it's time to actually deploy a real private AKS cluster. By real, I mean like a non-local one with a dedicated control plane, with a multiple nodes, high availability, all that stuff. And it will act exactly like as an EMIR, the main control plane to drive actual infrastructure. It will look like that. So we will use the same mechanism, right? The Argo will obviously talk to some GitOps configuration repo and eventually drive the crossplane to provision the main control plane EMIR in the form of a private AKS cluster, and we actually solve this Bootstrap problem, and the connectivity will be direct in this case because they sharing the private network between Bastion cluster and the main control plane. And after that, when we have our EMIR main control plane ready, we basically have all the goodness there, crossplane plus Argo, everything is API driven and everything is GitOpsified. And eventual state will look like that, right? So we have a EMIR as a main control plane that basically is capable to configure any infrastructure in your environment. It can be other Kubernetes clusters, virtual machines, networking, databases, anything you like, right? So with crossplane, you can drive as many things as you want. So just to conclude the solution, right? So 2 stages, starting with a standard GitHub hosted runner, bootstrapping Bastion cluster that is registered as a self-hosted runner, and the eventual implementation of the main control plane that is capable to control everything. So that's the solution for the chicken egg. And the next stage, the next part we discuss is actually how to run the stuff in production. So back to Antonella.
So, of course, this solution has many moving parts, and it has some of the challenges. I think first and foremost challenge is the Argo sync waves in a crossplane world. I think this is something that almost drove Yuri crazy, and he called it ocean of the sync waves. It's just because of the amount of the sync waves that are right now in our GitOps repository. Reason for it is that Argo CD doesn't support the eventual consistency. So in that case, let's say that you have a provider config. You need to have first provider that is ready in order for provider config to sync. Otherwise, it's going to fail. And it's not going to retry. It depends, of course, of your retry policy, but you don't want to put that many of constant retries in your GitOps repository. So the idea is that you are very careful how you are ordering stuff when you are deploying different components for the crossplane. There is a very good video of the Victor's rant about this specific thing. And also you can catch Yuri or me after the conference or KubeCon if you have something, some kind of like better solution or you just want to share the pain. So coming back to the private cluster. So when we were deploying this solution, we needed to have a couple of things just in consideration. And that is, first thing is how we are going to do the configuration package propagation. So on the first blue screenshot, you can see there is 2 packages. The first one is the Argo CD Bastion, and the second one is YIMR. So the first one is that first Bootstrap package that is going to be deployed. And that package consists of the Argo CD custom API that's going to create initial Argo CD that is then going to kick off all the GitOps, that is going to listen to the GitOps repository and then kick off all the installations. The second one is on our actual private cluster, and that is the Yammer one that is in the private network. Here we have a carpenter, but what is more important, we have the same Yammer configuration. So we use the same package to deploy a different type of clusters. So we are deploying a private cluster and as well the public ones for our customers. Second thing that we needed to make sure to have is we needed to have the provider upgrades and downgrades. When we started creating this solution, with the configuration, you couldn't do the upgrades and downgrades. So what does it mean? It means that you need to specify it in your configuration, the versions, and then also in your GitOps repository, you need to have Kubernetes manifest for each of them. And then when you want to do the change, you need to do it in two places. Package something and also change it so the Git can take it. Nowadays, you can do the upgrades, which is amazing, but still you cannot do the downgrades. So if this is something that is very important for you, you need to keep it in both places. And the last thing is how we are going to test features. So we have a static control planes, but we also have the ones that we can dynamically create. And what is important that everybody is able to test any kind of feature that they have. And how that is possible, it is through the pipeline. So we have a Bootstrap pipeline that is going to, you can specify the branch, and then you can, in a GitOps repository, for the first initial Argo application, you specify the target revision, and that is going to be propagated, and that branch is going to be listened by the control plane plus the Bastion cluster. So let me try to show it, how it looks. I hope it's going to be more like understandable what comes first and what comes second. So this is our Yammer repository. And two most important things are our two branches here, two pipelines. So the first pipeline is when we want to create a new private network and the Bastion host. So this is going to deploy those two things and also is going to deploy the VM. That VM is going to be then registered as a GitHub runner. And how we do it, we have a couple of variables that you can pass to the pipeline. And most important thing is that you pass the token. Then looking at the settings under the runners, you can see we have a couple of them that are running. Some of them are offline, but some of them are running. So now this is registered in our GitHub organization for our own repository. The second part then comes with the Bootstrap pipeline. So the Bootstrap pipeline, when you run it the first time, it's always going to run the up test. So what it does, the first time there is nothing on the VM. There is some tools that we install, of course, on the initial installation, but there is no cluster on it. So this pipeline is going to see if there is a Bastion cluster on it. If there is no cluster, it's going to trigger the creation of the cluster. It's going to package our custom APIs, and then it's going to start creation of the crossplane and all other stuff that we need in order for this to run. So it could be the provider configs, propagation of different secrets. It could be any kind of configuration that you need on that cluster for your APIs to run. So once this runs, then it's going to install, and I hope this is big enough, but then it's going to install the claim. In this case, we have the Xargo, this is our custom API, that is going to be triggered. The first thing that it's going to do is going to do the Argo CD release deployment, and the second one is going to do the application set. This application set is important, as I mentioned earlier. That is the one that is going to say, please listen to our GitOps repository and then start applying in specific order different things. Once this is done and GitOps is kicked off and our applications are starting to sync up, is going to then eventually create the private cluster in this private network. So, yeah, and just to add one more thing is on any other run of this pipeline, it's going to know there is a Bastion cluster there. So in order for us to test the features, we run this pipeline and we just specify what is our branch and what target revision to listen to. Then coming back to the providers, so in order for do the change, as I mentioned, you need to do it in 2 places. So here I'm doing the change of the Azure provider, where it was on 1.11.0, and we are just upgrading it to 1.11.1. And we are changing that in our configuration. But you can see here, there is like a sea of the Kubernetes manifest changes of all those packages to reference the same version as the configuration one. Of course, for the upgrades, you don't need to do it now, but for the downgrades, you need it. So this is just something that it's not nice, but you can automate it. So whenever you want to upgrade the version that is doing this, that is doing change in configuration, triggering the build pipeline that is going to package your APIs, and eventually it's going to change the package version, so the tag that your GitOps, your Argo CD is listening. And that is how we are usually propagating our changes on our private cluster. So coming back to the presentation. So just to wrap it up a little bit, with this solution, we were able to create a cloud-native air-gap environment. Also, we have the full GitOps flow after the initial Bootstrap, as you saw. We are also using cross-plane for everything. So we really didn't want it to use a lot of tools, and especially for like something as infrastructure as a code, we wanted to stick with one because it is just easier. And then we want to use the same setup that we have for our own infrastructure and as well for our client's infrastructure, so for our developers. And with this, we have a very extendable solution that is reusable, and of course, with our custom APIs, it's APIs first.
All right, so just to conclude, very powerful combination, and yeah, we are happy to accept Q&A. I just want to mention super quickly that there are a couple of 2 good cross-plane talks at KubeCon that I'm aware of. Maybe there are some more. One is also very production-centric, and another one by creators of cross-plane, a cross-plane V2 focus. So there is a lot of new stuff that will be covered. So thank you so much, and we are happy to answer any questions.
Shove your hand up if you want to ask a question, and I've got the mic, so I'll try and find you. Anyone? Don't be shy. Excellent. We've got 5 minutes roughly for questions.
I just want to understand how do you onboard new cluster on Argo CD, and in an automatic way. Like if there is a new cluster when you create private cluster, how do you onboard it on the cross-plane EMR cluster?
Yeah. So if we want a new control plane, in that case, we need to trigger that private VNet pipeline, and then we just trigger the second pipeline that is the Bootstrap one. That is going to initiate the creation of the new private cluster. So these private clusters are only for us. This is our control planes. And then for our customers, this private cluster that is YAML one, then it's able to create as many of the, we call it X clusters, as we wish. And for our customers, the clusters are not that important. For them, what is more important is the runtimes that we create for them. And if you're interested, like also my team is here, so we can talk about what we are actually giving to our customers, our developers.
The question, I think, then you have Argo CD as well, right?
So yes, Argo CD is
do you
created.
install Argo CD again on the private cluster, or do you onboard private cluster on the?
So we have a Argo CD on the Bastion cluster, then that Argo CD is triggering the claim that is the private cluster. Then it creates the private cluster. And then on the private cluster, we have another Argo CD installation that is then creating the target clusters.
Okay, we've got one more.
Hi, thanks for the presentation. Just one question regarding the whole bootstrapping bits. It seemed to me a lot of convolution of tools that we're using just to try to do simple CI triggers.
Just two amazing tools?
I mean, you're using CI with the same credentials to trigger crossplane, to trigger a CI, to trigger crossplane, right? Why did you go that route instead of just doing some simpler bootstrapping?
Define simple bootstrapping?
I mean, you could just use GitHub Actions, no?
Yeah, but what to put into the GitHub Actions?
You already have the credentials anyways, no? Like
yeah, exactly. We have credentials, but we're using these credentials for a local cross-plane bootstrap setup. So we basically are using the same abstractions that we will use down the road in a real scenario. So it makes this bootstrap mechanism much more testable, and basically
it's more for the reproducibility of it.
We don't need to fall back to any kind of Terraform, OpenTofu stuff and maintain a totally different lifecycle. We have a single one. Yeah,
thanks.
That's the main goal. Yeah, great question.
Okay, anyone else? Don't be shy. Okay, all good. Thank you very much. Hello. So you got half an hour? Yeah. Do you want 5 minutes for questions, or I'll give you the countdown anyway. You'll get 5, 3, 1.
We'll see how we're doing.
You'll know. It's fine.
Yeah.
It's fine. Break is after you guys, so and
We'll see how it
25
goes.
minutes for break.
We have a live demo, so it might be that while. Yeah.
Don't say it. Don't say it. I hear you, right? I know.
I think we'll be fine.
Well, we're ahead of schedule.
Now it's
So we've got 5 minutes to set up.
make sure to.
Time for the next talk. We've got Mika and Lucas. Over you go, guys.
Yeah, thanks everyone for coming. I'm Micah Hausler. I'm a principal engineer at AWS.
And I'm Lucas, working at Upbound as a staff engineer. And we're both in the Kubernetes community in different ways.
Yeah.
And today we'll talk about some ideas to how we could secure even more of the things.
So to start out, we just kind of wanted to ask the question, like, why does end-to-end security or end-to-end authenticity specifically matter? Well, actually, first, no, we jumped ahead. Outline. Okay, so we'll talk about an overview. So we've got a talk today just about end-to-end authenticity. Why does that matter? So we'll talk about why that matters, kind of common attacks, and why you might actually care about this. And then the good news, like, okay, how do we mitigate this? And so we'll talk about some of the methods that can be used to mitigate these kinds of attacks. The kind of step-by-step of what does that take? And we'll actually have a demo too and kind of talk about next steps, like what's the future in this space.
Yeah, and well, here's a demo link. So actually the demo involves you. So at the end of the talk, you can pull up your laptop and actually try it out yourself. We have a server running for this.
Yeah, so kind of beginning here, why does this matter? So typically in a cloud native system, you'll have microservices, right? You'll have some services talking to other services. And typically, you might secure this with mutual TLS. So you have TLS on the server, but you also might have client authenticating itself using TLS, like an X509 certificate. But you also might be using a bearer token. So in this case, you might have a user whose name is Lucas calling your service with a bearer token. And then you have some gateway that is calling some backend service. And it's doing its own MTLS with some backend service, right? So as a user, you're not even aware of this necessarily. It's just downstream of you. Between the user and the server, you get authenticity, knowing that, okay, I'm seeing that the certificate is by this server, and I have this ID token, and it's authenticated with the server, and you get confidentiality. Your data is encrypted in transit. Between the gateway and the backend service, you also get authenticity, right? In the base and best case, there's maybe MTLS. You have server to server talking to each other, so there's trust both ways. The integrity, the message is signed at the transport layer with MTLS. So if a bit flips in the middle, like you have a bad network gear or whatever, like there will be retries and stuff. And at the TCP level, and you know that the content is going to be conveyed correctly. And then finally, confidentiality, because it's TLS, it's encrypted at the network level, so no one can see that content. But what happens if you have a hijacked or misconfigured gateway? Lots of bad things can happen in the middle, right? You can have your authenticity basically can be compromised. You can maybe have the correct token forwarded, but maybe the content of the message changes, right? That's not something that the client necessarily wanted. Also, very common in these kinds of systems, especially when you're using bearer tokens, you log things lots of times. What happens if you log the authorization header? Now your token that's replayable across requests is logged in the system, and maybe you're not aware of it, and it's just in some log that persists for 10 years because that's what security said that had to be done. And that's not great. So the client doesn't even necessarily know that this is happening. And their request might, again, be mutated in between this hijacked gateway and the backend server. So the server would see multiple tokens, not just the one token, of the correct user, and have access to all of these. And then could replay those on, again, back to the backend server with maybe not the correct user. So in this case, if I'm Lucas and I'm talking to the gateway and I've got token A, the backend could talk to, or the middle gateway could talk to the backend service using a different token, but posting Lucas's data. And similarly, like it could also change the content of the message as well. So not only replaying one user's token for, credential for another, but also, again, modifying the integrity of, violating the integrity of this system. So every component in this request chain has to be fully trusted, and that, in this world, could be problematic. At least the data is encrypted, right? So that is something that you get with MTLS, but you sort of lose all these other important things about, like authenticity and integrity.
And it could just be like misconfigured as well. It doesn't have to be malicious. Maybe you just did a bad change in some configuration somewhere. Yeah, so short OIDC primer. So what is OIDC? Because we'll look at some extensions of it. So OpenID Connect protocol. If you ever used SSO, then that's what's happening behind the scenes. What is nice about OIDC is that the verifier, which is the server here, doesn't actually have to kind of synchronously call out to the identity provider when it sees a token. So instead, it downloads the public keys that it can use for verification in the very beginning. Then the user, logs in, gets redirected back with a token, thanks to giving the username, password, MFA, whatever. And then when they use that token, the server here can look at the signature of that token and using those public keys, figure out the identity. So this is good because, the application, our server in this case, the relying party, has an easy time validating this token. We can propagate all kinds of extra information about the user, groups, email, all that kind of stuff. Not too much, of course, because it's in a header, but still. And we have the problem, though, that we just talked about, that it's a symmetric credential, so that when you actually put it with the HTTP request, if someone happened to see it on the way, you can forward it, do bad things with it. And also, it's not bound to request content. So these are some things that we would like to mitigate. So how do we do that?
Yeah, so next, this is the good news part. We'll talk about kind of how do you mitigate this problem, because this is kind of, even if you're using MTLS like we discussed, like bad things can still happen. So there's a IETF RFC 9421, you can go check it out, for HTTP message signatures. So this is an open source part of the HTTP spec now to sign requests between a client and a server. So just take this idea. A client can sign a security-sensitive content of the request. So security-sensitive content being, what's the URL? Like, what are the headers in this request? What's the content? Like a header with a SHA-SUM of the content. Within either an asymmetric or a symmetric key. And then the server can validate that signature applies to that request. And it actually matches for the request. So if I have a post to users and I have even if I have a bearer token, and I put a signature on it, that signature is going to be a signature of the request itself. So because of how hash algorithms work, if you change any of the bits that go into that hash, the hash is not going to match anymore, right? So if I change the URL, if I change any of the headers that are signed into this request, if I change any of the body, the signature is no longer going to match.
And the nice thing about it is that, with TLS, everything, you don't get to choose what is important in this request. Everything is encrypted and kind of, if we would have a case where TLS would go all the way through the middle kind of box, the proxy can't make any decisions on specific headers and stuff like that. Now we get that option, but still read-only.
Right. You can obviously like end-to-end encrypt a system. So this is like used in things like Apple's PCC, where they talk about encrypting a request at the iPhone and then propagating that encrypted request all the way down to like the inference server, and that can have like advantages in terms of privacy, where your middle boxes can't even see the request. But as Lucas just said, like if you do want to do microservices or something where you do want to route parts of the request to a different backend, but you still, so you don't necessarily need encryption all the way through end to end, but you want to do validation of your authenticity of your message, you can do that. So what happens is, if I have a gateway, and even if I can see this request, right, I can see the headers, I can see the signature, I can pass that on all the way back to my backend service, which can do a verification to say, okay, I know, in this case, I know the key for Lucas, and I can verify that this signature was created by his key. Now, if there's any modification of any of the signed headers or the content in the request, it's going to not authenticate. But I can add additional headers that might not be signed, and that will work fine. So if I'm propagating an HTTP request through multiple services, say I have like an Nginx or something as sort of a proxy layer, I can still add other headers. They just can't be signed headers. So that leads to a key distribution problem, classic, right? Like, how do we distribute keys? So this also worth noting that this RFC is in part like pushed by AWS and Amazon, as well as other people in the IETF. And this is somewhat inspired by AWS's Signature version 4 or SigV4, which uses a similar idea of using a secret key, a symmetric secret key, and an HMAC. So this is basically putting your secret plus the content of the request into a hash, and doing that a couple more times on different parts of the request. So hashing, adding, and coming up with a signature. And so what AWS does is very, very similar to this in all the AWS services, where the client, when you're a client of Amazon, you get your access key ID and your secret key, and maybe a session token if you're an IAM role. And when you use an AWS SDK, what that's doing is doing all this HMACking. So it's saying, okay, I have my client secret. I'm going to add that with parts of the request, hash it, add another part of the request, hash it, and then it generates this signed tokens for that specific request. And that token is only valid for that specific request. So that, again, that's just what the AWS client libraries do. And AWS has an internal service, the auth runtime service, or ARS, that does the validation of this. So when you make a request to an AWS service, especially if you're using an IAM role, your session token gets sent to the service, and that's a signed header. That gets passed to ARS by whatever service you're calling. And that token has your secret in it, except it's encrypted. And so the service you're calling calls ARS, gets the decrypted secret key, and now can basically rebuild the hash that you included in your request and validate that, okay, yes, this really is you. That's the magic of AWS SigV4 kind of on the server side.
But the problem here is that still the client has to distribute, well, you get these magic keys, random bytes from an API call, but you still need to get them somehow to the
right,
client.
it's a pre-shared secret. You got your secret access key from AWS. AWS told you what it was. You didn't get to pick what it was.
Yeah. So on a high level, what are some other alternatives, and especially as the formalization of HTTP message signatures supports both symmetric and symmetric keys. Let's take a look at using asymmetric crypto for this. So the application, or the server in our case, well, it trusts an identity provider, and this is, well, you choose, it's your configuration. The idea is that the identity provider will attest the client, so like using, I don't know, username, password, whatever kinds of thing when you log in, maybe MFA. But once that's done, then identity provider has figured out who you are. Well, now we add one step where the client actually will have a key, and now the identity provider associates the key that they have with their identity. So then from the application perspective, because it's trusting the identity provider, it can also trust the key of the client. So there's a couple of ways to do this. This is the normal OIDC flow that we just talked about in a little bit more detail. Actually, there's, well, first you get redirected to the identity provider page, and then they redirect you back. You get a code in the redirect, a one-time use only, that you then do a normal HTTP post request to get the signed token. And then you use a token as you like. But if we add one thing, if now the client actually has a private key, it can be ephemeral, generated in the browser or whatever, non-exportable. Now you do the same thing, you redirect, get back, But then when you post the code, you actually sign a nonce, like a challenge from the server, and using your key. And now we see here that like the token that you get back is actually like has this confirmation claim. So like it says that identity provider, check that you actually do have this private key on your, well, in your browser or in your private memory somewhere, which means that now you can use this when actually doing the HTTP message signatures request. Because then the server will, the application will look at, well, is a token valid? Yes. It will validate it using the, well, orange is here for the identity provider key, green is for the user's key itself. So we'll validate using the orange key, see that, well, this is a known user. Oh, this user has this key. Let me see if that actually checks out with the signature for this specific request. The problem with this is that actually you need to have some support for this protocol. It's also another IETF RFC 9449, but it requires changes support in the OIDC provider itself. So there were some smart people at OpenPubKey that figured that actually we can use a nonce for this, because the client, when you start the login flow, actually get to choose a nonce, so like a value that should only be used once. You add some specific meaning to it and derive the nonce, well, from a random value, but still from a key as well. So now when the application is validating, it can, well, do the same thing. It can recreate the nonce from the data that it has and then see that does it check out or not, i.e. does the user actually have this key or not. So that's a link between the user-provided key and the trust of the identity provider. And well, now we don't need to this work with any OIDC provider because it's by the spec. So this is great. But then, just for fun, GitHub is also a public key database. If you add an authentication token, SSH authentication token, actually it's going to expose your keys here publicly, right? So we thought it would be fun to do a demo with this and actually use, well, GitHub as a key database. And now, like, because both the client trusts GitHub and the server we configure to trust GitHub, actually we can sign some messages and have some fun with this. So yeah, how's the demo going to work?
So yeah, so what we'll do here is basically, if you've already scanned the QR code, oh, it doesn't work? Okay, well, sorry. So we'll have, we have I'll demo it here in a second, but we have a client that, so you log into GitHub and you register your public key with GitHub, and then as a client, you can make a request signed with that public key to our demo server. So it's encrypted with TLS. You get like transportation level security and encryption. But then you also will say, okay, here's my, just say to the server, here's my GitHub username, and then generate a signature including that GitHub username signed. The server will then, well, actually, you'll do it through an Amazon load balancer is the implementation here, which passes it on to our backend server. And that server will look up the keys for this username and then download those and make sure that the key ID specified in the request is one of the keys in GitHub and is actually properly signed. So if you wanted to participate in this, you can generate a new key if you don't want to use one of your existing keys. If you don't trust us to run this client with and passing it your GitHub private keys. We promise we're not hacking your GitHub. But you can run this rejects demo. And I'll do it here in a second. But you'll basically pass it the key to say, here's the key I want to sign the request. Here's my username. And what it will do is actually just spit out a curl command for you to run yourself. So you can see that we're not doing magic, a lot of magic behind the scenes. You can inspect the source code. This is all open source. And then actually execute that curl command. So let's do that really quick. Thanks. So I've got my server here and my client. And what I'm going to do is, let's do, so I've got my go mod. I'm going to go run main, and it failed to work because I didn't give it a file, and we'll see the arguments I have. So I'm going to pass it a key, and that's just going to be SSH, IAD, ECDSA, and then -- username, my GitHub username, and run that. And so this spat out a curl command. So this curl command says, okay, I'm going to make a post to rejekts.dev.micahauser.com/hello. Here's my content type. Here's the signature input. So this is part of the RFC is to specify, okay, tell the server what goes into rebuilding this signature. And that includes things like the method here that I'm specifying, the target URI, so the whole URL, the content type, and this X GitHub username. So if I change any parts of those requests, the signature will change. If I add new headers that are not part of this signature, that's fine. The request still goes through, and the signature doesn't change because those those aren't what goes into the signature. And then I also specify here's the key ID. So it's just a SHA-512 of my public key. And then I have another header for the signature, which actually has that's generated signature, and I throw in my GitHub token. So let's try this. So if I do that, I get back, hello, Mike Hausler. So that worked great, right? Okay,
So it's authenticated, it works.
It's authenticated, it works. But what happens if I go ahead and I change the content type instead of to JSON to YAML with the same credential, right? I'm going to get unauthorized. That's because the server, once it saw my request, is like, oh no, you know what? That signature didn't compute. That's not signed by that key, or that key did not, the signature does not match the bytes put in that were signed by this key.
So this could, for example, represent the case of the ALB being misconfigured or something to set some specific headers that shouldn't be set.
So I've got some pods running in this cluster behind a ingress load balancer. And if I want to get the logs out of this, you can see that, okay, I authenticated successfully as Micah Hausler, but then I had a second request.
Oh, it was even,
Yeah, that wasn't even valid. So if any of you log into this, I'll see, hey, thanks for trying the demo. But that would work with anyone else's GitHub username because it's just taking the signature and validating it against your GitHub keys.
Cool. So what's next? Well, there's a lot of Cloud Native folks here, so I'll talk about how to integrate some of these in the Spiffy. So, well, now we had, for kind of simplicity, gave some examples on, well, SSO, like human clients logging into something using their human identities to access systems. But what is going to be as important, if not even more, is going to be, well, if we have these long chains of like a request hits a gateway, and then we have like 5 services in between before it hits a database. Now, like verifying that actually that request stays same across the whole request path is going to be pretty critical. And this means that like workload to workload authentication and request authenticity is good to have. So Spiffy is well, standard for distributing identities to workloads. The idea is that it's kind of the bottom turtle of all of this, kind of giving the identities to the workload. So when a workload starts up, it's going to ask, like, who am I? What are my identities? Through a gRPC API, which is well known. Then it's going to, well, attest. So then the agent running on that node is going to figure out that, well, who is this workload? What is this workload doing? What identities does it map to? And when it figured that out, it's going to, well, sign and give a, well, X509 cert or a JWT token to the workload, which the workload then can use in different ways to authenticate. But then, so that's normal Spiffy. Now there's another IETF internet draft, so third one of this presentation called WIMSI, so Workload Identity for Multi-System Environments going on. And it's, well, idea there is to kind of add to Spiffy a new type of token. They call it a WIT, Workload Identity Token. The idea is exactly the same as Depop and OpenPub key, in that a workload gets a private key. At the moment, it looks like Spiffy is going to generate the private key and give it to the workload. So Spiffy can kind of control the signing algorithm and stuff like that. But then the workload gets a public key, so a private key. The issuer, so Spiffy, binds the workload identity to the public key in the token that it gives. And then finally, anyone else that is kind of, well, wanting to authenticate this workload is then able to, by trusting Spiffy, look at the token is valid itself. And then when they know the token is valid, then they just get the key there encoded in the token and can then, well, authenticate this HMAC or HTTP message signatures thing as well. So that's it. And yeah, thanks to Evan and Peter from Spiral for answering questions and just making sure this was correct with the current thinking. There's a Spiffy pull request that you can check out for well, more information about what is going on here, and maybe by the next reject we'll have something more concrete. We'll see. Yeah, that's it. Thank you very much.
We've got a little bit of time for questions. Maybe 5 minutes left.
Yeah. No. I'm loud anyway. Give me that one.
Oh, no.
Now it's on. Okay.
Sorry, I've got this one. Anyone got any questions? No? Okay.
This seems to be very clear.
Yeah, very clear. Excellent. Thank you, guys. We're now going for break, and we're back here 4:05. 4:05, thanks.
Thank you. All right. I'm Thilo. I work as a maintainer on Flatcar Container Linux, and Microsoft pays me to work on that and on other open source projects. I'm here today to present a way to deploy and to update Kubernetes in immutable images, which has some advantages that I'm going to demo in this talk. Speaking of demos, this talk consists of demos. There are no slides. It's just 4 demos. So if you came for slides, I'm very sorry. There are no slides. All right, let's dive right in. Thilo, start provisioning the cluster API. Okay, before the first demo, I'll go to the 4th demo, which is the last demo, and I will deploy a larger cluster, 6 nodes, on Azure. It'll be in this resource group later, and we need it as kind of a wrap-up of the whole talk. All right, I'm going to talk to you about system extensions today. First, we will use Kubernetes in all of the examples. In the first 2 examples, Kubernetes is just there. It's not being used. It's there to demonstrate system extensions to you. System extensions ship system extensions in immutable operating system images. They're just a file system image. They can be a whole disk image. We'll be using file system image for the purpose of this talk. And we'll be working with Flatcar because that's what I know best. But you can basically use it on any operating system. It's been in systemd for years now, and it recently gained mutability, which is good for general purpose operating systems. For Flatcar, it doesn't matter because it's an immutable distro. It can deal with immutable images. All right. So in this first configuration, what we're going to do is we're going to run a local VM on this machine. It will pull an extension image from a local web server. That's the name of the extension image, and that is where it's going to put it. There's no magic here. This is the configuration which we're going to pass to the instance. And now, as it is tradition in the cloud native world, we will ritually transpile YAML to JSON. Here we go. And we feed JSON to the instance. Okay, so that's just Flatcar disk image here, which I'm going to boot in QEMU, and I will pass the system extension configuration. Before I do that, I actually need to start the local web server, which we're going to use to serve the system extensions. That's the directory of the web server where we're going to start it. And you see a number of files here. For now, the interesting one is this one. This one will be pulled by the instance at boot time. And this is just a Python wrapper around a local web server. All right. Now, I'm going to start the virtual machine. And I'm using the no graphic option, so we see console output of QEMU right here. I'm also using the snapshot option, which is beneficial for the demo purposes here. And that means that in the actual disk image file that you've seen, no changes will be written. The moment I shut down this virtual machine, all of the changes will be lost. And that's good if you want to provision over and over again. All right, what is a system extension? Now, the file that we told the instance to download is right here. And since it's a file system image, you can just go ahead and mount it, right? Whoops, it's now an MNT. And it's basically, it's your average Linux file system. There's a USR in it, there's a user bin in it, but it only ships the binaries that we want to ship, in this case, Kubernetes. As well as, so if you do it recursively, you'll see that it's really just Kubernetes in there, as well as some lightweight metadata to tell systemd sysext about the compatibility of that particular image. So if we look into that, we'll see that this runs on any distribution because it's statically compiled, right? It does need the x86 architecture, though, because that's what it's compiled for. And this tells the system manager that when I merge the system extension, it has to reload all of the configuration files. And the reason for that is we also ship in the same extension systemd units for the, sorry, for the services to start up. Right? So this starts kubelet, and we want this to apply at merge time so kubelet can start. Let's do it. So first, let's look at the active sysx. There's no Kubernetes in there. We have a number of sysx there. You won't see that on Ubuntu because Flatcar heavily bets on sysx because it's an immutable distro. It's the ideal thing for us, so we ship Docker and Containerd with the default distro as system extensions. And the reason it's not listed there is because we put it at a custom path, opt extensions Kubernetes. That is something we made up. We can make it easily, we can make systemd easily aware of that by creating a symlink. And systemd looks in etc extensions. And now it's aware of Kubernetes, but if we list the active extensions, and that's that command, you only see 3 merge, and the reason for that is it doesn't merge automatically. Before I merge, there's no kubelet, and there are no Kubernetes binaries here. They're not part of the system, but if I refresh, then it'll basically unmerge and remerge the whole stack of system extensions. And now I have Kubernetes binaries in the system, and I can run kubelet -- version. And that is what sysx are. This is how you ship it. This is how you use it. So that's basically the first demo to give you a rough idea what we're actually talking about. Now, I said they come with certain benefits. One of the benefits that you get from system extensions and from shipping immutable images is that you can update very, very easily and entirely independent from the base operating system. The lower half, Flatcar, with the only exception that Kubernetes would be using Containerd on Flatcar in order to run containers and pods, but that's fine since we test that layer extensively, also with a Kubernetes system extension. That is something Kubernetes sysx can rely on. If you want to own the Kubernetes layer in your deployments, that's a good way because you can update it in your own pace, you can ship whatever you need, it's bundled in one single need file, and it updates easily. To kind of validate this claim, let's boot things first, and then well, this is easy. Let's look. Okay, so another boot configuration that we're going to use on the virtual machine. This is a little more complex because we are creating the symlink right away from the start. So the sysx will be merged in the minute that we boot. We also pull a sysupdate configuration, and we instruct systemd sysupdate to handle the Kubernetes sysupdate configuration. We disable the systemd sysupdate timer. And the reason for that is I've not demoed to you, so I don't want it to happen automatically. Now again, our sacrifice to the transpile gods, and we're gonna start it. And then you'll see our little web server here working. And when the instance boots, it just pulls the 3 files it tells it I told it to pull. And when the instance comes up, I'll have kubelet readily available because everything's merged, right? And I can demo the update feature. All right. Now, there's a symlink created for us in etc extensions, and it points to the 31.0 release, to the 31.0 sysx. And there's one sysx in our custom path here, and that one is 130. There's also the sysupdate configuration file, which I provision, and I can, let me check if I need to do anything else. All right, yeah. So Let's make a little bit room here. And now let's kick off the sysupdate service. So this is something that would usually be triggered by a timer service. So you basically have regular polling of systemd sysupdate for any available updates. Zeus. Do I have a type? System, start. Okay. And you'll see it goes and gets the SHA-sums file, and then it figures out there's an update. And the reason for that is, so if you look again, this is the web server that and the directory that we serve. So if you look into that, it basically serves as an index file, and every file listed there is something that sysupdate will be aware of. And if you look at the sysupdate configuration itself, you see that you have this semantic version matching here and the architecture matching right there. And this is something that sysupdate reads, evaluates, and then it goes, fetches the SHA-sum, and it acts accordingly. Now, if we look into the logs for that, then sysupdate is really verbose. Like, it really tells you everything it's doing. And we see, look, I found the SHA-sums file. Look, it's that big. Okay, look, I found version 3. I'm gonna go and download it. And then, oh wow, I'm 1% done. And eventually, it's fully done. And if you check the extension images here, it just put the other extension image there, and it updated the symlink as well, so it's now pointing to the .3 release. And our kubectl version will be, exactly, it's the old version. And that's the old version because we only staged the update. We didn't tell systemd sysupdate yet to activate it, right? And so if you kind of run a larger deployment, this is beneficial because now you can coordinate your updates. I won't. I just do this. And then the new sysx by default applies because the symlink changed, and we will have the new version. But this gives you kind of the wiggle room and the opportunity to organize and orchestrate everything yourself. Now, we have kubelet, not found. Yeah. Now we have updated to 131.3. And again, this is the second demo. We didn't do any semantically Kubernetes here yet. I just used the binaries in the image and the service files to kind of demo how to provision a sysx, start a service that's included, and update the sysx. So let's do something real. Tilo, apply the QD YAML. Yeah, so the actual in-place update on an actual cluster takes ages because you want to be like really, really careful. So we now deployed a large-ish cluster on Azure, large enough for the demo. It's 6 workers and 1 control plane node. It's all neatly there. It's all in this resource group. I use Cluster API for that because it's really comfortable for this kind of demo. And it basically handles all of the creation and the setup and everything for me. And we will now start a reboot manager, install a reboot manager, and that's QD. And again, that will take probably the majority of this talk. So we're not gonna care for the time being. We'll get later. It will not be done. I can even set up this watch here. Sorry. Oops. And it'll be waiting for us when we get to this demo. All right. Okay, now what we can do with the principles of using Kubernetes as immutable image and the flat car being fully configured before we even start provisioning, we can pull up a local Kubernetes cluster really, really easily. Where are my YAML files? Sorry. Oh, I'm in the wrong directory. Local was right. Okay, we're gonna look into that YAML file really, really soon. I just want to start the provisioning. So this is a little more complex. So I'm using a wrapper script for that. And the wrapper script basically runs this. So we're deploying Flatcar with some custom networking stuff. This will be the host networking. This will be a port to the host in order to connect via SSH. But it'll also be like a second network interface that will connect all of the 3 instances I'm going to start via a UDP multicast bus. That's something that QEMU provides, and it's really, really handy in order to pull up a local cluster. Now, this will take some time because kubeadm basically, oh, it's done. Interesting. Wow, the Wi-Fi is great here because it pulls down a lot of stuff. So again, this is things that you've already seen with a few new additions on top. So again, we're using the Kubernetes sysext here, and it's coming from our hard-working little web server there, and it served all of the files. We're installing the sysupdate configuration as well. This here is some static network configuration I used to interconnect all the 3 virtual machines. You don't need that, that's very Flatcar specific. This time we're enabling the sysupdate timer because I already demoed what this part would be doing. And we actually set it to a pretty aggressive schedule. We also instruct kubeadm to boot up and to create a control plane node for us. Lastly, the instructions for sysupdate to handle updates are a little more complex here. And the reason for that is we want to signal to an upper layer that an update has happened and that a refresh of the node is necessary now. I'm going to give you the details in a second. Okay, so now, since we have our control plane node, we can fetch us the kubeconfig from there, which will make things a little handier. We can check how the cluster is doing. And how is the cluster doing? It's not doing really well. Does anybody even know why? What's missing? The CNI is missing. So we didn't provision a CNI, just a bare-bone Kubernetes deployment. And without a CNI, the node does not feel well. So we're going to do that. And that will again take a short amount of time, and that node will then get ready. But we are already in a stage where we can ask kubeadm to generate commands for us that we can use for the worker nodes to join the cluster. So I need this token, and then I can update the worker configuration. This is not something you would do for a production cluster, but it's insanely handy for testing. So you see that I've done this before with other tokens. And you can iterate really fast on this. So now transpile this. Here we go, and the second worker. And so the beauty of the beauty of using QEMU in the snapshot mode is that it never ever touches the image that we're using on disk. So I can run the worker nodes with the same image. So I'm booting 3 nodes from the same operating system image here and use them for ephemerally testing stuff. Right. Now at this point, we can just use kubectl to check how our nodes are doing. I really like the Wi-Fi here. It's super fast, so if they aren't ready yet, they should be ready really soon. Control plane isn't ready. Okay. That's unexpected. It was so fast. So apparently, Calico isn't feeling well. Let's see how Calico is doing. Whoop. It's dying. Image pullback off. Image pullback off? Why? What's image pullback off? It worked an hour ago. Okay, so it's container creating. Is GitHub kicking me here? What's happening? Very interesting. Anyways, oh, the worker is ready. Okay, the control plane hasn't finished yet, but I got a worker ready, which is nice. And so since that worker is probably ready, it will be our first victim. So we're gonna check this, right? Oh, the second worker is ready. Control plane is still suffering, but hey, here we are. Anyways, and I do the bad thing now, the thing you don't want to do in production. I will do a node refresh. And then you'll see that this node will in-place update from 131.0 to eventually 131.3, right there, in-place update of Kubernetes. Why did it in-place update? And we can check the second worker to find out. We didn't update that one yet, right? So that one is still on 131.0, but the new version already has been downloaded because we told system users update to do everything automatically, and system users update also did this thing where it just created in the post update script, after an update actually happened, it created that file for us. Now, we've been watching for that file. We're being the reboot orchestrator here, and we see that file, and oh, this node needs a reboot. Right? So it's going to get a reboot. And it'll come up with version 3 as the control plane is still suffering. I don't understand it, but I'm not going to ask any questions here. I'm just happy the workers are happy. So, all right. So this is in-place updating your Kubernetes cluster the way you shouldn't do it for 2 reasons. You don't want to log in on your nodes and type stuff. That's like the antithesis of Kubernetes. And second, you don't cold reboot your nodes like that because you know these have workloads, and these workloads might be disrupted by this. So how do you actually do it? Well, you use a reboot orchestrator. A reboot orchestrator basically does what I just did, but in a much nicer way. It just watches this file. If the file exists, it will slowly and customizably evacuate that node, get all pods into safety, only then reboot the node, and then when the node comes back, it'll uncoordinate, and it'll rejoin the cluster. And as you see here, this is working hard on the Azure cluster. So it's updating to a newer version, 2.9. The reason for that is Azure doesn't use my private web server here. It actually uses the repository we have in the internet for updating stuff. And it will nicely chew node by node by node through your cluster and bring everything on the latest state. And one of the large benefits I didn't automate that, but I mean, it's easy to picture, right? Of using system extensions here instead of like any other traditional way of deploying Kubernetes is a rollback. It's just one symlink away. Like, you change the symlink again, you either re-merge if you don't have any pods because they don't like the new version, or you reboot, and then you can automate it in the very same way, and you've rolled back to a known good version of Kubernetes. And that is why I really like systemd sysx. I don't get the, anyways, this updates. This is slowly updating, and if you check out the, here we go. If you check out the QD configuration, so this is all of the options that you can use to customize Kubernetes. You can basically use annotations. You can slice and dice the update process in any way you want. You can even have webhooks or Slack messages being posted by the update manager to kind of keep you up to date. And you can, of course, exclude nodes entirely. Like if you don't want to update your control plane node automatically, you can do that. You just exclude them from the update. It's something that we use. We actually also maintain our very own update operator for Flatcar clusters, and that's called Fluo, the Flatcar Linux update operator. It's kind of like QD. It's less flexible. It's more specific. But you have more options if you already work with Flatcar. I'm showing QD here because I want to get you interested in sysx and not in Flatcar, and because it's very, very useful for a lot of other cases as well. So this is how you in place update your Kubernetes cluster. Any questions?
Thank you. Yeah, many questions, at least two. How is it with integration with MetalCube of Flatcar? I noticed it was discussed some time ago. There are some requirements which needs to be done to integrate Flatcar into the MetalCube control plane handling during the upgrades. Do you have any update on that?
That was like quite a long time ago, back in the day when we didn't like fully embrace system extensions, and by now we're doing everything with sysx. Like all of the cluster API providers that we support, they use sysx for flexibility. They don't really in-place update yet because KubeCon can't do that yet. There's work in progress, but it might be worth like to rekindle that discussion. I know we looked into a number of those operators and environments, and I mean, in general, as a project, we're always happy to cooperate and to accept patches. I'm not aware of any maintainer currently working on it, but if it's desirable for users, Flatcar is a very use case-driven project. Like if people want that and need that, we're gonna do it.
Yeah, I'm not particularly asking about in-place upgrades, but the general those.
Yeah, no, I know. That's what I'm saying. If people are interested in using that provider and that environment, then in general we are open to investigate and how to adopt that.
Are you aware already of people using Flatcar with MetalCube deployments with CAPI? I mean, Cluster API, MetalCube infrastructure provider.
I'm not sure, but if you're talking cluster API specifically, it's insanely easy nowadays to add Flatcar. The ignition provider is there in cluster API upstream, and using Flatcar is way less of an effort than like using traditional operating systems because you don't need to build any images. You use the stock image, and you just have a cluster API template. And then everything's there, and it uses basically this mechanism that I just demonstrated for pulling up Kubernetes. I mean, in fact, the cluster API cluster that I launched on Azure, this is fully it's a full stack of sysx. There are no pre-built images that contain Kubernetes bits. It's all composed at provisioning time.
Okay, thank you.
Welcome.
Anyone else got a question?
Yeah, thank you for the talk. Does it work with other Kubernetes distributions like K0s or anything else? Like
I'm
you
glad you asked.
So KubeADM.
There's this thing we operate called the SysX Bakery. It has a lot more system extensions here than just Kubernetes. And we have K3S and RKE2 here as well. So these are already basically readily available as system extensions, and you can just consume them from the bakery. If you check this out, like if you go into the, you mentioned K3S, right? Okay, if you check this out, you get a ready-made configuration snippet. You just go to extensions.flatcar.org or to the SysX Bakery in the Flatcar GitHub project. The two are the same thing. And you'll get examples and everything that you need in order to get up and running.
And if I want to add something myself, I can just start from here. Because you have the K3S, but if I want, for example, the K0S from Mirantis,
the bakery is very laissez-faire with accepting PRs. Like we have a lot of stuff in there we're not using ourselves. Our users want that on Flatcar. Like someone crazy actually did a static build of Keep Alive D in an Alpine container and automated all of that, and it's in the bakery, and the SysX is right there. You should go there and grab it. So we're very happy about PRs, and it's self-updating. So if there's a new upstream version available of K0S, then it will automatically build the SysX and host it at the bakery.
Okay, we're out of time. Thanks very much.
Thanks, Fox.
Awesome. Next talk is up in 3 minutes' time. And we've got Nick talking. Yay, perfect.
Okay, time for the next talk. We've got Nick. He's going to give us an autoscaling party.
All right, thank you very much. Very excited to be here. Only have 30 minutes, so I'm going to have to go fast. I mean, not too fast. So the goal of today is to understand a bit better how VPA, HPA, KEDA works. I'm not going to talk too much about nodes. Actually, I'm not going to talk about cluster autoscaler. But I mean, basically for nodes, you have cluster autoscaler, Carpenter. Use Carpenter, it's better. Job done, all right? So it will also be based on a demo, like a Rube Goldberg machine, and the goal is going to be to break my application. But before that, I'm going to have to be able to understand what's going on, I'm going to have to talk about requests, limits, quality of service, priority class. So who is familiar a little bit with that already? Some of you? Okay. It's kind of confusing, so I'm going to use a couple of metaphor and images to be able to explain that. Let's aim for maybe 10, 15 minutes, and then we'll try to break the application where we'll see everything in action. So my name is Nick. I've been doing Kubernetes stuff for probably the last 8 years around CNI, CSI, edge security. Usually I'm either in DevRel, engineering, or product management. I've been in this industry for 25 years, getting old, but yeah, it's just experience, right? Yeah, I enjoy coding fun apps, usually like Rube Goldberg machine, overkill application. This is my thing, I love to do that. I'm also an avid distance runner, and probably the best way to connect with me is either LinkedIn, but probably Strava, where I'm probably the most active. All right, so why do we need to do autoscaling? Well, because simply, a lot of resources are wasted in the cloud, so it makes sense not only to scale up, but to be able to scale down, and having a good, good idea of what is running in our cluster. But at the same time, we have to right-size everything, and to have, elasticity is probably one of the most important aspects. So according to one report from Akamai 2017, like 100 millisecond delay is 1% decrease in sales, right? So we have to make sure that our infrastructure can handle performance application. But unfortunately, HPA, VPA, KEDA, autoscaling, there's a lot of notion to be explained there, and there's a lot of knobs. So like Homer, you can be very confused because of all these knobs. So there's a metaphor I like to take, is a kitchen metaphor, to be able to make distinction between VPA, HPA, and KEDA. So let's start with the kitchen, right? So the kitchen is basically our cluster. So we're not going to scale the kitchen today. And then we have the orders. Orders will be our containers, and the orders are made of ingredients. And ingredients are themselves resources, or the metrics associated with the resources. And our scalers are, the pod is essentially the chef, right? Or a group of chefs. And this is the resource that we need to scale. So if we make this comparison, we can first talk about VPA, so vertical scaling, which is essentially you have, for one particular chef, you give it much more power. It can do a lot of things with the ingredients. It has more tools. And the idea inside Kubernetes for the VPA is to recommend requests for your workloads, right? So typically, you start with VPA just at least to have an idea for profiling your application. This is the basis to profile your application. Then you can, of course, enforce those requests, which we're going to see later. And then we have HPA. So HPA is kind of, by default, quite dumb. The ingredients are exactly the same, typically CPU memory, and you just scales based on that, right? So it's not super intelligent. You can customize it. We're going to see how to do it. But if you really want to customize HPA, then there is the smart guy, right, which is much more lean. KEDA is acting as a chef, as a proxy. So you have the chef of all the chefs. And KEDA will give you those special ingredients, or different kitchen. Maybe you're going to eat, you're in London, so probably it's a good idea to eat Indian here. So it's acting as a proxy on top of HPA to have specialized chefs, right? So essentially, it's making HPA much more intelligent. We're going to see this in detail. But before going into those details, we have to understand the notion of requests, limits, and quality of service. Essentially, I mean, mainly requests, because request is going to be the special metrics that is going to be used by all the scalers. So if you say the trigger is going to be 50% or 60% of my resources to scale, this is going to be based on the requests, which means that request typically needs to be as much as possible as close as the profile of your application. So if your application is consuming 100 millicore of a CPU, that needs to be the value as an average. Same for memory. You have to know your application, how it's behaving. And then, of course, the request itself guarantee, it's the amount of resource guarantee in case of contention. So it's really the minimum. And it's also informed the scheduler for placement decisions. So if the request you want to allocate to a pod is not available on the host, then the host, that particular node, is not going to be considered for placement. So it's also very important. So if it's too low, well, pods might be scheduled on stray nodes, which is not good. If it's too high, you can waste a lot of resources. And as I said, the good practice, the request should be aligned closely with the actual usage. And as I said in the beginning, you can start just using VPA just to profile your application. So limits, it's the resource boundary. It has a couple of effects. So usually you can, if you look at Reddit or some documentation, it's not necessarily recommended to apply limit on CPU, just because if you apply limit on CPU and you go above that, you will have CPU throttling, as opposed to if you don't put any limits and if the node doesn't have enough cycle, then your pod, the task in the pod, is going to be scheduled less on that CPU. And there's quite often a confusion. If it's scheduled less, it doesn't mean it's throttle, right? These are two different things. So remember, limit equals CPU throttling. If you don't put any limit and there is a contention for CPU, it just means that the task or the pod is going to be scheduled less often. And of course, memory limits, this one is quite bad because, if the pod goes above that limit, whether there's contention or not, then it's going to be OM killed by the kernel, right? Okay, now quality of service is determined by those two resources. There are three classes: guaranteed, burstable, and best effort. And these three classes determine the eviction priority under resource pressure. So a node resource pressure, the typical two ones, there's no such thing as node pressure for CPU. Maybe for PIDs, but not for CPU. Typically, you will experience node pressure for disk and node pressure for memory. Those are the main two conditions. But here, remember, guarantee, burstable, and best effort, which is the metrics that is going to be considered, are related to request and limits for CPU and memory, right? So those are kind of disjoint, right? So guarantee is deemed for pods where requests equal limits, and that will be the last considered to be for eviction, with the little kind of tricks where if you only put limits on a pod without any interaction with other webhooks or admission controllers, if nothing is modified, then so Kubernetes is going to copy the value of the limit into the request. So basically, if you only set limits for pods, you're going to end up with guaranteed workloads because it's going to copy the value of the limit into the request. Therefore, they are equal. For other scenario where, actually it's the opposite. I just realized so limits is superior to request and not request superior to limits. Those are deemed burstable. So typically, this is most of the time what you're going to end up with. And there's also other scenario. For example, if you omit one request for CPU and only have memory, then it's going to be burstable. It's basically everything else, except when nothing is defined. In that case, it's going to be best effort, right? So I think I will have a table later. With that particular gotcha that's if you apply CPU limits, like I said before, CPU throttle can happen. Therefore, if you define a trigger that is too close. So if you say request equal limit, remember what I said at the beginning, then it's a percentage not of what is used by the pod, it's a percentage of the request, right? So if the percentage for the trigger, let's say 90%, is too close to the limit, and if limit for CPU equal request, it means that probably the CPU will be throttled before the triggers happen, right? So there's a kind of gotcha here, so be sure that when you want to monitor for CPU scaling, put the trigger not that high so that CPU is not throttled, or just don't put any limit on the CPU. But again, if you don't put limit on the CPU, your workloads move from guaranteed to burstable, right? Which is then again, in terms of eviction, priority may change. All right, so these are three, oh, I need to go fast. So three scenarios. Requests, we have a use case here, 100 mil CPU, 200 mil memory, or not defined at all. In that case, if we also have limit defined, Kubernetes is going to copy the limit into the request, if the request is not defined. Or if they are equal, it's guaranteed. So this is falling into that particular area. Then for basically anything else, so when you are missing one request for CPU or memory or limits, or a mix of requests being inferior to limits, so basically not equal, it will be burstable. So anything that is not equal, where CPU and memory limits equal request, anything that is not that will fall into burstable, and the rest, meaning that nothing is defined at all, is going to be best effort, which you really want to avoid because they are considered first to be evicted. I'm not going to talk too much about priority class here, but just be aware that there is a completely orthogonal mechanism, which is priority class, that is only evaluated for scheduling, that can also preempt, which means that it can evict pods if you do it. I mean, don't necessarily enable that option, so you can just say, don't evict pod, just use priority class at scheduling without evicting. And the priority class, you can think about it once the scheduler is going to consider, once kubelet is going to consider the different quality of service for eviction, so first best effort, burstable, guaranteed, you can establish order within those quality of service by using priority class. So the recommendation here, without going too much into details, if you have workloads you manage with HPA or VPA, therefore probably going into the burstable, if you don't want to set the limit on the CPU, right, it's going to be burstable. Always make sure that you have a priority class that is high for those workloads, right? Okay, so VPA. I'm just showing here some configuration. Essentially, it has three modes, initial, off, or auto. Initial is great for, is going to generate recommendation, but not doing anything else. So more like for profiling. Off, which just run into dry mode. Auto recreate, then you can have, this is where it's going to restart the pods to apply requests and limits because you have to restart the pods to do it. You cannot do it live, right? So if it's a stateful set, you have to have extra care, and of course you can also plan for a pod disruption budget, which is guaranteeing a minimum of pods for a particular workload, which is the recommendation. If you're using VPA, essentially make sure to go initial, or if you want auto, make sure to have PDB configured. Then you can monitor memory or CPU. Typically, you want HPA working on CPU because CPU is actually representing a value that will have a direct impact on the number of pods rather than memory. Memory is like a watermark, so it's more difficult to use HPA for that. So the idea, use memory for VPA and use CPU for HPA. It's not, I would say, most of the time it's going to be that, but depending on your environment and the type of workloads, it can be other things. But usually, memory, VPA, CPU, HPA. So three main components, the recommender that is going to monitor the resource usage metrics, either using kubelet and cAdvisor, or the metric server, if it's available, and store the recommendation in the custom resource, which we're going to see. The updater's job is just to evict the pod. It's only active in the auto mode. And of course, as I said, if you have PDB, which is best, it's going to respect PDB. And then the admission controller, it's basically using a webhook to intercept the pod at creation time and modify on the fly the request for CPU and memory if you control both. Okay, so this is whatever, I mean, I've also already mentioned all of that. The only thing I didn't mention is configure max allowed, which is basically telling VPA never go above that particular threshold. For HPA, so you give essentially a minimum number of replica, maximum number of replica, and then again, average utilization in percentage in that particular example for CPU, but remember, it's not percentage of memory used, or CPU used, sorry, it's the percentage of the requests that you have defined for that particular workload, right? There's a big difference in this. How does it work? So we say number of desired replica is just basically number of currents times the current metric value divided by the desired metric value. So here I just have an example. If you have currently 90% CPU use, I mean, from your request, 50% desired targets, one replica, it's 1 times 90 divided by 50. Ceiling of that is 2, so it's going to move to 2 replicas, right? So it's a constant formula. So for HPA to work, you need the metrics server to be there. And you can also implement custom metrics through Prometheus adapter, but you have to do it yourself, right? And register that to the custom metrics API endpoint. But if you're smart and don't want to work for nothing, if you really need to do that, just use KEDA, right? So essentially, HPA use metric server, which is installed in 2 minutes. And HPA is, by the way, it's already there inside Kubernetes. You don't need like a special operator, right? But if you want to do smarter things than CPU and memory, use KEDA. And HPA cannot scale to 0. KEDA will give you that particular capability to scale to 0. And KEDA is going to automate the creation of HPA, implementing external metrics. So KEDA, instead of having Prometheus adapter register on the external metrics, is going to use its own object, which is called a scalar, and that particular scalar, which represents a set of metrics, is going to be available on this particular external API endpoint, and then HPA can just leverage that, right? So KEDA is going to implement all of the intelligence into, and register that into the external API, and HPA will just base the scaling on that, right? But we're going to see in the demo. So it's all I said. It acts as a metric server. So think about KEDA really as a proxy, intelligent proxy for HPA to operate. So you define a scaled object in Kubernetes, and that CRD will essentially influence and automate HPA custom resource. So it's the combination of both. It's really automation. We have the super chef, the proxy, which is the scale object, and we have the dumb chef, which is the HPA object inside Kubernetes. Right, so here we have an example. It's Kafka. In the demo, we're going to do use NATS. So here you can see the scale target reference, which is the name of the object to be auto-scaled. So here a Kafka consumer. You give the trigger, and then the metadata is going to be all the parameters for the metrics to be able to be gathered by KEDA. So here we need the address of Kafka, the consumer group, and topic. And then because we expose directly this into the metrics, HPA can directly access that without having to use a Prometheus adapter that you have to customly deploy for if you were using HPA only. Okay. All right, this is a bit of anti-patterns. Essentially, I've already mentioned this. If you set CPU limits equal request, the risk is that you're going to have performance throttle before HPA can scale. HPA with low requests, then we can trigger too easily because it's a percentage of that request. HPA and VPA on the same workload but on the same resource, CPU memory, doesn't work. You can use same workload but different metrics that work. Not using PDB with VPA, it's bad, so always use PDB. to make sure that, especially if it's a stateful workload, so that you don't run into this issue where you don't have enough workloads for serving your application. And priority class. Priority class is very important, especially if you don't set limits, because those workloads, again, instead of being guaranteed, they fall into those particular burstable class. Okay, let's go for the demo. So again, if you have a laptop, it's the moment to use it, or your phone. So if you can scan that, or just use the URL, it's ngrok, so it's running on my laptop. So the idea, it's a meme generator with a front end. That front end is, actually, I'm just going to wait for a couple of seconds. How much time do I have? 10 minutes? 10 minutes. So probably no questions. All right, so the idea is to make the environment scale by using a meme generator. So it's a, let's say we have multiple components. So we have the front end, the React front end that you see on your device that is requesting when you enter, whatever prompt in the application is going to send a meme request on the NATs. So we have a dedicated subject for that, so meme request. So from the NATs TypeScript code, we send a request to the meme request subject into, I'm using Jetstream for NATs because it's persistent and actually support WebSocket. So we have a WebSocket connecting to the stream. Then we have a backend written in Rust that is going to process that particular meme request, so subscribing to that particular subject. And then we have a Redis cache that is going to cache all the different memes that are rendered. And the goal of the backend in Rust is to process the meme request using the Hugging Face inference API, using Flux text-to-image. And once Rust is managing that request, it's going to reply back to another subject that is meme response, and then it's going to be displayed into the front end. So we have different things to scale. First, we have the front end, but the front end is behind an ingress controller. So actually, we're going to scale not the front end, but the ingress controller, because this is the one that's going to handle all the requests from the front end. Then we want to scale the backend based on the number of pending messages into the Jetstream stream. And finally, we're going to scale vertically the Redis cache based on the number of memes that are going to be cached. Right? So let's move to that. And if you don't manage to do it, which probably I don't think there's enough people, but we'll see. I have a bunch of script. But let's go to this whole idea of, so hopefully everyone now kind of have this image of the application. We have the front end, we have the message bus, we have Rust, and we have Redis, and we have the API. So here the application is deployed. Actually, there's already a front end, so probably you've generated already. That's good. I didn't expect that. I thought the ingress would be scaled first. Well, that's good. So we already have the HPA. So HPA definition, so just to show you, we have the namespace meme generator here. So this is our front end. Now we have 2, 4, 6 replicas. And they have just been, because you were guys using it, it scaled from 1 to that number. And we have the backend. So the backend is just 1. If we check at what we have in terms of HPA configuration, this is the front-end configuration. If you go into the YAML version, if we go to the definition, so we have here target usage. Average utilization is 30% for the CPU, 50% for memory. And here I've got some policies that have been applied. So the period second when it's going to monitor before scaling down. And we have the same thing for the scale up. And the value is how much. So 100% means that, for example, here, you will scale up by 100% of the current number of pods. So if I have 5 pods, if I put 100% there, next time it's going to scale, it's going to be 10 pods, right? Scale down, same sort of principle. 50% means that after 60% of where I'm going to be watching that's how much it's used, then 50% is going to mean that you can reduce the number of replicas by not more than 50% of the running replicas. So if you have 10, it's going to reduce it by 50%, so only by 5, right? So that's for HPA. So if we take a look at the VPA configuration, here the ID, 5 minutes, okay. I've put it on auto, but because I have a stateful set, it's not going to restart the pod for me. So this is my VPA configuration, so minimum allowed, so it won't recommend anything below that. Maximum allowed, it's not going to recommend anything above that, and it's going to monitor both CPU and memory. So this is for Redis. So if I look into Redis right now, if I go to pods, Redis, if I go into YAML, and then if I check the resources, so it's the one I've done at the beginning from when I deployed the application. Request 100 mil for CPU, 512 for memory. So now what I can do for my pod, Redis, I can go into, I need to run my Redis. So that will be Redis 6379. And now I can probably run something like Redis cache, benchmark. So I'm going to stress Redis for memory. So Redis is memory bound. So here what I want to do is, oh, did I deploy the VPA? I'm not even sure. Let's try to do this. VPA, I don't have the vertical pod autoscaler. So let's deploy this. So we're going to do kubectl apply, not this one. So apply. That's Redis and VPA. Here you go. VPA. If I just check the YAML, 3 minutes, my God. Okay, we have to go fast. Let's run that. So hopefully we should see CPU and memory appear here. Yeah, so this is now the recommended values, right? And now what I can do is just restart Redis because it's a stateful set. I'm just going to restart it. And I should see the container popping again with the appropriate. Now if I go to resources again, right, I can see that the memory request has changed, so job done. So we've done VPA. I mean, VPA worked for the front end, so I won't show you for the ingress. Now the last part is the message bus. So remember, we have this namespace meme generator. So I want to scale the meme generator backend, which is that one, by stressing NATs. So I'm going to send a lot of requests using the Hugging Face. And normally, if I check also, it's going to be here. I've got all the Grafana dashboard coming from my Rust backend. It's going to spike, you can see here. So not that much Hugging Face, so I should have like a lot of more 1,000. Okay, still $0. I don't want to kind of stress it too much, but I've got room for that. Okay, so you can see now the KEDA, the scale object. I'm just going to show you very quickly. Scale object is defined here. It's active, and how I've configured it is basically it's going to monitor that particular external metrics. So remember what I said at the beginning, KEDA is this kind of proxy. So KEDA is going to tell HPA, monitor that external metrics that I've implemented for you. And if I go into, 1 minute, if I go into HPA now, I will see the backend scaler programmed by KEDA, and if I look into it, I will see that here, the metrics it's using is the one provided by KEDA without having me to create a manual adapter using Prometheus. And because it was quite on purpose, I make it quite aggressive in terms of the metrics. Now that I've served all those messages, I have 0 message in the queue, so it's scaling back to the minimum, which is 1, but I could also have made it 0, but then with 0, there's always a bit of, especially because it's a Rust backend, a little bit of, cold start, which I didn't want to happen. It worked. I was a bit fast. All right, so I think we are over. So just if we want to remind something and get something out of that particular talk, use VPA to scale memory. Use KEDA HPA for CPU scaling. Use KEDA if you want to be smart and not scale based on CPU and memory. Set requests and limits for memory. Set requests for CPU with no limits. If you do that, remember of the priority class, because it's then is moving into this burstable instead of guaranteed quality of service. If you need scaling to 0, again, KEDA is a good solution for that. And the final thing is really use VPA, at least by default, without doing nothing, in initial mode, so at least you have the right profiling for your application. And I think that's me done. All right. I think we're out of that. Thank you.
Do you have time for maybe 2 questions?
Oh, okay.
Maybe 2? Anyone got a question?
So did you guys understood everything, or it was the opposite?
They're all shy. Excellent. Okay, thanks. We'll be back in about Okay, let's get started with the next one. And shout out to the live stream. We haven't mentioned that really much today at all, so hello. It will be live streamed tomorrow. Yay! Yeah, it's on YouTube, so check out there. Right, Emma, over to you.
You hear me? Yeah, that's good. Now it's working. So thanks for joining the session. I'm very honored to be here. This is a talk that's very dear to my heart about how survivorship bias can affect us women in tech, especially in cloud native. I'm Emma Biles. I'm a staff developer advocate at Grafana Labs. So I'm also a passionate community builder. This is what to expect from this presentation. We'll have some stats about the landscape of women in tech and in cloud native. What are the barriers of entry and retention? What is survivorship bias for the ones who don't know? And how intersectionality and survivorship bias can interact, and how to build diverse and inclusive communities. So this is actually the first stats that surprised me, because from experience, I know that a lot of women around 30, 35 leave tech, but and most of them also go into management and leave technical jobs. And I actually found some stats that say that 50% of women who take a tech role actually leave at the age of 35, 45% more than men, and 20% more than in other jobs. So something was going on. I didn't understand this because I've been in tech for more than 25 years, so I did not understand why. So in Cloud Native, it's very difficult to find some stats, but there is a World Economy survey, I think, that says that in cloud, it's only 14% of women. So compared to engineering, where we have 20% of the workforce, and in AI, it seems we have a little bit more, 32%. So I guess this is even probably worse in Cloud Native. And also trying to find stats on KubeCon and CloudNativeCon. What we see is that we actually have a lot of representation in women speakers, but if you look at attendees, when I'm in the halls of a KubeCon, I don't see a lot of women. So these stats probably show that there's not a lot of women attending. Even if we have enough representation probably in speakers, we don't have women attending, and that's something also I did not understand because I usually attend. So what are the barriers of entry and retention? I guess mostly what we see in tech, there's a pay gap. Women usually we get paid more for the same roles. There's a lack of opportunities sometimes for women. There's the environment sometimes is not as safe as we would like it to be. So there's a lot of issues that can be actually a barrier for entry and retention that we have experienced ourselves. And this comes from usually what I hear, because I'm an organizer in one of the conferences we have in a community in Barcelona. And we used to be like 50% of women in the organization, and now it's none, it's all men. I'm leaving this year. And when I talk to people in the organization, why don't you have women? They say, oh, this is a meritocracy. If they don't join, it's because they don't want to join. We are not preventing them from joining. So I find this is a very interesting way of understanding that the system is not the right one. I mean, for some people, even if we give them the right tools, like give them the same ladder, if the system is skewed, it doesn't help. Even if we change the tools and we address this inequality, it's not always enough. I mean, we have to create a system that is just, that you know that the tree now is straight. So this is what we have to do, I think. So we need to focus on this systemic justice to fix these issues. So this is, I've asked some of my friends about how they feel in tech. For example, I have a friend of mine who says that she changed the GitHub profile so that it would look neutral, and that helped. So instead of having a profile that says I'm a woman, she changed it to a neutral profile, and that helped. Or other things that can happen is that you feel that you are the only woman in the room. And it can feel exhausting because you don't feel identified, or you can feel that if you speak up, people will say, they will not trust you, that you think that you're making a mistake. So it doesn't help that we don't feel that we have this support, and it's not a safe space for us sometimes. So I don't know, who knows what survivorship bias is? Have you heard of that? 1, 2, not a lot of many people. So when thinking about that, I was thinking of myself, because I survived in tech, and I was thinking, why did I survive and other women did not survive? And I found this concept of survivorship bias, which is in World War II. What they did is they analyzed the aircrafts that made it to base, that survived. And they were thinking, we need to improve the aircrafts, we need to protect them somewhere, so more aircrafts get back to base. And the first thing they thought is, okay, we're going to protect the places where the airplanes that get it to base got shot. But actually, if you think of it, the pilot that is in there, in the cabin, is not protected. So probably if we shot the pilot, the aircraft goes down. So what they end up seeing is that they needed to protect the places where the aircrafts that did not get to base were actually shot. So for example, if the pilot is shot, the airplane goes down. So this is a little bit of the same. The concept applied to many things. If we're looking at a data set that it's not complete, we're only looking at the survivors. When we analyze what we need to do to get more people to join and stay in tech, we might be missing the women that did not make it and why they did not make it. So it's the same thing. We need to analyze not only the survivors, but most especially the ones that don't survive or leave tech. And for me, that was difficult because, of course, I survived, and it was very difficult to think, how do I know when I'm doing something, like when I decide to help in a way, if this is the right way, because I'm focused on my own experience. I'm an engineer. I have certain privileges. So for me, what helped a lot was recognizing intersectionality. Of course, I'm a woman. But intersectionality acknowledges that individuals have multiple overlapping social identities. And this wheel is very useful for me because it's a framework that allows me to see what are my privileges and what are not my privileges. So the closer you are to the center, the more privileges you have. So some social identities that we have apart from gender, it's race, it's the class, it's studies that you have, it's how advanced you are in your career. You can be starting, you can be mid-career. So for me, this is a framework that actually helps me a lot when I try to decide if I'm doing something that will help these women that don't join or don't stay in tech, if this is going to help. For example, this is my case, no? I could be staying saying, oh, I survived, so anyone can survive. But of course, I have a lot of privileges. Maybe I'm a woman, but I'm an engineer, I'm a citizen, I'm not a migrant, I'm a white European, I don't have children or family to take care of, so there's a lot of things that actually help me. And when I look at other women who survived my age, a lot of them have similar characteristics. So they have an engineering degree, they don't have children, so they are not migrants. So all things were like that. So that's actually something I find very useful. And it changed a little bit how I was helping. For example, I was mentoring women who had studied at the same university as me, had the same engineering degree. And then I decided to change that and say, hey, maybe I need to help women who don't have an engineering degree and who are migrants, because this is a very different case. So probably I can help more if I do that than if I mentor women who have the same privileges I have. Of course, they still have discrimination, but the amount of discrimination they have is way less. So finally, why do we want to build diverse and inclusive communities? So, you know, we all know that probably. Diversity is inviting different people to contribute. And inclusion is making sure that it's a safe space and they feel welcome there. So always keeping systemic justice in mind, if you recall the image you had before, because this is what we need to work on. Why? Because, of course, the communities will be more sustainable. Innovation, we know, is better if the teams are diverse, we'll build better software. So all of this is a thing that we can work on. These are concrete things I think we can work on. There's a lot more that we can suggest. For example, for me as a survivor, I always went to conferences. I didn't care. I felt, even if it was not maybe the safest space for me, or I didn't feel recognized because it was all guys usually, I didn't care. But I know that if we have a code of conduct, even if I never needed it, it helps. So now what I think of when I organize a conference or a community is to make very clear that we have a code of conduct, how you can report this code of conduct, because it's important. And I find this video from Lian Li very interesting because she says things like, at a conference, if you want to really enforce a code of conduct, don't just have a code of conduct and reach out to that person. If that person is not a dedicated person to the code of conduct, the problem is that person is doing catering or is doing registration as well. If someone goes there to report something, that person is busy. So it might just not be reported. So it's important to have, for example, a dedicated team, to have them trained so they know what they have to do in case something happens. So I think that, for example, she gives a lot of very interesting pointers. And there's a training and some scenarios that I think are very interesting to have a look at. Other important thing for me, again, as a survivor, I didn't feel that I needed inclusive language to survive in tech. But of course, after 25 years, I recognize it's important. Using gender-neutral language, like when people say guys, I don't feel identified with guys. I'm a woman. Use the correct pronouns from everyone. Be sensitive to cultural differences, because now, like 6 years ago, I started working at a multinational company. We have people in different countries. And actually, then I learned, hey, different countries have different culture, and you cannot not expect the same thing from everyone. And if you look at intersectionality, you'll recognize there are loaded words. Like for me, blacklist is not a problem, but it might trigger someone who is black. So we can try to change these words. So there's a lot, if you go to this URL, you'll find a lot of words that we can change. Of course, as a survivor, I can say, hey, I survived, why do we need to change that? People can actually just ignore that. But it's not like that. It's not about how do you feel, it's how the other person feels. So it's not about you, it's about the others. So if we are empathic with people, that actually helps. Another thing that we do a lot is feedback. I see a lot of pull requests that actually say, that's why actually my friend changed her profile on GitHub. Because we get like, sometimes after a pull request, we get a, this is wrong, yeah, but this is not correct feedback. We need to explain what would you change? Why do you consider this is wrong? So if we take that into account, giving correct feedback is a good thing that we need to learn. And we need to create this psychological safety where everyone is able to ask stupid questions if it's necessary. Stupid question can lead to a very interesting point at some point. So we need to create this safe space where everyone can ask anything and everyone feels welcome. And working at Grafana, we actually use the culture map when we start, and it's very interesting because it shows you how different cultures understand things differently. So for example, in my country, I gain trust by knowing you, by having coffee with you, by going to lunch with you, but my manager is from the US, and he's more task-oriented. So he trusts you once he can see that you do the task that he assigned to you correctly. So knowing the differences is also important when we deal with people, because they have different cultures and that can have different contexts. And of course, again, mentoring. I never had a mentor, but that doesn't mean it's not necessary. So again, I think if you come from a survivorship with the survivorship bias, it's like, well, I survived without a mentor, but it's important to have someone that can actually be with you, make it easy for you, especially if it's someone you recognize yourself with. For example, if you're a woman, having a woman mentor you, it really helps because, well, we have something in common for sure. So I would recommend going to these links. There's a group of women in Cloud Native. There's resources for mentorship in open source. And I think tomorrow a lot of speakers will share this slide because one of the tasks at the CNCF is starting to offer mentorship, and they are looking for mentors. So the more diverse mentors they have, the better. So I really, I will apply for that. I will offer to help, and I really encourage you to help them as well. And to take home, as I was saying, work with empathy. I mean, talk to people that have different experiences. For me, for example, I don't have children. I talk to women that have children, and men also. Why don't you go to a conference? Well, because I have kids and I don't have a childcare service. So you can actually, if you can, in your conference, add childcare services. So if you listen to other people's experiences, you might learn what are the barriers for them that maybe you don't experience. So the one thing I try to do now is listen to migrant women, to what are the problems that you face and how can we help? Because otherwise I just think, no, for me everything works. I used to work, for example, I wasn't able to bring myself to work when I was younger. I used to work with guys, so they always talk of football. So I ended up learning a lot about football. I don't care about football at all. I was an expert. Every Sunday I was listening to the radio, and on Monday I could go to coffee with them and feel one of the team. So we need to change that. So you have to be able to bring yourself to the communities, to work, and be yourself. So that's one thing I think if we listen to other people, it's easier to achieve that, and people will feel more comfortable. I also have another anecdote here that's very interesting. Like maybe 20 years ago, I was working in a team of all guys, like 20 guys, and I was talking to a friend of mine from university, and I was like, well, you know, in my team, we are all guys. And she said, no, that's not true. I was like super angry. How do you know this is not true? I work there and you don't. Because you're a woman. I said, wow, that's true, I'm a woman. So I just fit in because I wanted to belong to the team, but that should not be necessary, and it's up to us to make it not necessary, and be welcome to everyone. So these are the slides if anyone wants to download them. And questions, which is my favorite part, if there's any.
So I like what you said about having the dedicated person for the events, for the code of conduct. I've run a lot of meetups in the past, and the code of conduct, in the last few years has been something that I've thought about that I didn't used to think about in the past. But meetups are generally very small events, and it's hard to have a dedicated person for that because frequently it's just one person, organizing and running the events. Do you have any advice for that sort of situation?
Yeah, I would say because sometimes they want to report you, for example. So there should be, for example, somewhere else, an email they can write. For example, in the Cloud Native community, they can reach out to the CNCF. So I always make sure in the meetups that we say, hey, we can reach out to us if something happens. We are not dedicated. But if anything happens, there's a way to reach out to the CNCF and report that. So at least that helps a little bit. But yeah, for meetups, it's a little bit difficult because sometimes we are one or two on each meetup organizing. And I was probably thinking more of big conferences. My previous employee, we did that. Actually, I was one of the people in charge of the code of conduct. I didn't understand it at the time. I was a dedicated person with someone else for the conference. And we didn't do anything else. We were just points of contact, and that really helped, I think. But yeah, for me, that's probably a good question, but I don't have a solution.
No, that's fine. I'm just curious.
Yeah, it'd be nice. We try to do that. Just say, hey, there's a way that you can report that. If I'm not listening to you because I'm busy doing this and that, you can always go and report the CNCF.
Hello, question here. First of all, thanks for the presentation, Imma, and also being in the community, not only here, in Spain as well. So I have a question about the survivor bias, because the other day discussing with my mom, she asked me about, parity in my work, and the numbers weren't very good. So this survivor bias, have you found any study where other career paths where maybe women are more representative are asked why they took that instead of engineering or IT, because usually I see that the point of focus is why there are not many women in IT, but other career paths like education where it's more representative, like 80%, 90%, nobody says, okay, so the problem has two sides. So there is also less men, why they took that and not engineering. So sometimes the point of focus is in IT, there are no women, but in other places, it's different.
If you look at nurses, all of the nurses are usually women.
Like nursery or education. In Spain, it's usually more women there,
I think
but the focus is in IT.
I think this goes to education, and if you go to the UNESCO, they have very good reports on education side of things, and they address all the diversity issues in different sectors. It's not just tech. They say, okay, there's no parity in different sectors, and they have actually points on how to improve things. But I think it's very cultural why women study nursing, because we are caregivers, and why we don't study tech is because we think it's difficult, it's not something women should do. I don't know. That's what I was told when I was about to study engineering. They told me, why are you studying engineering? Is this something that women don't study? I didn't know. But yeah.
And this is something that I saw the other day also, that in IT didn't got the engineering title on it, and when they put engineering to it, the rate of women dropped by half. So this is something that I saw on LinkedIn some days ago, and it was like, why? Just by changing the name? People
sounds
is
like,
scared?
I think it's a cultural thing. It sounds like men should study engineering. Like now, doctors, there's a lot of women doctors. And it's also a very difficult career and very long one. But probably engineering is a term that scares women culturally because of the way we are brought up, probably. I don't know. Also, some countries have different ratios as well. Some countries are worse than others. So probably something with the upbringing that we need to address probably when they are young, 8, 10, 12 years old. It's when women usually stop STEM. They decide they're not going to study STEM careers. So.
Well, I hope more women are there, so we have people to reference. And
I find UNESCO has very interesting stuff on that, because it's the part of the education that they really work on that, on the gender gap that is in general everywhere.
I'll run. We have some fantastic women examples in engineering, civil engineering in London that have done fantastic big projects here. So when you're out and about, some of those projects have been led by women.
Thank you, Chris. Thanks for the presentation, super inspiring. Sometimes when these topics come up, one of the things that, well, I'd like to hear if you have some examples of situations where you felt included. You know, like there's a lot of examples and a lot of talks about the things that are happening where the opposite is the case, but sort of like, do you have like a good example of a story of, you know, a positive interaction or a situation where, yeah.
Pretty sure probably a lot. I do appreciate allies, for example, because women sometimes in the room when you say something, you feel like no one is listening. But if there's an ally in the room, it's gonna talk for you and say, hey, she already said that. So for me, that helps a lot. And yeah, having a facilitator that actually sees that women sometimes, we don't dare to speak up, and actually looks at, hey, who hasn't spoken so far? Or there's a woman who hasn't spoken. And trying to offer her the opportunity to speak, that has helped me a lot, because I was very shy also in meetings and everywhere. So if I didn't have someone who said, hey, Ima, do you have anything to say? If you say no, that's okay. But I think that allies help a lot in that. And I had very good experiences recently, to be honest, compared to 20 years back. I think it has changed a lot, but yeah, there's still room to improve, for sure.
Hello. One thing you mentioned during your talk was the meritocracy argument. I instinctively know it's nonsense when somebody says, oh, the reason there's only one woman in the team is because it's a meritocracy. It's, aside from saying you're talking bollocks and shutting that person down.
It's not very good argument, yeah.
Exactly, yeah. What is the best way of actually trying to demonstrate how rubbish that statement is?
I find it very difficult. Sometimes I try to counteract the argument and because sometimes they say, no, but we hired this woman and she's terrible. Didn't we ever hire a guy that was terrible? And do you say that this is because it was a guy? No. So meritocracy is also, I also now bring intersectionality into the conversation. Like, hey, some people have a lot of added problems, not just being a woman, so we need to be really careful about that. Because some people are not aware. People just think of privilege like you have it or you don't have it. But this wheel of privilege, actually, if you build it for yourself, it's very useful because you find that you have privileges and you have things that are not a privilege. Everyone has things that can cause discrimination. And whenever I show this wheel, actually, it has helped a lot to people don't feel like very confrontational, like it's about men and women. No. It's about a compound of discrimination, potential discriminatory things, but everyone has it. Like maybe someone doesn't speak English, so that in our sector is a problem. So guys also sometimes don't speak English. So it's something that when you bring that into play, I feel that they understand it a little better. Like it's not just about black and white. There's shadows in there. And if you can identify with some discrimination, then you can probably understand others. But I usually try to do that now. But before I discovered this, I didn't know how to do it.
Hey, Ima, thank you for the presentation. One thing really spoke to me is this difference between radical candor and brutal honesty. I was involved in a code of conduct thing lately. I thought I was radically candid, but turns out I was brutally honest. Do you have an example? Can you clarify the difference? Because for me, I'm still learning.
I don't know. I think it's a way to say it. Like if you're brutally honest, and I don't have a concrete example right now, but I think there's a difference between being just brutally honest and say, I don't like this, and trying to explain, hey, what do you think about this and that? Because when you make very concrete statements, sometimes you're very brutal, very direct. And sometimes it's also very cultural. Some cultures are very direct. I'm Spanish, I'm not that direct. So the ways I will say things are not as harsh. So I guess it's finding the balance. Also, that's why culture map is important, because if you're in the same culture, probably you're okay. Because some cultures are very direct, and they understand this. But when I talk, for example, from people from the Netherlands, you are more direct with feedback. And for Spanish people, that is like, oh my God, I'm not doing anything else because he told me that. And the way you told me, for your culture is perfect probably, but for my culture it's not. So trying to be, probably adjust to the cultures a little bit more. And feedback is just to help improve. It's not just to say, hey, this is wrong. No, this is wrong, no. I saw this, maybe I would suggest doing that. What do you think? Sometimes try to that the other person arrives to the conclusion without telling them. So great facilitators I've seen are people who don't tell you what to do, but they ask you a question, and then you think, oh, yes, this is what I should say, or this is what I think. But if people tell you directly something, you don't reach the same conclusion yourself, and you might be like, oh, okay, it's very direct, and I don't agree.
If it helps, I know that I have that problem when I communicate over text. So when I do things at work, it's much harder for me in the open source world, but when I'm able to communicate over voice, so hopping on a video chat, I don't have that same problem as I do when I do it over Slack or something like that. And so sometimes if you find yourself having that sort of problem where people think you're being brutally honest versus candid, let them see your face. And so sometimes that personal connection can make a big difference.
And the other thing you made me think now with ChatGPT and the likes, I do that a lot. Sometimes I want to say something to a user in our forum who's not being polite. I go to ChatGPT and say, hey, I want to tell this user this is not right. They are not following the code of conduct. But I want to say it in a way that's polite and that they don't feel attacked. And it proposes an email that's super nice. I say, oh, that's really nice. I wouldn't write that. So before that, it was difficult, but now for me, at least I try to use these tricks and say, hey, okay, I would like to say this is not correct, but how do I say it? So if you cannot speak in person. Make it polite. That's a good plugin that you can do.
Awesome, Ina. Thank you very much. Okay, next one will start at 10 to 6, last talk of the day. 10 to 6. Okay, we've reached the last talk of the day, 10 to 6. Yeah, woo! So we've got Marcus up next. No?
Yes?
Yes, good. You never nodded. Good
Cool.
to go.
Oh. Cool. Hello, everyone. For those of you that don't know me, I'm Marcus Noble. I'm a platform engineer that works at Giant Swarm, and I won't talk much about that, seeing as Joe covered it this morning in the first talk. But I work on, mainly these days, around release engineering, CI/CD, and some like general Kubernetes cross-provider stuff. I also recently started doing a monthly newsletter where I talk about all things cloud native and all the things that have happened in the past month. So if you're interested in that, do check it out. And as of now, I've got about 7 years experience working with Kubernetes in production. Started off as a full stack Node.js developer doing web apps, and I was responsible for trying out this new thing called Kubernetes for our team to see if it would work for our quite large e-commerce offering that we had in this big multinational company. Turned out to be pretty good, and I ended up running 3 clusters for our team, dev, staging, and production. Moved on in the same company to a more R&D role where I was doing best practices and like tooling and stuff for the entire multinational organization, so hundreds of different teams, and then moved on more into platform engineering, building out the stuff that we did at Giant Swarm, so some of the stuff that Joe talked about earlier this morning, and more recently around release engineering, CI/CD, testing, stuff like that. Now, I'm here to talk about pods and do a pods deep dive. Now, I've got a little bit of a confession to make to you all. When I submitted this talk, I wanted to tell you everything there is about pods. I got to 100 slides. It was an hour long when I did my first run through, so we're all here for 2 hours for the full thing. You're cool with that, yeah? So yeah, I can't do a pod deep dive into everything. Instead, what I'm going to talk about is the interesting bits, the things that I learned while doing this initial talk that took an hour and wasn't even everything, and the things that are just a bit weird, a bit strange, a bit stuff you might not know about when it comes to pods. So, without further ado, what is a pod? I'm sure if you've used Kubernetes, you've come across it at some point. But let's go for an official definition from the documentation. Pods are the smallest deployable unit of computing that you can create and manage in Kubernetes. What we mean by that, by the smallest deployable unit of computing, so this is something that runs our containers or our WASM or WebAssembly, whatever. It's generally seen as a wrapper around one or more containers or WASM functions, managed by the Kubernetes scheduler and assigned to nodes at runtime. Workloads within the pod, within a single pod, all share the same runtime context. So these are things like your Linux namespaces, the same local host, things like that. They are designed to be relatively ephemeral most of the time and disposable. So you will see them get deleted and new ones created. And for the most part, most of the pod spec is immutable. There's a few exceptions, so the image, the active deadlines, they can be changed at runtime, but everything else you will get an error from the Kubernetes API server. So, as I said, but there really are much more than that. Like, they're too much for us to cover. So I'm going to talk about some of the interesting, weird, or some of the surprising bits that I came across as part of this. And these are the kind of sections we're going to go through today. And I'm going to quite speed through this because it is still quite a long talk when I did this. So I hope you're all buckled in. So we're going to start off with containers. So I hope we all know about containers, seeing as we generally all work with Kubernetes. And we know that a pod is a wrapper around one or more containers. And so I'm not going to talk about your app containers in general. What I'm going to talk about first are these sidecar containers that were first introduced, that were enabled by default as of 1.29, so you can use them in the latest versions of Kubernetes. And what's weird about these is they are disguised, as I like to call them, as init containers. So the way you create a sidecar container is you define it as an init container, and you set this restart policy property to always. And that is the only value that can be on that property, is always. And this is not to be confused with restart policy at the pod level. Now, if you set restart policy always on your init container, it will start as your pod is launched right at the very beginning, along with all other init containers. But once your other init containers have completed, it will continue running, and it will continue running until after your app containers have finished, and then it will quite aggressively be terminated, much more so than your app containers. You will generally see much harsher sig terms followed by sigins in these sidecar containers, so don't rely on any shutdown logic, generally speaking. I personally hate this spec. The way that they've designed this and how confusing it is, I hate it. I'm sure there's reasons for it, but I just want to call it out that I'm not a fan. Now, ephemeral containers are very cool. These are designed for debugging and figuring out why are things broken. I use these a lot. These can't be defined on your manifest. So this ephemeral containers that you see here, this is a read-only property. You can't write this and do a kubectl apply. You have to do it through a special ephemeral containers handler using something like kubectl debug command that you see here at the top. One little caveat is they're not supported on static pods. So your API server, for example, you won't be able to use these. And you can target either the entire pod itself or specific containers within that pod using this container, target container name property. For the most part, they have the same spec as all other containers, except for they don't have support for things like ports, probes, resources, and life cycles, because they don't really make sense in this context. These ephemeral containers are really just a case of let's get an executable shell in this environment that we can play about with. And if you have one that's running, you can reattach to it at a later date using kubectl attach, so you can continue debugging in multiple sessions. Cool. Now, pause container. So these have been around since the very beginning of Kubernetes, I think from the very start, I'm not entirely sure. But what I found interesting about these is when I was actually trying to write this slide, the official documentation for Kubernetes, the only reference that I found for pause containers was on the documentation page about Windows containers, and nowhere else. Very strange, because they are all used for everything. For those that don't know, every pod that is created in Kubernetes gets a pause container. It's this empty container that its sole job is basically to set up the environment that that pod's going to run in. Create some cgroups, some reservations, it sets up the networking, that kind of thing. And it can be thought of as like a parent container for all the other containers that your pod's going to run. So even if your containers crash through bad code, environment issues, whatever, the pause container keeps running so that environment remains available for your containers to use again when they restart. You can't see these pause containers through the kubectl API, so if you do a get pod, you will not see these containers listed. But if you go onto the nodes itself and you, depending on your container runtime, use, for example, with containerd, if you use the CTR command, you can list out all of the containers running on that node, and you can like grep for pause containers. As you see here, we're using a giant swarm specific one in our environment. Cool. Containers are done. Let's have a look at images. I'm going to talk very quickly about these, but image pool policy, I'm sure you're all aware of this to one extent or another, but I just wanted to talk about the different defaults that are available with image pool policy, because they may not necessarily be totally clear. There are 3 values that you can have for your image pool policy on your container. If not present, always, or never. If not present will go and fetch the image from the registry, the container registry, if it's not already available on the node. So it'll have a look first if it's already in the node cache, and if not, go and get it. This is the default if you specify your image tag as latest or omit it completely, which then defaults to latest. The value always will always go and fetch the image from the registry. This is the default if you use, sorry, I got the defaults the wrong way around. The first one is if you don't specify latest, if you use a name tag. Always is if you do specify latest or omit the tag. Now what's interesting about always is it doesn't actually always go and download the image. It always goes and checks if it needs to download the image. So what it actually does, it calls the registry and says, what are the layer shards for this image? And it will check if it has those same shards on disk. If it does, it just uses those, doesn't download them. So you're not actually, it's quite nice that it won't actually waste bandwidth and all that kind of thing if you do use always. And then the final one is never. This is like the kubelet's like, the image better be there because I ain't doing anything about it if it's not. This is if you're using a third-party thing that will make sure images are available. Maybe you're in an air-gapped environment where your images have to be preloaded onto every node that you deploy. They have to be there. You can set things to never, and it will never try and call out to the internet. Image tags. Using a SHA-based image tag is best practice. The reason for this is you can be certain that the image you are pulling down is exactly the image you pulled down the previous time. Whereas named tags, so things that are like either latest, which is generally seen as mutable, that will always change as new things are available, but also things like your v1s, .2.3s, or whatever can also be mutable if you decide to do so in that image. Now, a SHA will always be the same. SHA is based on the content of that image. So best practice says, let's use a SHA so we are certain that what we're getting is not a virus, not malicious, not whatever. What's interesting is, when you do use a SHA, the tag is meaningless. It's completely ignored. This example here is not for 125.1. It's a completely different version, and it will pull down that completely different version, the one that matches the SHA. I can change that 125.1 to anything, and it doesn't care. But it still needs to be there. So be careful if you've got things like Renovate or Dependabot or stuff that updates these things in your GitOps files, that it does update the SHA and not just the tag, because otherwise you're not updating anything. Great, runtime class. So let's get to some actual running pods in this case. I'm going to talk about the runtime class resource and how it works with pods. So what this allows is for your cluster, for a single cluster, to have different runtime environments that it can support. By default, it will use whatever container runtime is defined on the node that that pod is running on. So this is your container D, this is your cryo, this is your Docker, whatever you have configured in your Kubernetes cluster by default. But if you want to use a different one that you have installed, you can specify this runtime class name that has to point to a runtime class resource within your cluster that defines the other runtime that you support. Now, for that to actually work, your node has to have that runtime installed. So it has to have that runtime handler installed on the node that your pod is going to run on. And to make sure that pods are only scheduled on ones that have that, you can use this scheduling node selector on the runtime class to say, here is a label selector where any nodes that have these labels will have this runtime installed, so only pods that use this runtime class will run on those nodes. Now, it's pretty rare, at least from my experience, that you will have multiple runtimes for your containers, so it's very rare that you'll see cryo and containerd. But where you will see this is with WASM. So the way that WASM generally works is for your containers in your cluster, you will probably run like containerd or whatever it is. And then for your WASM functions, you may use something like WASM Edge that you define as a secondary runtime class that you can then run your WASM functions in the same cluster as all your other containers. And this is how it works. Cool, static pods. So I mentioned these very briefly earlier when we were talking about ephemeral containers. But for those that aren't aware of what a static pod is, these are managed directly by the kubelet. These are managed directly by the kubelet, not by the API server. These are always bound to a single kubelet on a very specific node, and they are defined either through a directory of static YAML manifests or via a URL that points to a YAML manifest. Now, the example on the right here is an extremely cut-down version of a kube scheduler static pod that is just a file on disk on the control plane node. Now, this becomes a static pod, and what the kubelet will do is it'll see this file, and it will create this pod in our cluster, and it will also try and create what is called a mirror pod. A mirror pod is effectively a read-only view of a static pod in the Kubernetes API server, so that when you're doing kubectl get pods, you can see these static pods, and you can view the information about it. You can get the status, you can get the dedone stuff, but it's read-only. You can't make any changes to those through the API server. It doesn't do anything. To make changes, it has to be wherever the source is. They all get a suffix of whatever node they are running on, because these are specific to a specific kubelet and a specific node. So this kube scheduler will get something along the lines of kube scheduler control plane 1, and then for however many nodes we have. Because these are run by the kubelet and not by the API server, they cannot reference any other resources within our cluster because they don't know about them. They only know about containers, basically. So you can't have config maps as volumes. You can't have volumes, really, because you can't reference a persistent volume, you can't reference a config map, no secrets, nothing like that. So these are generally quite specific to just running containers. And the kubelet will watch these sources, so either the directory or the URL, and when new things are found or removed or whatever, it does kind of reconcile those in a similar-ish way to the Kubernetes API server does. Great. Let's talk about lifecycle hooks. I quite like these on our pods. not containers rather. There are two lifecycle lifecycle hooks that we can use on our containers. These are guaranteed to run at least once, but may be triggered multiple times. So if you can, try and make sure that that's fine and doesn't cause problems. As I said, there are two possible hooks that we can use here. There's a post start, which will run after our container has started. But there's no guarantee here as to whether it comes before or after the container's own entry point has run. So try not to rely on whatever happens in your entry point if you can. It's also worth pointing out here that the container that this hook belongs to isn't considered running until this post-start hook has completed. So don't have anything that just waits forever or watches, because your container will never be considered ready. An example of this is, I've taken this from the Cilium chart from Bitnami, where if you're running Cilium in a ENI AWS cluster, it does some IP tables stuff at startup. It doesn't include in the actual upstream Cilium image. It kind of does this as a hook. You've also then got pre-stop, which runs immediately before the container is terminated. So generally speaking, your application will get the sigterm command. It will do its shutdown logic, and then your pre-stop will occur. This can be used for things like cleanup logic. So in this example, they use it as an uninstall for the CNI plugin. I've used it myself personally in my home lab to back up an SQLite database to a persistent volume on a Nash share that I have in an empty dir at runtime and then just ship it off. There's three different mechanisms that you can use for these hooks. Generally speaking, at least from my experience, you'll see exec, which allows you to run a command within the container. You can also have HTTP get, which performs a HTTP get command against the container. I've seen this in situations where you've got a web application where you may have like a pre-cache endpoint. So you can have that call as part of your start hook to pre-populate a cache within that web server. And then if you enable the pod lifecycle sleep action feature gates, you can have this sleep, which just pauses it for a while. Conditions and readiness gates. So you've probably come across conditions multiple times when looking at Kubernetes resources. They all have them in some degree or another, or most have them. And these are on the status. And for pods, the kubelet manages 5, with one of them being beta, itself to tell you the state, the current state of the pod. Now, the first one I've got here is pod schedule. This will be true as soon as the pod has been assigned a specific node to run on. So this is when the scheduler has determined which node is best for it and has updated the pod spec.node name property with that node. The beta feature here is this pod ready to start containers condition. This lets us know when the sandbox and the networking is ready in the pod. Sorry. Containers ready is when all of our containers are ready. Quite straightforward. Initialized is true after all of our init containers have finished running, but not our sidecar containers because of, yeah. And ready is when everything is green, we're good to go. That means our load balance, our services can start pointing traffic to it. We can start scheduling workloads and whatever. And generally speaking, like each of these, I've not got it on the example here, but each of these usually have a machine-readable reason property that you can use to figure out if something's broken or not, and then like a human-readable message to be like, yeah, help me debug this, what's going wrong. Now, the reason I wanted to talk about these is because I wanted to introduce you to readiness gates, which I hadn't come across before, and I quite rarely use, at least from what I was able to find out. They've been around for a while. And readiness gates allow you to implement your own status conditions and have them as one of the checks that the pods will use as part of their is it ready or not. These have to be implemented by some external application, so you'll have another controller running in your cluster more than likely that handles is the readiness gate done. The way it works is it adds in this readiness gates, which is an array, and then this condition type is just a value here. This is an example from the AWS load balancer, ingress controller, whatever. It adds that, and then it will update this condition down here that has the same type, as the condition type. And in this example, what it does is once the ALB or NLB that is related to this service is ready and can start serving traffic to the pod, that will then update the status to be true, which, assuming everything else is true, we'll be able to set the pod's ready status to true as well. This means that until this external resource, this AWS ALB or NLB is available, we won't start serving traffic to this pod because we know it's not going to work properly because we rely on something external, and we can do this through registers. Config. So config, when I was doing this original talk, huge topic. Config maps, volumes, all this kind of thing, loads to talk about. That's a whole 2 hours worth right there. So this is going to be very brief, or very picked little bits out that either bugged me or found weird or whatever. So we're going to talk about environment variables first. One thing that I had come across before but never really registered with me was you can actually have dynamic environment variables in your container spec. So you can reference other environment variables in your environment variables. So here, this would actually come out as greeting would be hello world, because we can reference these other ones through this parentheses syntax rather than the braces syntax that you normally have when referencing variables in Bash and things. Now, where that might be useful, rather than the hard-coded example I had previously, is if you use it with the downward API. I love the downward API. This allows us to expose properties from our pod and a few other things as environment variables into our containers. You can't expose all properties. There is a subset of things you can, but you can expose things like some metadata from the pod's metadata, so the name, the namespace, the labels, annotations, things like that. You can expose some of the spec. So one of the things that you probably see in a fair few examples is the node name. So this gets added by the scheduler to the pod's spec.node name. This allows your container to then have an environment variable that says what node you are running on. You may need this for handshake logic with other pods in a replica set or something. Quite a lot of the status properties can be exposed. So the pod IP is often one that you will see here, so that the thing that your application knows what what IP it has to the outside cluster. And then you can also expose limits. So limits being your resource limits, so your CPU and your memory. This is very useful if you have applications where they need to know how much memory they are allowed to use without causing OOMs. So if you can tell your application, don't use more than what my limit is, it will not get, hopefully, not get to the OOM stage and kill your container. Now this, I hope you can kind of see where this dynamic environment variable might be useful, that you can then reference these other environment variables to build up more complex ones, perhaps. Cool. Volumes. Again, volumes, huge topic. Huge topic, but we're going to talk about a few things. This annoys me. When you're referencing config maps versus secrets as volumes. Config map is configmap.name, secret is secret.secretName, and I hate this inconsistency so much. I know it's never going to get fixed, but we need a V2 just to fix this. It bugs me. I have to look it up every single time. Again, we can use the downward API with volumes, so it doesn't have to just be environment variables that we use all these nice pods information. We can actually create files on disk, or in our pod, on a container, whatever. So for example, we can have the labels and the annotations created as files in our pod. So here, the path becomes the file name, and it's mounted into etc/podinfo/labels/annotations. Empty dirs. I'm pretty sure a lot of you will have used these to some degree or another, but generally speaking, you will see this as just curly braces, empty, no values set. What you may not know is it has a medium property. You can tell it what medium to use for the empty dir. By default, generally speaking, this is disk from the node that the pod is running on. So sort of like host path volumes, but not quite, a special directory, that sort of thing. You can specify memory, which creates an in-memory empty dir, an in-memory file system. So this is good if you need something that's very fast, writes to memory, reads out, all this kind of thing. Just be very aware that this will then take memory away from other workloads on that node, so maybe not the best, but if you do need something very fast, great. Size limit is a best practice to use, in my opinion. This allows you to specify the amount of disk space that this empty dir is allowed to have. This prevents you from utilizing or exhausting resources that other applications on the same node may need and break if they run out of. This works in a couple different ways depending on the medium. If it's if it's using the default, you will get, the pod will be evicted if it goes over this and get rescheduled. If the medium is memory, it actually just reports it back as no space left on device. So it's a bit inconsistent there, which is not great, but yeah. And then finally, not finally, we also have projected. Hadn't come across this one too much, but this allows you to kind of merge multiple volume sources together into a single volume mount. It doesn't support everything, so it supports secrets, config maps, download API, service account token, and cluster trust bundle. But for example, if you have a config map and a secret that has all your apps information in, you can use a projected volume type to then mount that as a single file in your application or whatever, or single mount point. And then one thing that I want to talk about that's still alpha as of 131 and therefore disabled by default is the ability to use OCI images as volume sources. So this is very cool and allows you to have things like, I've seen examples of machine learning models as OCI objects that then get mounted as directories within your pod through this kind of interface. And it's a similar sort of thing as with containers, same image pool policies, all this kind of thing. Scheduling, resource allocation. So I talked about this briefly. I'm not going to go into details about this. There is much more knowledgeable people that can talk to you about this. The reason I wanted to talk about resource requests and limits is because I didn't realize that you could have more than just CPU and memory. It's possible to define GPU, for example. So the NVIDIA GPU driver has this nvidia.com/GPU resource request and limit that you can define that tells you how much of a GPU your application wants to use. And you can have multiple of these, like AMD GPUs have the same or similar. And there's a few caveats here. So for the this GPU one, for example, they have to be the same. You have to specify limits. You can't specify, yeah, it's weird. But it's some limitations of the implementation. But like, you can have your own custom resources, which is pretty cool. And a KEP that's currently in progress is the pod level resources that allow you to have the same sort of thing, but rather than having all of the container level resources added together and exposed as the pod level, you can just define a single time for the whole pod and allows you to like more easily say this entire pod can't use more than a gig or whatever. Node assignment. So the only thing I want to talk about here is, because it's the only thing that was new to me and I hadn't really come across before, is topology spread constraint. Now, I haven't got much time left, so I'm going to be very quick about this, unfortunately. So please look it up elsewhere if you're interested. But this allows you to have more control over where your pods end up getting spread to. It has this concept of a skew, which is the number of pods within a given topology minus the minimum number of pods within any topology. Now, a topology is a grouping of nodes with a given label. So in the example I've got down here, we're using a zone label. So we've got zone 1 on the left, zone 2 on the right. And with our example, because our skew is 1, even though both of them match our pod's label selectors and all this kind of thing, it will attempt to put it into zone 2 because that gives us the least skew from what we want. It more evenly distributes them across. What's worth being aware of here is this is not guaranteed to be honored when scaling things down. So if you've got a horizontal pod autoscaler, when it scales down, you may end up with skew because of this. But when things get rescheduled, it should try and do it. Very quickly, I'm going to talk about priority and preemption. This allows you to say this pod is much more important than this pod. You can define this pod priority, this priority class, that you then associate with your pod. It's just a number. The bigger the number, the more important it is. And there's a few things you can do with this. Depending on whether you set the preemption policy to never or not on your priority class, if it's set to never, you won't evict other pods if a higher priority one comes along. If it's not set to never, then if a high priority pod needs to be scheduled and there are lower priority pods elsewhere, it will kick them off and get that scheduled. Otherwise, it's just a queuing thing. And I am very quickly running out of time. This is all I just want to say. You can have multiple schedulers, which is pretty cool. You can define a scheduler name on your pod spec and tell it which scheduler to use for your pod. So if you have something that's like super specific, super bespoke in your environment, you can have that handle it instead and decide where to go. Yeah. Networking, everybody's favorite thing, and obviously I can get through this very quickly. DNS, yeah, I'm going to skip over a bunch of this, but every pod gets a host name. The host name is generally the name of the pod, but that can be overridden either with the host name or the subdomain property. You can add some more host aliases and things like that. What I do want to talk about is the DNS policy, where the options are default, cluster first with hostnet, or none. The default is not default. The default is cluster first. There are reasons for this, but naming is hard, all this kind of thing. Default is actually the default from the node that you're running on. Whatever the node's DNS configuration is, that's the default. Generally speaking, you want cluster first, because that allows you to resolve things within the cluster. If you've got host network, you can use host with it, yeah. If you set it to none, then you have to tell it everything. So you have a DNS config, you have to define everything, and it creates basically a resolve.conf within your container, and you have to define where all your name servers are and things like that. So to wrap up, I hope this is better than the hour-long talk that I was originally going to give. And I hope there's at least still interesting things in here. I've been quite worried about this, that I wasn't able to actually include all the things that I wanted to because of there's a lot to cover. So hopefully at least some of this is still interesting and things like that. And I would very much appreciate feedback on this because it's the first time I've done this talk. It's a bit different for me. So good feedback, bad feedback. Found it useful, found it terrible, whatever, I would love to hear it. Reach out to me, come find me. Thank you very much.
We made it to the end of the day. Any questions? We've got time.
Do we?
There's no more talks.
Cool, we got 2 hours worth of questions. Let's go. Can I grab my drink first?
Thank you. Could you please go back to the slide with the host name and the subdomain name?
Yeah. Okay. I know everybody loves DNS.
Yeah, that one. But that one, most probably, doesn't create a DNS record, does it?
No. Yeah, I wish I had more time to talk about it. Yes, this is inside the pod itself. So this is the host name that the containers themselves see, not what other pods see. That's core DNS or whatever is responsible for that. So even if you set host name to my super cool host name, other pods within your cluster will still see it via the name of the pod because core DNS is responsible for that. Yeah, I hate that as well. I don't understand it. If somebody can explain to me why that is good, great, I'd love to hear. Anything else?
Anyone else? Awesome.
Cool. Thank you very much.
Thanks very much. See you all tomorrow.